Hey, 66 million years ago, Earth had a really, really bad day. And I mean the kind of bad day that makes everything after it look like a spa retreat. We're talking about a rock the size of a city slamming into our planet, at speeds that make fighter jets look like shopping carts. No survivors, no warning, just silence and then absolute chaos. But here is the wild part. That was not the end of the story, it was the beginning of ours. Before we get into it, drop a comment right now and tell me where you're watching from. What city? What country? What time is it there? I want to see the map fill up. Now get comfortable, because we are going back to a world so alien it barely resembles the one outside your window, and somehow it is the reason you exist. To understand where life on this planet went after that catastrophic moment, you first need to understand exactly what hit us, and more importantly, how it hit us. Because the popular image of a fireball streaking across the sky and landing with a loud boom is, to put it gently, the most dramatic undersell in the history of dramatic undersells. Picture the Yucatan Peninsula, 66 million years ago. It is a shallow tropical sea sitting on top of thick layers of limestone and sulfur-rich rock, not exactly the best real estate for absorbing a cosmic impact as it turns out. The asteroid itself was somewhere between 10 and 15 kilometers across. To give you a sense of scale, that is roughly the size of Mount Everest, except instead of sitting politely on the ground, it was hurtling through the atmosphere at around 64,000 kilometers per hour. For comparison, a commercial airplane cruises at about 900 kilometers per hour. This rock was moving roughly 70 times faster than that, which means the atmosphere had almost no time to slow it down in any meaningful way before it made contact with the surface of the planet. The energy released in that single moment was, by scientific estimates, equivalent to billions of nuclear weapons detonating simultaneously. Not one, not 100, billions. The explosion was so instantaneous and so violent that the rock itself did not so much land as it simply ceased to exist in solid form, vaporizing along with an enormous chunk of the Earth's crust in a fraction of a second. The crater left behind, now called the Chicxulub crater, named after a small town in Mexico near its center, stretched roughly 180 kilometers in diameter and was buried under subsequent layers of rock and ocean sediment for millions of years before scientists figured out it was there at all. Which is, in retrospect, a slightly embarrassing geological oversight, though to be fair, it is hard to spot something that big when you're standing on top of it. What happened in the first few seconds after impact is difficult to fully wrap your mind around. The shockwave that radiated outward from the impact site travelled through the planet's crust at tremendous speed, triggering earthquakes that would register well above magnitude 10 on the Richter scale, a level of seismic violence so far beyond anything recorded in modern history that the comparison barely means anything. The largest earthquake ever measured by modern instruments, the 1960 Chilean earthquake, registered 9.5. The Chicxulub-triggered tremors were orders of magnitude more powerful than that. Essentially, the entire crust of the Earth rang like a struck bell. Those seismic waves reached distant tectonic fault lines and volcanic systems that had been sitting in a state of geological tension for thousands or millions of years. In several locations across the planet, the sudden ground movement was enough to push already stressed volcanic systems past their tipping point. Volcanoes in what is now India, the massive Deccan Traps province, had already been erupting sporadically for thousands of years before the impact, releasing enormous volumes of lava and volcanic gas. The impact may well have dramatically accelerated that activity, turning a slow geological drip into something considerably more aggressive. Whether or not the impact directly caused the Deccan Traps eruptions is still debated among scientists, which honestly says more about the complexity of planet-scale geology than it does about the uncertainty of the catastrophe itself. Either way, things were not going well for anyone living on or near a shoreline. The tsunamis generated by the impact were in a different category entirely from anything we would recognize today. Modern tsunamis, caused by underwater earthquakes or volcanic collapses, can generate waves tens of meters high, devastating and terrifying. The waves produced by the Chicxulub impact have been estimated at hundreds of meters tall near the impact site, with the energy radiating outward and reshaping coastlines across the Gulf of Mexico region and beyond. Evidence of these waves' chaotic layers of jumbled sediment, displaced marine material dumped far inland, has been found across what is now the southern United States, in Texas, Alabama and Mississippi, in rock layers precisely dated to 66 million years ago. The Gulf of Mexico, essentially a closed basin at the time, acted like a bathtub being struck from below. The water had nowhere to go but up, and then outward, and then violently back again. All of this, the earthquakes, the tsunamis, the volcanic activity, happened within hours of the initial impact. It was, by any reasonable measure, a genuinely terrible afternoon. But here is the thing about all of those immediate effects. As catastrophic as they were not actually what killed most of the life on Earth. The earthquakes and waves were local and regional horrors. What came next was global, systematic, and considerably more patient. The real killer was the sky itself. When that asteroid vaporized into the Yucatan limestone, it did not just release energy, it also released the contents of the rocks it destroyed, and those rocks happened to contain something particularly unfortunate: enormous concentrations of sulfur compounds, locked up in the ancient carbonate deposits of the seafloor. Studies of the rocks around the Chicxulub crater have shown that the impact excavated through some of the most sulfur-rich geology on Earth. Had the asteroid hit almost anywhere else on the planet's deep ocean floor, granite continental crust, even slightly different sedimentary rock, the atmospheric effects would still have been severe, but potentially not quite as catastrophic as what actually happened. The universe, it turns out, has a dark sense of humour about real estate. The vaporized sulfur compounds shot upward into the stratosphere, along with billions of tons of pulverized rock, soot from global wildfires, and steam from the vaporized ocean water. This material did not simply drift back down. Fine particles in the stratosphere behave differently from dust at ground level. They circulate in high-altitude wind currents that can carry them around the entire planet within weeks, and then keep them suspended for years because there is no rain at that altitude to wash them out. Within a relatively short time, geologically speaking, the entire atmosphere of the planet was wrapped in a dense shroud of debris. The sunlight did not disappear all at once like someone flipping a switch. It faded and kept fading over days and weeks until photosynthesis became essentially impossible across most of the planet's surface. The term scientists use for this is impact winter, though calling it a winter is a bit like calling the Pacific Ocean a puddle. A normal winter involves reduced sunlight for a few months, followed by spring. What followed the Chicxulub impact involved reduced sunlight for an estimated decade or more. Some models suggest the photosynthetic collapse lasted between 10 and 15 years before the atmosphere cleared sufficiently for plant life to begin recovering in a meaningful way. During that period, surface temperatures across much of the planet plummeted, in some regions by as much as 15 to 20 degrees Celsius or more. To understand what this means for an ecosystem, consider that modern tropical forests, among the most biologically diverse environments on Earth, can be severely damaged by temperature drops of just 5 or 6 degrees. A drop of 15 to 20 degrees, sustained for years, in an environment that had previously never experienced frost, is not a stress event. It is an extinction event. Tropical ecosystems that had been evolving continuously for tens of millions of years simply could not cope, and most of them did not. The collapse of photosynthesis cascaded through every food chain on the planet with brutal efficiency. Plants died first, because they were the ones directly dependent on sunlight. The herbivores that ate plants followed, because their food supply had vanished. The carnivores that ate herbivores came next, for the same obvious reason. Large animals with high caloric needs were hit hardest and fastest. A creature that requires hundreds of kilograms of food per day to maintain its body mass does not have a lot of wiggle room when the entire plant kingdom starts shutting down. The dinosaurs, who had dominated terrestrial ecosystems for over 160 million years, found themselves on the wrong side of a metabolic equation that suddenly had no good answers. What is remarkable, looking at the fossil and geological record from this period, is how abrupt the transition appears. Geologists call the boundary between the Cretaceous and Paleogene periods the KPG boundary. It used to be called the KT boundary, before some reorganization of geological naming conventions, which is a level of drama that scientists rarely get to experience. In rock layers around the world, this boundary is visible as a thin layer of clay enriched with iridium, a metal that is rare in the Earth's crust but relatively common in asteroids. Below that layer, you find the fossils of Cretaceous life in extraordinary diversity: dinosaurs, ancient marine reptiles, ammonites, a full and complex biosphere. Above that layer, the silence is striking. The diversity of species does not decline gradually. It stops, almost as if someone drew a line. That iridium layer is, in effect, the fingerprint of the asteroid. When it was first identified in 1980 by physicist Luis Alvarez and his geologist son Walter Alvarez, it transformed our understanding of how life on Earth actually changes, not always slowly, not always through gradual competitive replacement, but sometimes in sudden, violent ruptures that rewrite the rules of survival overnight. The Alvarez hypothesis, as it came to be known, was initially met with significant skepticism from the geological and paleontological communities, who were very attached to the idea that everything in Earth's history happened slowly. Finding out that one of the biggest events in biological history happened in an afternoon was, for some researchers, a genuinely uncomfortable adjustment. Science, much like the dinosaurs, does not always appreciate sudden disruptions to established patterns. But the iridium layer was only part of the evidence that accumulated over subsequent decades. Shocked quartz, a distinctive form of quartz crystal that only forms under the extreme pressures produced by meteor impacts or nuclear explosions, was found in the same geological layer worldwide. Glassy spherules called tektites, formed from molten rock that was ejected into the atmosphere and cooled as it fell back to Earth, showed up in the boundary layer across multiple continents and ocean basins. Soot deposits consistent with global wildfires appeared in rock samples from around the world, and then, of course, there was the crater itself identified in the 1990s, using geophysical surveys of the Yucatan Peninsula and the Gulf of Mexico floor, buried under kilometers of later rock and sediment, but unmistakably real, and unmistakably the right size and age. The global wildfire component of the catastrophe deserves particular attention because it represents one of the most counterintuitive aspects of the whole event. When the asteroid vaporized on impact, it ejected an enormous amount of material rock, steam, and debris high into the atmosphere and even briefly into space. As that material came back down through the atmosphere, it heated the air through friction, in much the same way that a spacecraft heats up during re-entry. For a period of perhaps an hour or several hours after the impact, the upper atmosphere was hot enough to ignite forests and dry vegetation across enormous areas of the planet purely from the thermal radiation of all that falling debris. This was not fire spreading from a central point. It was, in effect, the atmosphere itself briefly becoming an oven. Fossil charcoal layers, technically called fusaine by paleobotanists, who apparently felt the situation needed a technical term, are found worldwide in Cretaceous boundary deposits, confirming that the fires were indeed global rather than regional. So to summarize what the planet looked like in the weeks and months following the impact, widespread fires had consumed or severely damaged most above-ground vegetation across large parts of the globe. Colossal waves had rearranged coastlines across the Gulf region. The sky was dark and growing darker, temperatures were dropping, the oceans were beginning to acidify as sulfur compounds dissolved into seawater, and the food chains that had been operating reliably for over 160 million years were starting to unravel from the bottom up. The magnitude of the biological loss that followed is genuinely staggering. By most estimates, somewhere between 75 and 80% of all species on Earth went extinct at or very shortly after the KPG boundary. In marine environments, the numbers were similarly devastating. The ammonites, those spectacularly diverse spiral-shelled mollusks that had been swimming in Earth's oceans for roughly 300 million years, were completely wiped out, not reduced. Not set back. Gone, entirely and permanently, in what amounts to a geological eye blink. The mosasaurs, large, predatory marine reptiles that looked somewhat like a cross between a Komodo dragon and a dolphin, and filled the role of apex ocean predator that sharks occupy today, vanished. The plesiosaurs, long-necked marine reptiles that had somehow survived multiple earlier extinction events and adapted through hundreds of millions of years of oceanic change, also disappeared at this boundary. On land, the non-avian dinosaurs, the enormous, dominant, astonishingly diverse group that had been the unquestioned kings of terrestrial ecosystems since the late Triassic, were gone. All of them, within what the geological record suggests was a relatively brief period. The last tyrannosaurs and triceratops and hadrosaurs did not go out fighting. There was no dramatic last stand. They simply found themselves in an environment that no longer supported anything their size, and they died, mostly from starvation and cold, probably without any particular awareness that they were witnessing the end of their 160 million year dynasty, which is, in its own way, one of the more melancholy facts in natural history. Before we get to the survivors, it is worth dwelling a little longer on the ocean, because the marine story of the KPG extinction is in some ways even more dramatic than the terrestrial one, and considerably less well known. Most people, when they think about the end Cretaceous extinction, think about dinosaurs, which is understandable. Dinosaurs are visually impressive and culturally embedded in our imagination in a way that foraminifera, for instance, are not. But the collapse of marine ecosystems at the KPG boundary was in many ways the more fundamental catastrophe, because the oceans had been, for hundreds of millions of years, the most reliably productive biological engine on the planet. At the base of almost every marine food chain are tiny photosynthetic organisms, phytoplankton, cyanobacteria, microscopic algae. These organisms are so small that they are invisible to the naked eye individually, but collectively they produce roughly half of all the oxygen on Earth and form the nutritional foundation of essentially every ocean ecosystem. When the sky went dark after the impact, these organisms were affected just as profoundly as land plants. Photosynthesis stopped, and without photosynthesis at the base of the food web, the entire marine ecosystem began to collapse from the bottom upward, in the same cascading pattern that occurred on land, but across an even vaster and more interconnected system. The chemical composition of the oceans also changed dramatically and rapidly after the impact. All those sulfur compounds ejected into the atmosphere by the impact did not stay there permanently. Over the years following the event, they gradually came back down, dissolved in rainwater as sulfuric acid, falling as acid rain across both land and sea. For marine organisms with calcium carbonate shells or skeletons, this was particularly lethal. Acidic water dissolves calcium carbonate with ruthless chemical efficiency. The ammonites, whose spiral shells were made of exactly this material, had no evolutionary defense against ocean acidification. They had survived previous extinction events, multiple ice ages, massive volcanic eruptions, but they had never encountered anything quite like this particular combination of darkness, cold, and chemical assault. The KPG boundary was, for them, the final boundary. It is worth pausing to appreciate just how extraordinary the ammonites were before they vanished, because they deserve more than a footnote in the extinction narrative. Ammonites had been living in Earth's oceans for approximately 300 million years before the asteroid arrived. They first appeared in the Devonian period, diversified through the Carboniferous and Permian, survived the catastrophic end Permian extinction that killed over 90% of all marine species, diversified again through the Mesozoic, and by the late Cretaceous had evolved into hundreds of distinct species, ranging from thumbnail-sized to nearly 2 meters in diameter. Some were tightly coiled in the classic spiral shape. Others were loosely wound or straight, or shaped like paperclips, a form technically called heteromorph ammonites, which sounds like it could be a character from a science fiction film. They were ecologically diverse, filling roles from slow-moving bottom dwellers to fast-swimming predators of the open ocean. And then, at the KPG boundary, they stopped. All of them. Every species. The shell shapes that had diversified and varied through 300 million years of evolution simply ceased to appear in the rock record above that thin iridium layer. The mosasaurs, those large marine predators mentioned earlier, deserve similar consideration. They were not actually dinosaurs. Despite their reputation in popular culture, they were more closely related to modern monitor lizards, having evolved from a lizard ancestor that entered the sea during the late Cretaceous and rapidly diversified into an astonishing range of body sizes and ecological niches. Some mosasaur species were relatively modest in size, perhaps 3 or 4 meters long. Others grew to 14 or 15 meters longer than most modern busses and considerably more aggressive about what they ate for breakfast. They had flexible jaws lined with conical teeth, strong tails built for powerful swimming, and they had effectively conquered the open ocean during the last 20 million years of the Cretaceous. Fossils of mosasaurs are found in marine deposits on every continent, including Antarctica, which was considerably warmer and more hospitable in the Cretaceous than it is today, though still probably not somewhere you would choose to vacation. Like the ammonites, mosasaurs vanish completely at the KPG boundary, leaving behind not even a single lineage that survived into the Paleogene. The contrast with what happened to sharks in this context is instructive. Sharks had been around for over 400 million years by the time of the Chicxulub impact, having survived every major extinction event in the planet's history, including the catastrophic end Permian event. They survived the KPG extinction as well, reduced in diversity certainly, and the massive Cretaceous shark species that competed directly with mosasaurs for apex predator status were gone, but the fundamental shark body plan and way of life persisted. Why? Partly because sharks are remarkably metabolically efficient. They can go for extended periods with very little food, a useful trait in an ocean where the food web has just partially collapsed. Partly because their body plan is ancient and proven, and partly perhaps because the smaller species that survived the Cretaceous were not dependent on the kind of large prey that itself went extinct. Flexibility, in an extinction event, is worth more than specialization. This is a theme that repeats itself throughout the KPG extinction story with striking consistency. The survivors were almost never the biggest, the most powerful, or the most evolutionarily sophisticated by the standards of the Cretaceous world. They were the flexible ones, the ones that could eat almost anything, the ones that could go dormant or slow their metabolism or burrow underground or drop into a state of torpor and wait for conditions to improve. The ones whose biology did not depend on the continued functioning of the complex ecological systems that the impact had just destroyed. On land, this pattern was dramatically illustrated by what happened to the crocodilians. Modern crocodiles and alligators are sometimes described, with a mixture of admiration and exasperation, as living fossils organisms that have changed relatively little over tens of millions of years. And while that description is an oversimplification, it contains a kernel of important truth. The crocodilian body plan, low-slung, heavily armoured, semi-aquatic, capable of going months without eating, able to regulate body temperature by moving between water and land, turns out to be one of the most durable designs in the history of vertebrate life. Crocodilians were present in the Cretaceous, and they survived the KPG extinction essentially intact. They did not thrive. Exactly the immediate aftermath of the impact was genuinely terrible for almost everything, but they persisted, and that was enough. Being the best swimmer in the Cretaceous would not save you. Being an animal that could lie in a muddy river and barely move for 3 months while waiting for something edible to wander past turned out to be an unexpectedly excellent long-term strategy. Turtles tell a similar story. Turtles had been around since the Triassic period, over 200 million years before the KPG impact, and they had developed a body plan that, much like the crocodilians, prioritized defense, longevity, and metabolic flexibility over speed, aggression, or ecological specialization. They could eat almost anything organic. They could reduce their metabolism dramatically during periods of cold or food scarcity. Their shells, far from being merely defensive armor, also served as mineral reserves that could be metabolized during extended periods of nutritional stress. And they survived, not brilliantly, not without loss, but they survived. The sea turtles of today are the direct descendants of lineages that lived through the end of the Cretaceous, which gives them a reasonable claim to being among the most proven survivors in vertebrate history. The insects, collectively, barely noticed. Or at least that is somewhat how it appears in the record, which is not to say that no insect species went extinct at the KPG boundary, because many certainly did. But the class as a whole, with its extraordinary diversity of species, its short generation times, its capacity for rapid evolutionary change, and its vast range of metabolic strategies and dietary habits, proved deeply resilient to even this level of disruption. Insects that depended entirely on specific plant species, or specific ecological relationships with other animals, were certainly hit hard. But generalist species, those that could eat decaying organic matter, fungal growth, or almost any available organic substrate, were in a much better position. The dead and dying Cretaceous world was, in a grim sort of way, a feast of decomposing material, and the organisms best equipped to exploit that kind of resource were exactly the ones that survived. Which brings us to the mammals. Because the story of mammalian survival through the KPG extinction is simultaneously one of the most important and one of the most humbling stories in the entire history of life on Earth. Humbling specifically for us because the creatures that would eventually give rise to all modern mammals, including humans, survived the end of the Cretaceous not through any particular strength, intelligence, or evolutionary sophistication. They survived because they were small, they lived underground, and nothing large enough to eat them was still alive and functional enough to bother. Mammals had existed alongside dinosaurs for over 160 million years, and for almost all of that time they had been, by the standards of the Mesozoic world, utterly unimpressive. The largest Cretaceous mammals were roughly the size of a modern badger. Most were considerably smaller, mouse-sized or rat-sized, nocturnal, insectivorous, or omnivorous, living in burrows or rock crevices and coming out to forage at night when the large predatory dinosaurs were less active. This lifestyle, which had been forced upon them by the ecological dominance of the dinosaurs, turned out to be exactly the set of adaptations needed to survive an impact winter. Small body mass meant low caloric needs. Burrowing behaviour provided insulation against the temperature crash at the surface. Omnivorous diets meant flexibility in what they could eat as different food sources appeared and disappeared. Short generation times meant that populations could recover relatively quickly once conditions began to improve. There is something almost poetic about this, the 160 million years of being squeezed into the margins of the Mesozoic world, of being small and hidden and generalist, of never being allowed to grow large or specialized, turned out to be the perfect training program for surviving a catastrophe. The dinosaurs had spent those same millions of years perfecting the art of being exactly what the Cretaceous world rewarded, and then found themselves completely unprepared when the rules changed overnight. The mammals had spent those years becoming exactly the kind of flexible, low-maintenance, hide-and-wait survivors that the post-impact world would favour. The great KPG extinction was, for the mammals, not the end of anything, it was the starting gun. Birds, it should be noted, also survived, and this is because birds are not, in the strict technical sense of the word, distinct from dinosaurs at all. Birds are avian dinosaurs, the direct descendants of theropod dinosaurs, the same group that includes Tyrannosaurus and Velociraptor, and the only dinosaur lineage to make it through the KPG boundary. Why birds survived when all other dinosaurs did not is a question that has generated considerable scientific debate. The current leading explanation involves a combination of factors. Birds were small, low caloric needs, many species were capable of eating seeds, which can persist in the soil long after the plants that produce them have died, and many were capable of flight, allowing them to range widely in search of food in a disrupted landscape. The seed-eating hypothesis is particularly interesting because it suggests that what saved the ancestors of modern birds was essentially the same dietary flexibility that saved the mammals the ability to eat something other than what the Cretaceous ecosystem had been providing. The months and years immediately following the impact were, even for the survivors, desperately difficult. The global temperature crash did not reverse overnight. The atmosphere did not clear in a season. The food webs that had been disrupted did not reassemble quickly. The full recovery from the Chicxulub impact in the sense of returning to a world with complex, highly diverse ecosystems took roughly 10 million years. That is a number worth sitting with for a moment. 10 million years to recover from a single afternoon. And even after that recovery, the world that emerged was not the same world that had existed before. The specific species, the specific ecological relationships, the specific food chains, all of those were gone and replaced by entirely different configurations. The KPG extinction did not merely set the clock back, it reset the board entirely and started a new game with different pieces. What is not worth noting is that not everything died. Far from it, in fact. And understanding what survived and what did not tells us something profound about the nature of resilience, which turns out to look nothing like strength, nothing like size, and nothing like the dominant strategy of the moment. But that part of the story comes next. For now, it is enough to sit with the scale of what happened on that particular day in the Cretaceous and appreciate that the world we live in, every forest, every ocean, every species, including our own, exists not despite this catastrophe, but in a very direct and measurable sense because of it. The asteroid did not just end one chapter of life on Earth. It cleared the space for an entirely different story to begin, one that would eventually, after an improbable series of evolutionary detours and climate shifts and geological accidents, produce something sitting in front of a screen trying to understand how it all started. The universe works in genuinely mysterious ways. Sometimes those ways involve a very large rock, so we have established that the impact itself was spectacular, global, and deeply inconvenient for almost everything alive at the time. But here is where the story gets chemically interesting and genuinely more complicated than most people realize. because the asteroid did not kill most species by hitting them. The direct blast radius, enormous as it was, affected a relatively contained geographical area. What killed 3/4 of all life on Earth was something considerably slower, considerably less dramatic, and in some ways considerably more sinister. The chemistry of what that asteroid did to the atmosphere on its way in, and to the rocks it hit when it arrived. The Yucatan Peninsula, as geological real estate goes, was spectacularly unlucky in terms of what it was made of. Not unlucky for the asteroid, which did not particularly care about local mineralogy, but unlucky for everything else alive on the planet. The rocks of the Yucatan are primarily anhydrite and limestone, ancient marine sediments full of calcium sulfate and calcium carbonate, deposited over hundreds of millions of years when this region sat beneath a shallow tropical sea. These are not inert materials. When subjected to the kind of temperatures and pressures generated by a hypervelocity asteroid impact, they do not simply vaporize cleanly. They react. They release their chemical components in a violent, sudden outgassing event that turns the impact site into something resembling the world's least pleasant chemistry experiment. The sulfur content of those Yucatan rocks was, in a word, extraordinary. Estimates based on the composition of the target rocks and the size of the impact suggest that somewhere in the vicinity of 100 billion tons of sulfur dioxide and sulfur trioxide were blasted into the upper atmosphere in a matter of seconds. To put that in perspective, the largest volcanic eruptions in modern history events like the 1991 eruption of Mount Pinatubo in the Philippines, which cooled global temperatures by roughly half a degree for about 2 years, released somewhere between 15 and 20 million tons of sulfur dioxide. The Chicxulub impact released approximately 5,000 to 7,000 times more sulfur than Pinatubo, in a fraction of the time. If Pinatubo was a moderately bad day for the atmosphere, Chicxulub was something that does not really have a useful comparison in modern experience. Sulfur dioxide in the stratosphere behaves in a very specific and well-understood way. It reacts with water vapour to form tiny droplets of sulfuric acid, which then remain suspended as aerosol particles. These particles are extraordinarily effective at scattering and reflecting incoming solar radiation, far more effective, molecule for molecule, than simple dust or soot. A sufficient concentration of stratospheric sulfate aerosols can reduce the amount of sunlight reaching the surface to a small fraction of normal levels, and they persist in the stratosphere far longer than ordinary dust because there is no precipitation at those altitudes to wash them out. They eventually settle by gravity, but very slowly. Estimates for how long the sulfate aerosol veil from the Chicxulub impact remained thick enough to significantly reduce surface sunlight range from several years to over a decade, with most models clustering around 10 to 15 years of meaningful photosynthetic suppression. This is what scientists technically call an impact winter, though the word winter, as mentioned, rather undersells the duration and severity. A typical winter lasts 3 months. What followed Chicxulub lasted, in its most intense phase, potentially longer than some entire geological periods in Earth's early history. And unlike a normal winter, it did not end with spring. It ended when the aerosol particles finally settled out of the stratosphere, which they did on their own schedule regardless of whether anything on the surface was surviving or not. But sulfur aerosols were only part of the atmospheric insult. The impact also injected enormous quantities of fine rock dust and soot from global wildfires into the atmosphere, contributing additional light-blocking material. Recent studies using climate models calibrated against ice core data from ancient volcanic events have suggested that the soot component generated by those planetary-scale fires discussed earlier may actually have been the dominant factor in the initial temperature crash, with the sulfate aerosols taking over as the longer-lasting suppressant once the initial soot settled out. The precise relative contributions are still being refined as climate models improve and as more geological samples are analysed. What is not in any serious scientific doubt is that the combined effect produced one of the most dramatic and rapid climate shifts in the geological record, and that it was sustained long enough to be genuinely catastrophic for the vast majority of complex ecosystems that had been functioning perfectly well the previous Tuesday. The temperature effects were not uniform around the planet. The Chicxulub impact happened in a tropical region, and tropical ecosystems, which had evolved in an environment of consistent warmth and had no biological toolkit for dealing with sudden cold, were in some respects more vulnerable than ecosystems at higher latitudes that had some prior evolutionary exposure to seasonal temperature variation. Polar regions, paradoxically, experienced less relative temperature change than the tropics, not because they were protected, but because they were already cold enough that an additional drop mattered less in absolute terms, even if the biology there was already stressed. The thermal gradient across the planet's surface, which had been relatively gentle in the warm, ice-free Cretaceous world, became dramatically steepened during the impact winter years. The surface temperature drop at tropical latitudes has been estimated in various studies at somewhere between 10 and 20 degrees Celsius during the peak of the impact winter. In a world where tropical forests had been growing at consistent temperatures for millions of years, a sudden 15-degree drop is not a cold snap. It is an ecological catastrophe. Tropical trees, which in the Cretaceous had no evolutionary mechanism for cold hardening or dormancy, could not survive sustained temperatures near or below freezing. When they died, the animals that depended on them died too, or dispersed into an increasingly hostile landscape looking for food that was becoming increasingly scarce everywhere. The scale of the ecological unravelling was not dramatic in the way that the impact itself was dramatic. It was quiet, gradual and inexorable, which in its own way is considerably worse. The acid rain aspect of the post-impact chemistry is something that tends to get less attention in popular accounts, probably because it is harder to visualise dramatically, but it was a significant factor in both terrestrial and marine ecosystem collapse. Sulfur dioxide in the atmosphere, when it eventually descends back toward the surface, combines with water vapour in the lower atmosphere to form sulfuric acid precipitation. Normal rainwater is already mildly acidic, with a pH of around 5.6. Acid rain from industrial pollution, which we are moderately concerned about in modern environmental contexts, typically has a pH of around 4 to 4.5. The precipitation that fell in the years and decades following the Chicxulub impact is estimated to have been considerably more acidic than that acidic enough to leach nutrients from soils, damage or kill vegetation directly, and alter the chemistry of rivers, lakes, and shallow coastal waters in ways that were deeply hostile to freshwater and nearshore marine life. For organisms with calcium carbonate shells or skeletons, and this includes an enormous proportion of marine invertebrates, acidification is a direct and efficient killing mechanism. Acidic water dissolves calcium carbonate with chemical indifference. It does not matter how well adapted an organism is to its environment, how many millions of years its lineage has been refining its shell-building biochemistry. If the water around it becomes acidic enough, the shell simply dissolves. The ammonites, as established, were gone by the end, but they had plenty of company among the calcareous organisms of the Cretaceous oceans, bivalves, corals, echinoderms, and the vast communities of calcite-secreting microorganisms that formed the base of marine food webs all suffered catastrophic losses at or just above the KPG boundary. There is a somewhat uncomfortable irony in the fact that ocean acidification, one of the primary concerns associated with modern human-caused climate change, was also a central mechanism of the end Cretaceous mass extinction. The chemistry is slightly different. Today's ocean acidification is driven by dissolved carbon dioxide rather than sulfuric acid, and it is happening on a timescale of decades rather than years. But the basic biological consequences for calcareous marine organisms are broadly similar. The oceans of the late Cretaceous, in a geological eye blink, became considerably less hospitable to shell-building life. Given that shell-building life had been one of the foundations of marine ecosystems for hundreds of millions of years, this was, as understatements go, a fairly significant development. What is easy to overlook, amid all the chemistry and physics of the impact itself, is the sheer duration of the difficult period that followed. 66 million years of geological distance can compress these timescales in our imagination. We talk about the KPG extinction as if it were a single event, a moment, a page turn in Earth's history. But for the organisms that lived through it, the recovery was measured not in days or seasons, but in generations, centuries, and millennia. The initial impact was a single terrible day. But the dark years that followed were not years in the sense we experienced them. They were approximately 3,650 to 5,475 days of reduced sunlight, falling temperatures, acid precipitation, collapsing food supplies, and biological attrition, followed by a gradual and uncertain recovery that continued for millions of years afterward. Understanding this duration matters because it helps explain something that puzzles people when they first look at the KPG extinction data. Why did some apparently vulnerable organisms survive while some apparently robust ones did not? The answer, often, is time. An organism can survive a bad season. It can survive a bad year. But 10 years of reduced food availability, cold temperatures and chemical stress is a fundamentally different challenge, one that selects not for the traits that made an organism successful in the Cretaceous world, but for traits that allow it to persist through extended periods of scarcity and instability. This brings us, in a rather roundabout but entirely logical way, to the biology of the Dark Age itself specifically, to the question of who managed to make it through and why. And the answer, as established in the previous chapter, had almost nothing to do with being impressive. The survivors of the KPG extinction were almost uniformly small. This is not a coincidence. Body size and metabolic rate are linked in a relationship that biologists call Kleiber's law. Larger animals require exponentially more food per unit time than smaller ones, not just proportionally more. A single large dinosaur might have needed hundreds of kilograms of plant matter per day to maintain its body mass and temperature. A small mammal weighing 50 grams might survive on a handful of insects and seeds. In a world where the food supply had been catastrophically reduced and would remain reduced for years, this difference was not a matter of comfort. It was a matter of survival. The burrowing behavior of early mammals deserves particular credit here, and it is worth thinking about this more carefully than the simple narrative of hiding underground might suggest. Burrows are thermally stable environments. The temperature inside a burrow, even in the aftermath of an impact winter, would have remained far more consistent than surface temperatures, which were swinging dramatically as the atmospheric aerosol veil unevenly affected different regions and seasons. Soil also retains moisture better than the surface, meaning that burrow-dwelling animals had access to a more reliable microhabitat even when the surface world was experiencing the equivalent of a prolonged environmental catastrophe. And importantly, soil itself contains nutrients, fungal networks, roots, invertebrate communities that persisted even when surface plant life was gone. The underground world was, by the grim standards of the immediate post-impact years, a relatively sheltered place to be. The fungi deserved a great deal of evolutionary credit in this period, though they rarely receive it in popular accounts. When plants die in large numbers, the organic material does not simply disappear, it decomposes, and decomposition is primarily driven by fungi and bacteria. In the immediate aftermath of the KPG impact, as plants died in vast numbers across the planet, there was an extraordinary pulse of organic material available for fungal decomposition. Fungal spores, preserved in rock samples from the KPG boundary in multiple locations, show a dramatic spike in diversity and abundance in the period immediately following the impact. Fungi do not need sunlight. They do not need photosynthesis. They feed on dead organic matter, and suddenly there was an almost inconceivable supply of exactly that. This fungal proliferation was, in its quiet way, one of the most important ecological processes of the early post-impact period. Fungal networks provided food for a range of soil-dwelling invertebrates, springtails, mites, beetle larvae, earthworms, which in turn provided food for small insectivorous mammals and surviving birds. The entire above-ground ecosystem might have been largely destroyed, but the below-ground decomposer network continued functioning, and it was this network that kept the food web barely alive during the darkest years, threading a narrow biological lifeline between the collapse of the Cretaceous world and the eventual recovery of the Paleogene. Seed banks played a similarly crucial role in the eventual recovery of plant communities. Seeds, particularly those with hard outer coats, can remain viable in the soil for extended periods under adverse conditions. The fires and cold of the impact winter killed enormous numbers of living plants, but buried seeds, particularly those of flowering plants, which had evolved a remarkable diversity of seed dormancy mechanisms during the Cretaceous, survived in the soil, waiting for conditions to improve. When the atmospheric aerosol veil finally began to thin and sunlight started returning to the surface in meaningful quantities, those seeds were ready. The recovery of plant life was not a slow process of recolonization from distant refugia. Much of it happened from the soil up, as dormant seeds germinated in response to returning warmth and light. This is where the famous fern spike comes in, and it is worth pausing on this particular piece of evidence because it is one of the most visually striking signals in the entire KPG geological record. In rock samples from the Boundary period, collected from dozens of locations across multiple continents, there is a distinctive and consistent pattern in the spore and pollen record. Above the impact layer, the diverse assemblage of Cretaceous plant species essentially vanishes, replaced almost immediately by an overwhelming abundance of fern spores. In many samples, fern spores constitute 70, 80, or even 90% of all plant reproductive material in the layers immediately above the impact horizon. This is the fern spike, and it reflects a real ecological phenomenon. Ferns are, in the technical language of ecology, pioneer species. They were producing spores rather than seeds, and spores are extraordinarily light, numerous, and capable of travelling vast distances on wind currents. They can colonize bare mineral soil with minimal organic matter, the kind of surface left behind after fires and the death of the pre-existing vegetation. They have underground stems called rhizomes that can survive fire and cold and resume growth when conditions improve, giving them a head start over seed plants that need to germinate from scratch. And crucially, ferns were already well adapted to disturbed or marginal environments in the Cretaceous, having coexisted with the flowering plants that had largely pushed them out of more favourable habitats. The post-impact landscape, stripped of the complex forest ecosystems that flowering plants had built, was effectively empty of competitors, and ferns moved in. The fern spike lasted, in most geological sections, for a few thousand years, a blink in geological time, but long enough to represent several hundred generations of ferns and the animals that fed on them. After that, the flowering plants began to reassert themselves. Their seeds, germinating from those preserved soil banks, allowed them to quickly re-establish communities as temperatures rose and light returned. The ferns did not disappear. They are still very much with us today, in exactly the same ecological role they occupied in the post-Cretaceous recovery, but the botanical succession of the early Paleogene moved rapidly from fern-dominated pioneer communities toward increasingly complex, diverse, and ultimately forest-forming plant assemblages. The recovery of animal communities tracked this botanical succession closely, which is exactly what you would expect from ecosystems where plants form the productive base. As plant diversity recovered, the herbivore communities that fed on plants began to diversify. As herbivore communities diversified, the predator communities that fed on herbivores followed. But critically, this was not the same community of animals reassembling. The dinosaurs were gone. The large herbivorous mammals that would eventually replace them were not yet large. Evolution does not work that fast. The early Paleogene was a world of small animals rebuilding from the ground up, exploring ecological space that had been emptied by the extinction, with the cautious curiosity of organisms that had never, in their evolutionary history, been given this kind of room. The crossing of what scientists call the ecological release threshold, the point at which the ecological constraints imposed by the dominant organisms of the Cretaceous were sufficiently relaxed to allow new forms to expand, is one of the most fascinating transitions in the entire history of life. The mammals, in particular, showed a rate of evolutionary diversification in the early Paleogene that has no real parallel in their previous 160 million year history. Within a few million years of the KPG boundary, mammal body sizes began to increase. New ecological roles were explored. New dietary strategies appeared. Species that had been insectivorous generalists began to differentiate into herbivores, carnivores, frugivores, and specialists of various kinds. The evolutionary acceleration was not magic, it was simply what happens when 160 million years of ecological constraint are suddenly removed. What is genuinely remarkable about this recovery is how it was driven not by the strongest or the largest, or the most sophisticated survivors, but by the most flexible, the most hidden, and the most seemingly unimpressive. The Dark Age after the KPG impact was, in biological terms, a great equalizer. The criteria for success that had operated for 160 million years, size, speed, specialization, metabolic efficiency at scale, were replaced overnight with a completely different set of criteria. Small, flexible, hidden, low maintenance. And the organisms that had been shaped by the long Mesozoic marginalization of mammals and the extraordinary resilience of fungi and ferns and small burrowing reptiles turned out to be precisely the right shapes for the new world that was slowly, tentatively beginning to emerge. There is one more aspect of the Dark Age biology that deserves attention before we move forward. because it illustrates something important about how survival actually works, at the level of individual organisms rather than species. And that is the question of behavioral flexibility specifically, what the surviving animals actually did differently in the years immediately following the impact, and why those behaviors made the difference between a lineage that persisted and one that did not. Consider the dietary shifts that occurred in early Paleogene mammal populations. The fossil record, combined with isotopic analysis of fossil teeth, shows that many early Paleogene mammals rapidly shifted their diets in response to the collapse of their normal food sources. Species that had been primarily insectivorous began incorporating seeds, fungi, and plant detritus into their diets. Species that had included some plant material in their diets became more broadly omnivorous. This flexibility was not a conscious adaptation. Individual animals do not choose to evolve. But populations with individuals that happened to have slightly broader dietary tolerances survived at higher rates than those without, and over generations the surviving populations showed increased dietary breadth. This is natural selection working in real time, driven by a selection pressure so intense that its effects show up clearly even across the relatively coarse timescales visible in the fossil record. The same pattern appears in body size data from the early Paleogene. In the first few million years after the KPG boundary, mammal body sizes were extremely small and relatively uniform across groups. Then, as plant communities recovered and food availability increased, there is a clear trend toward increasing body size in many lineages, with the rate of size increase tracking closely with the pace of ecosystem recovery. Groups that found themselves in environments with recovering plant productivity grew larger faster. Groups in areas where recovery was slower stayed smaller for longer. The match between ecological opportunity and evolutionary response is striking enough to be visible, even with the limited temporal resolution of the fossil record, and it reinforces a point that cannot be overstated. Evolution in this period was being driven not by gradual long-term pressure, but by the acute, immediate, survival or death consequences of a world that had just been thoroughly demolished and was trying to put itself back together. The insects, which have received perhaps less attention in this narrative than they deserve given their enormous importance to terrestrial ecosystems, showed their own version of this post-impact resilience. Insect diversity at the KPG boundary did take a significant hit, particularly among groups closely associated with specific plant species or specific ecological roles tied to the Cretaceous world. But the overall class of insects, with its extraordinary diversity of body plans, reproductive strategies, metabolic capabilities, and dietary habits, proved extraordinarily difficult to damage at a fundamental level. Within a few million years of the KPG boundary, insect diversity was already recovering strongly, tracking the recovery of plant communities that insects pollinated, lived on, ate, and decomposed after death. The partnership between flowering plants and insects, which had been one of the great evolutionary stories of the Cretaceous, resumed in the Paleogene with new species taking the old roles, rebuilt from the scattered survivors of both groups. One of the most striking aspects of the post-impact recovery, looking at it from a sufficient distance, is how it demonstrates what biologists call ecological redundancy. In a complex ecosystem, many species occupy roughly similar ecological roles. There are multiple species of ground-dwelling herbivores, multiple species of mid-level predators, multiple species of seed dispersers and pollinators. This redundancy seems, from the perspective of a single species, like wasteful competition. But from the perspective of ecosystem stability, redundancy is a safety net. If one species is lost, another can expand to fill the vacated role, maintaining the ecosystem's functions even under stress. The Cretaceous world had, after 160 million years of diversification, developed enormous ecological redundancy. The KPG extinction stripped most of that away, reducing ecosystems to bare minimum functionality, sustained by the generalist survivors discussed throughout this chapter. The early Paleogene ecosystem was, in the language of ecological theory, a simplified system running on reduced functional diversity. It worked, life continued, the planet did not sterilize itself permanently, but it worked clumsily, with far less of the elegant complexity and interconnection that characterizes mature, diverse ecosystems. The analogy that comes to mind is a city that has experienced a catastrophic disaster. The essential services, water, basic food supply, shelter are restored fairly quickly, but the full richness of urban life, the cultural and economic complexity that makes a city genuinely productive and interesting, takes much longer to rebuild, and the rebuilt city is never quite the same as the one that existed before. The process of rebuilding that ecological complexity took, as established, millions of years. And during those millions of years, the survivors, the small mammals, the birds, the crocodilians, the turtles, the insects, the ferns, the flowering plants regrown from their seed banks, were not simply waiting passively for conditions to improve. They were evolving, diverging, experimenting with new body forms and new ecological strategies, filling the empty ecological space of the post-Cretaceous world with increasing confidence and diversity. The Dark Age was ending, slowly and messily and without any particular fanfare. But what was coming next would more than make up for the low-key beginning. Evolution, it turns out, does not reward the impressive. It rewards whoever is still alive when conditions change. The freshwater ecosystems of the early Paleogene offer one more angle on this story that is worth examining, because they behaved quite differently from marine and terrestrial systems, and the reasons why tell you something important about the structure of ecological resilience. Rivers, lakes, and wetlands were, relative to the open ocean or tropical forests, considerably more buffered against the immediate effects of the impact winter. The reason is primarily thermal mass and physical structure. Large bodies of fresh water retain heat more efficiently than the surrounding land, and the sediments and organic matter of lake beds and river channels provide a physical substrate that persists, regardless of what is happening to the atmosphere above. Freshwater ecosystems also had a somewhat different food web structure than either terrestrial or marine systems, with a larger proportion of their energy flowing through detritivorous organisms that eat dead organic matter, rather than through photosynthesis-dependent chains. In a world where photosynthesis had been dramatically reduced, a food web with a large detritivore component had a built-in buffer that purely photosynthesis-dependent systems lacked. Dead leaves, woody debris and organic sediment continued to accumulate in freshwater systems, even when the plants producing them were dying en masse, providing an extended food subsidy that sustained bottom-level consumers through the worst years. This is probably why freshwater turtles, crocodilians, freshwater fish, and freshwater invertebrates showed higher survival rates across the KPG boundary than their terrestrial or marine counterparts. Not because rivers and lakes were pleasant places during an impact winter, they certainly were not, and many freshwater species did go extinct, but because the structural properties of freshwater ecosystems gave their inhabitants a slightly longer runway before starvation became the dominant selection pressure. A slightly longer runway, in a mass extinction event, can be the difference between a lineage that persists and one that does not. The geographical patterns of survival across the KPG boundary are also worth considering, because they were not uniform. Fossil evidence suggests that survival rates varied significantly between different regions of the planet, in ways that reflect the uneven distribution of the impact's immediate effects. The northern hemisphere, closer to the impact site and more severely affected by the initial thermal pulse and acid rain, shows generally lower survival rates than equivalent ecosystems in the southern hemisphere. High-latitude regions, paradoxically, may have had slightly higher survival rates than tropical ones for certain groups, partly because organisms adapted to seasonal cold were less vulnerable to the temperature crash than tropical specialists, and partly because high-latitude terrestrial ecosystems tended to have a higher proportion of dormancy-capable species plants that lost their leaves seasonally, animals that hibernated or entered torpor, seeds designed to survive winter cold. Southern Hemisphere records, particularly from New Zealand, Patagonia, and parts of Antarctica, show a somewhat different pattern than Northern Hemisphere sections, with evidence of a slightly less catastrophic initial collapse and possibly somewhat faster recovery in some groups. This is consistent with modelling studies showing that the sulfate aerosol veil, while global, was somewhat thicker and more persistent in the Northern Hemisphere where it was initially generated. The planet experienced the same extinction, but the intensity and pace of that extinction varied across its surface in ways that left different biological legacies in different regions, legacies that would eventually shape which lineages were present to diversify into the new Paleogene world. All of this geological and ecological detail serves a single, rather remarkable conclusion. The world that emerged from the KPG extinction was not a lesser version of the Cretaceous world, recovering towards some pre-existing template. It was something genuinely new, the specific configuration of survivors, small mammals with rapidly evolving body plans, birds exploring new ecological roles, insects rebuilding their partnerships with flowering plants, ferns and pioneer plant communities giving way to increasingly diverse forests set the stage for an entirely different biological story. One that would eventually, through a long and extraordinarily contingent series of events, produce every ecosystem currently functioning on this planet, including the one outside your window right now. The Dark Age was not a pause in the story of life. It was the transition between two fundamentally different versions of the world. And on the other side of that transition, something extraordinary was waiting. And whoever was still alive in the early Paleogene, blinking cautiously in the slowly returning sunlight, rooting around in the recovering fern fields for fungal threads and beetle larvae and newly germinating seeds, was the ancestor of every mammal, every bird, and every complex ecosystem on Earth today. Not a triumphant inheritance, not a glorious succession, just the quiet, stubborn, metabolically efficient persistence of the unremarkable, which, when you think about it, is probably the most honest description of life's long history on this planet that you will ever find. While everything discussed so far has focused primarily on what happened on land, there was an entirely separate catastrophe unfolding simultaneously beneath the surface of every ocean on the planet. The marine story of the KPG extinction is, in many ways, the less glamorous version of the same disaster. There are no iconic fossilized skeletons of sea creatures in natural history museums commanding the same kind of cultural attention as a Tyrannosaurus. No Hollywood blockbusters centered on the collapse of Cretaceous phytoplankton communities. And yet, what happened to the world's oceans between 66 million years ago and the eventual Paleogene recovery is arguably the more fundamental part of the story, because the oceans had been, since the very beginning of complex life on Earth, the primary engine of biological productivity on this planet. Understanding how they broke and how they eventually fixed themselves is essential to understanding how the modern world came to be. The ocean in the late Cretaceous was a genuinely extraordinary place, and it is worth spending a moment appreciating just how rich and complex it was before cataloguing its destruction, because the contrast is instructive. Surface waters across the tropics and mid-latitudes teemed with a staggering diversity of planktonic life. Coccolithophores building intricate calcium carbonate plates, foraminifera secreting delicate shells of remarkable geometric complexity, radiolarians constructing silica skeletons of such precision that they look, under a microscope, like something a very talented jeweler might produce on a very patient afternoon. These organisms were individually microscopic, but collectively they formed the photosynthetic and metabolic foundation upon which everything else in the ocean depended. Zooplankton fed on them. Small fish fed on the zooplankton. Large fish and marine reptiles fed on the small fish. The food web radiated upward from this planktonic base with the kind of elegant efficiency that only 400 million years of marine evolutionary refinement can produce. Then the sky went dark. The collapse of surface ocean productivity after the impact was, in its fundamental mechanism, essentially identical to what happened on land. Without sunlight, photosynthesis stopped, and without photosynthesis, the base of the food web vanished. But the marine version of this collapse had several features that made it, in some respects, even more complete and even harder to recover from than the terrestrial version. On land, seeds and dormant root systems could preserve the biological template of plant communities through the dark years, ready to regenerate when light returned. In the surface ocean, the equivalent organisms phytoplankton had no comparable dormancy mechanism for most species. They simply died when conditions became unfavorable, and their populations collapsed to near zero in many regions within weeks or months of the impact. The speed of this collapse is reflected with striking clarity in the geological record. Sediment cores drilled from ocean floors around the world show, directly above the KPG boundary layer, a dramatic shift in composition. Below the boundary, rich, diverse assemblages of calcareous plankton, the accumulated shells of foraminifera and coccolithophores that had been raining down onto the seafloor for millions of years at rates consistent with a productive, healthy surface ocean. Above the boundary, almost nothing. Sediment layers from the earliest Paleogene, in some locations, are so depleted in calcareous material that they were initially described by scientists as barren zone sections of ocean floor. where the normal rain of biological material from above had essentially ceased. This is not a gradual change. In the rock record, it happens in centimetres, representing, given normal marine sedimentation rates, perhaps a few thousand years of abrupt biological impoverishment. The acidification of the surface ocean compounded the productivity collapse in ways that specifically targeted the calcareous plankton that formed such a critical part of the Cretaceous marine ecosystem. As sulfur dioxide and carbon dioxide from the impact and from triggered volcanic activity dissolved into seawater, ocean pH dropped not uniformly or immediately across the entire ocean, but progressively and substantially over the months and years following the impact. The carbonate saturation state of surface waters fell below the threshold at which calcium carbonate shells can be maintained, meaning that even organisms that survived the initial productivity crash faced a secondary threat. Their shells simply began dissolving in the increasingly acidic water around them. The foraminifera record at the KPG boundary illustrates this with almost clinical precision. Pre-impact assemblages in ocean cores contain hundreds of species of varying morphology, size, and ecological specialization, evidence of a group that had been diversifying and filling ecological niches in the Cretaceous ocean for tens of millions of years. In the earliest Paleogene layers, the diversity collapses to a handful of tiny, simple species, often described by paleontologists as disaster fauna, the ecological equivalent of the fern spike on land. These survivors were small because small shells require less calcium carbonate to build and are less energetically costly to maintain under acidic conditions. They were simple in form because simpler shells are structurally more robust against dissolution. And they were generalist in their feeding habits because the highly specialized feeding strategies that had supported the diverse Cretaceous foraminiferal community could no longer be sustained in the impoverished post-impact ocean. The practical consequence of losing the foraminifera and the other calcareous plankton from the surface ocean was a cascade that affected every level of marine life that depended on them. Zooplankton that fed on phytoplankton had nothing to eat. The small fish and cephalopods that fed on zooplankton had nothing to eat. The larger predators that fed on those smaller organisms had nothing to eat. The collapse was not instantaneous at every level. Organisms higher in the food chain could persist for some time on declining populations of their prey, hunting through the ruins of a food web that was collapsing beneath them. But ultimately, the arithmetic was unforgiving. Without the base, the entire structure came down. The cephalopods deserve particular attention here, because their story at the KPG boundary is one of the most dramatic selective extinction events in the entire fossil record. Cephalopods, the group that today includes squid, octopuses, cuttlefish, and nautiluses, were, in the Cretaceous, represented by three major groups: the externally shelled ammonites, the internally shelled belemnites, and the ancestors of modern nautiluses and soft-bodied cephalopods. The KPG boundary killed the ammonites and the belemnites completely. Both groups, after hundreds of millions of years of evolutionary history, went extinct entirely and simultaneously. The nautiloids survived, as did the ancestors of the soft-bodied cephalopods. The pattern of which cephalopods survived and which did not is informative. The ammonites and belemnites were both highly dependent on the productive surface and mid-water zones of the ocean, where the food web collapse was most severe. The nautiloids, by contrast, were already living somewhat deeper and were known to be metabolically flexible, capable of descending to depths where conditions were less immediately catastrophic. The soft-bodied cephalopods, ancestral squids, and octopuses similarly had the flexibility to exploit a wider range of depths and dietary sources. The deep sea, in the immediate aftermath of the KPG impact, was simultaneously the ocean's best refuge and its most important biological bank account. This requires a little explanation, because the deep sea in the modern ocean is often portrayed as a strange, cold, barren place, inhabited by bizarre creatures adapted to crushing pressure and perpetual darkness. And while that description contains some truth, it misses something important about the deep sea's relationship to the rest of the ocean. The deep ocean is connected to the surface through a constant slow rain of organic particles, dead phytoplankton cells, fecal pellets from zooplankton, fragments of dead animals from upper layers that paleoceanographers poetically call marine snow. This material drifts downward continuously, carrying energy from the productive surface layers to the deep seafloor communities that depend on it. In the Cretaceous, this organic rain had been rich and continuous, supporting diverse deep-sea communities of bacteria, fungi, invertebrates, and fish that were accustomed to receiving a reliable supply of organic material from above. When the surface productivity collapsed after the impact, that supply did not stop immediately. The organic material already in transit, the bodies of the phytoplankton and zooplankton killed by the productivity crash, continued sinking to the deep floor for some time, providing a temporary subsidy to deep communities even after the source had been cut off. For a brief period, the deep sea was paradoxically better fed than it had been before the impact, as enormous quantities of dead biological material rained down from above. This was not exactly good news in the bigger picture, but it did give deep-sea communities a buffer that surface communities lacked entirely. The organisms living in the very deepest parts of the ocean, communities clustered around hydrothermal vents on the seafloor, sustained by chemosynthesis rather than photosynthesis, entirely independent of sunlight, were largely unaffected by the surface catastrophe. These vent communities, built around bacteria and archaea that derive their energy from the chemical reactions between hydrothermal fluids and seawater, existed in a biological world utterly disconnected from the surface. The darkness, the cold, the absence of photosynthesis, these were, from the perspective of a hydrothermal vent community, simply normal Tuesday conditions. They had been functioning in permanent darkness for as long as the vents had existed. The Chicxulub impact was a catastrophe for the surface world. For the vent communities, it was barely worth noticing. The significance of these deep refugia, both the hydrothermal vent communities and the deeper water communities sustained by falling organic material, lay not in their immediate ecological importance, but in their role as biological reservoirs. They preserved lineages, genetic diversity, and ecological templates that would eventually contribute to the rebuilding of marine ecosystems as surface conditions slowly improved. The recovery of the surface ocean did not happen purely by evolution producing new forms from scratch. It happened partly because deep water populations of surviving species repopulated the surface as conditions became hospitable again, a process of upward ecological succession, the inverse of the marine snow that had helped sustain the deep during the dark years. The timescale of ocean recovery is worth examining in some detail, because it differed significantly from the recovery of terrestrial ecosystems. On land, as described earlier, the fern spike and seed bank recovery began showing results within decades to centuries of the impact, and a recognizable if simplified forest ecosystem had returned in many regions within a few 100,000 years. In the oceans, recovery was considerably slower, and the reasons for this difference illuminate something important about how marine ecosystems are structured. Marine food webs are built on biological time delays. Phytoplankton, at the base, can reproduce within hours to days under optimal conditions. Their potential recovery rate is actually extremely fast. But the organisms that feed on phytoplankton, zooplankton, filter feeders, small fish, have generation times measured in weeks to months, and the organisms that feed on those have generation times measured in years. And the apex predators at the top of the food web may reproduce only once every few years and take years to reach sexual maturity. Rebuilding a complex marine food web requires not just the recovery of the base, but the sequential rebuilding of every level above it, each level waiting on the level below it to achieve sufficient density before the next level can recover. This sequential dependency means that marine ecosystem recovery is inherently slower than the recovery rate of any individual species within it would suggest. Paleoceanographic data shows that different components of the marine ecosystem recovered at dramatically different rates after the KPG impact. Bacterial communities at the seafloor recovered relatively quickly. Bacteria have short generation times and high metabolic flexibility, and they were among the first organisms to take advantage of the enormous pulse of organic material deposited on the seafloor during and after the surface collapse. Phytoplankton diversity began showing signs of recovery within tens of thousands of years, though full pre-impact diversity was not restored for millions of years. Zooplankton diversity tracked phytoplankton recovery with a lag of thousands to tens of thousands of years. The recovery of larger, slower reproducing marine animals, fish, marine mammals in the early Paleogene, the various invertebrate groups that would eventually diversify into modern coral reef communities, took millions of years, with different groups reaching full ecological recovery at different times and in different regions. The coral reef ecosystem specifically took an extraordinarily long time to recover after the KPG event. Cretaceous reef systems, dominated by a now extinct group called rudis bivalves, rather than corals as we know them today, were completely destroyed. Modern coral reefs, built by scleractinian corals that had survived the KPG boundary in reduced numbers, did not return to anything resembling their current ecological complexity until roughly 10 million years into the Paleogene, and some researchers argue that truly modern reef ecosystems, with their extraordinary diversity of fish and invertebrate species, did not fully establish until considerably later. The reason is the same sequential dependency mentioned above, combined with the particular ecological requirements of coral growth. Corals need warm, clear, relatively shallow, nutrient-poor water, and they need the associated communities of fish, invertebrates, and algae that maintain reef health and structure. Assembling all of those components simultaneously, in the right place and at the right densities, turns out to require a very long time indeed. The recovery of the world ocean also showed strong geographic variation, with different ocean basins showing different rates and pathways of biological rebuilding. The tropical Pacific and Atlantic basins, where surface temperatures recovered relatively quickly as the atmospheric aerosol veil thinned, showed some of the earliest signs of returning phytoplankton productivity. High-latitude oceans, which had experienced less severe initial warming, but were closer to the margins of habitability for tropical plankton communities, showed slower and more patchy recoveries. The recovery of deep water circulation patterns, the global thermohaline circulation that moves cold, oxygenated water from polar regions to the deep sea, and drives large-scale nutrient mixing was also disrupted by the temperature crash and took substantial time to re-establish, affecting the delivery of nutrients to surface waters in ways that further complicated phytoplankton recovery in some regions. One aspect of the post-impact ocean that is both scientifically fascinating and genuinely strange to contemplate is what happened to ocean chemistry during the dark years, independent of the acidification. A productive ocean is in a state of constant chemical activity. Phytoplankton absorb carbon dioxide and nutrients during photosynthesis. Zooplankton recycle nutrients through their feeding and excretion. Bacterial communities process organic matter, and the whole system maintains a set of chemical balances that have been refined by hundreds of millions of years of biological activity. When phytoplankton productivity collapses, all of these chemical cycles are disrupted simultaneously. Carbon dioxide is no longer being absorbed by photosynthesis at the surface. Nutrients accumulate in surface waters that nothing is available to consume them. Oxygen levels in deeper water drop as bacterial decomposition of the organic material raining from the dying surface ocean consumes available oxygen. These chemical changes were not merely academic. They fed back into the biology of recovery in complex ways. High nutrient concentrations in post-impact surface waters created conditions that initially favored certain kinds of rapidly reproducing, opportunistic phytoplankton species that could bloom explosively in nutrient-rich conditions, but did not contribute much to rebuilding the ecological complexity of a fully functioning marine food web. The early stages of ocean recovery were, in this sense, somewhat analogous to the fern spike on land, dominated by fast-reproducing generalists that could exploit available resources quickly, rather than by the diverse specialists that would eventually replace them. It took the better part of several million years for the global ocean to return to something resembling the complex, stratified, species-rich ecosystem of the late Cretaceous, and even then, what it returned to was not the Cretaceous ocean restored. The ammonites did not come back. The mosasaurs did not come back. The rudest reef systems did not come back. What emerged was a new configuration of marine life, built from the survivors and their descendants, filling the ecological roles vacated by the extinction with new bodies, new strategies, and new evolutionary lineages that the Cretaceous ocean had never contained. The bony fish, which had been present in the Cretaceous but had not yet achieved their modern ecological dominance, expanded dramatically into the niches left vacant by the extinction of large marine reptiles. The marine mammals that would eventually evolve from terrestrial mammal ancestors, the ancestors of whales, dolphins, and seals, had not yet appeared in the early Paleogene, but the ecological stage for their eventual entry was being cleared as the old Cretaceous caste departed. What the ocean story adds to our understanding of the KPG aftermath is a sense of depth, literally and figuratively. The catastrophe was not a surface event that spared the deep world, but a global restructuring that reached to the very bottom of the ocean disrupting even the chemical systems that had been running since long before complex life evolved. And the recovery was not a restoration, but a rebuilding slow, sequential, geographically uneven, and ultimately resulting in a world that was different in almost every detail from the one that had existed on the other side of that thin iridium layer. The darkness that descended on the surface ocean in those first terrible years after the impact was eventually replaced by light and life and extraordinary biological complexity. But it took considerably longer than the ferns. To fully appreciate the marine recovery, it helps to understand something about how the ocean actually works as a biological system, because the ocean is not simply a giant tank of water containing fish. It is a three-dimensional, chemically active, physically dynamic environment in which biological processes at the microscopic scale drive conditions at the planetary scale. The phytoplankton that form the base of the marine food web are not merely passive players waiting to be eaten. They actively shape the chemistry of the water and atmosphere around them. They absorb carbon dioxide. They produce oxygen. They influence cloud formation through the chemical compounds they release. They control the distribution of nutrients through their uptake and eventual sinking. In a healthy ocean, the relationship between biology and chemistry is so tightly coupled that it is genuinely difficult to say where one ends and the other begins. When the phytoplankton crash happened at the KPG boundary, the ocean did not simply lose a food source, it lost a chemistry engine. The carbon cycle, which had been running through the combined activities of marine photosynthesis and deep water decomposition for hundreds of millions of years, was thrown into disarray. Carbon dioxide that would normally have been absorbed by phytoplankton accumulated in the atmosphere and dissolved into surface waters. The biological pump, the process by which photosynthetically fixed carbon is transported from the surface to the deep ocean in the form of organic particles, effectively stopped working. The ocean and atmosphere exchanged gases in different proportions than they had before, and the global carbon cycle lurched into a new, unstable configuration that took millions of years to settle back toward equilibrium. The isotopic record in ocean sediments captures this disruption with extraordinary clarity. Carbon isotopes in marine sediments record the relative activity of biological productivity. Heavy carbon-12 and lighter, carbon-13 are incorporated into organic matter and carbonate shells in ratios that reflect how much biological processing is occurring. In the rock layers immediately above the KPG boundary, there is a pronounced negative shift in carbon isotopes, what geologists call the Strangelove ocean signal, named after a slightly morbid reference to the idea of an ocean where biology has essentially stopped. The signal is visible in sediment cores from ocean basins worldwide, confirming that the biological collapse was indeed global and approximately simultaneous. The ocean, for a brief geological moment, was running almost entirely on chemistry rather than biology, and chemistry without biology, in an ocean context, is a considerably less productive and considerably less interesting place. The organisms that survived through this chemical disruption had one thing in common, beyond the size and metabolic flexibility that characterized terrestrial survivors. They were organisms whose fundamental life processes were either independent of, or highly tolerant of, the altered chemistry of the post-impact ocean. The bacteria and archaea of the deep sea, which had been running their metabolic processes through pathways that predated photosynthesis by billions of years, were simply running the same programs they always had, in conditions that were, for them, essentially normal. The deep-sea invertebrates that fed on bacterial films and sediment organic matter continued their business. Even the deep-water fish, which were ultimately dependent on the rain of organic material from above, had enough of a food subsidy from the collapse of the surface ecosystem to persist through the worst years. Among the organisms of the shallow and mid-water zones, some genuinely surprising survivors emerged. The bony fish, which in the Cretaceous had been ecologically overshadowed by the large marine reptiles, and the enormous diversity of ammonites and other cephalopods, turned out to be remarkably resilient. Modern teleost fish, the group that today constitutes roughly 99% of all living fish species, were present in the Cretaceous, but had not yet achieved their current ecological dominance. They survived the KPG boundary in significant numbers, probably because of several characteristics that now appear, in retrospect, like fairly good evolutionary investments. High reproductive rates producing large numbers of offspring, relatively small adult body sizes in many lineages, flexible diets spanning multiple trophic levels, and the ability to occupy a very wide range of marine environments, from shallow coastal waters to open ocean. The early Paleogene ocean, with its simplified food web and reduced competition from the large reptilian predators that had died out, represented an enormous ecological opportunity for the surviving fish. The diversification of bony fish in the Paleogene and Eocene is one of the most rapid and extensive evolutionary radiations in the history of vertebrates. Over the first 20 million years of the Anazoic, the basic ecological roles of the modern ocean fish community were established, with lineages diversifying into herbivores, planktivores, mid-water predators, deep-sea specialists, reef dwellers, and open ocean apex predators at a pace that reflects both the available ecological space and the significant productive opportunity represented by a recovering but still relatively uncrowded ocean. Not exactly a competitive market, which historically tends to produce rapid innovation. The sharks, as mentioned in an earlier chapter, had survived the KPG boundary, and in the early Paleogene they found themselves in an ocean where their primary competition for large prey, the mosasaurs, the plesiosaurs, the large marine crocodilians, had been removed. Shark diversity expanded moderately in the early Cenozoic, and several lineages moved into ecological roles that had been vacated by the extinct reptiles. The sharks that would eventually culminate in the largest predatory fish in Earth's history, a creature called Otodus megalodon, which we will return to in a subsequent chapter, were already beginning their evolutionary trajectory in the warm, resource-rich oceans of the early Paleogene. They had the time and the ecological space to get very large indeed, which they eventually did with considerable enthusiasm. The recovery of marine invertebrate communities followed a pattern that reflected both ecological succession and the sequential rebuilding of habitat structure. Many of the key invertebrate groups that form the ecological framework of modern shallow water marine environments — corals, sea urchins, bivalves, gastropods, crustaceans — survived the KPG boundary in reduced numbers and diversity, and then diversified through the Paleogene as conditions improved. But the pace of their diversification was constrained by the pace of physical habitat recovery, which was in turn constrained by the pace of water chemistry stabilization. Corals, for instance, cannot build reefs in acidic, nutrient-poor water with unstable temperature and chemistry. The coral reef ecosystems that had existed in the Cretaceous, built by the now extinct Rudis bivalves, were gone, and the scleractinian corals that would eventually build modern reefs needed a long period of recovery before the chemical and physical conditions necessary for reef construction were consistently available. The story of sea urchins in the post-KPG recovery is a relatively obscure but genuinely informative case study in ecological resilience. Irregular sea urchins, the group that includes the sand dollars, and heart urchins that burrow through seafloor sediments, diversified explosively in the Paleogene, becoming one of the dominant groups in shallow marine sedimentary environments. Regular sea urchins, which graze on algae and invertebrates on rocky substrates, also diversified significantly, though their recovery was somewhat slower because it depended on the recovery of the hard-bottom algal communities they fed on. The urchins illustrate a broader pattern: groups that were ecologically positioned near the surviving base of the food web. In this case, deposit-feeding animals that ate sediment, organic matter, and bacteria recovered faster and diversified more rapidly than groups that depended on ecological structures further up the chain that themselves needed to be rebuilt first. One of the genuinely remarkable stories of post-KPG marine recovery is what happened to the coccolithophores, the tiny calcareous algae that had formed such a crucial component of Cretaceous plankton communities. These organisms were devastated by the combination of productivity collapse and ocean acidification, and their diversity at the KPG boundary dropped dramatically. But within a few 100,000 years, coccolithophore diversity had begun recovering, and within a few million years they had diversified into new species that had not existed before the extinction. The genetic analysis of modern coccolithophores shows signatures consistent with a severe population bottleneck followed by rapid diversification, the molecular equivalent of a narrow, strangled lineage suddenly expanding into open water. The species that emerged from the Paleogene recovery were not the same as those lost at the boundary, but they occupied the same ecological roles, performing the same photosynthetic and carbonate cycling functions that their predecessors had. Ecology, it turns out, has a kind of gravitational pull toward particular configurations of function and form, even when the specific species performing those functions have been completely replaced. The nitrogen cycle in the post-impact ocean is another aspect of chemical disruption that rarely makes it into popular accounts, but was ecologically significant. Fixed nitrogen in forms that biological organisms can actually use is a limiting nutrient in much of the ocean, meaning that the productivity of many marine ecosystems is constrained by how much available nitrogen is present. Nitrogen fixation in the ocean is carried out primarily by certain specialized bacteria and cyanobacteria, and the recovery of nitrogen-fixing communities after the KPG disruption was critical to the eventual recovery of broader phytoplankton productivity. In the immediate post-impact period, nitrogen cycling in the surface ocean was disrupted both by the death of the nitrogen-fixing organisms themselves and by the altered physical conditions, temperature, chemistry, light availability that controlled where and how quickly those organisms could recover. The gradual rebuilding of the nitrogen cycle in the early Paleogene ocean was a quiet, invisible process that had enormous downstream consequences for everything that ate phytoplankton. The physical structure of the ocean, its temperature, its layering, its circulation patterns, was also significantly altered by the impact and took time to return to something stable. The thermohaline circulation, the global system of deep water formation driven by the sinking of cold, dense polar water and its replacement by warmer surface water flowing from the tropics, is the ocean's primary mechanism for distributing heat, oxygen, and nutrients globally. Disruptions to surface temperature patterns during the impact winter, including the rapid temperature crash and the complex uneven pattern of warming and cooling, as the aerosol veil thinned, affected the density contrasts that drive thermohaline circulation. Evidence from sediment cores suggests that deep water circulation patterns were perturbed for an extended period after the KPG boundary, with implications for oxygen delivery to deep-sea communities and nutrient supply to surface waters in high-productivity upwelling zones. Gradually, over millions of years, the physical and chemical ocean stabilized. Surface temperatures in the early Paleogene were warm, considerably warmer than today, and the return of abundant sunlight and the recovery of phytoplankton communities drove a resumption of active biological cycling that began to repair the chemical disruptions of the dark years. Carbon isotopes in marine sediments shifted back toward positive values as biological productivity recovered, and the biological pump began moving organic carbon back to the deep ocean at rates approaching pre-impact levels. The Strangelove ocean signal faded in the sediment record, replaced by isotope ratios consistent with a returning biological activity. By the time the Paleocene epoch merged into the Eocene, roughly 56 million years ago, the world ocean had been thoroughly rebuilt. Not restored, rebuilt. The species were different, the specific ecological configurations were different, the detailed chemistry of different ocean basins had been modified by millions of years of altered circulation and biology. But the fundamental architecture of a productive, stratified, biologically diverse ocean ecosystem was back, running on the energy of sunlight filtered through billions of individual phytoplankton cells, cycling nutrients through food webs of astonishing complexity, and driving the global carbon cycle with an efficiency that had been reborn from a near-total collapse. The ocean had survived its own dark age, and what it had built on the other side of that survival was the foundation for every marine ecosystem that exists today. The ocean's recovery story is, in the end, a story about patience. Not the patience of individual organisms, they do not have the luxury of taking a long view, but the patience of biological processes operating at timescales that dwarf anything in human experience. The ocean took millions of years to fix itself, not because it was inefficient or poorly designed, but because the scale of the disruption was so vast that even the extraordinary reproductive capacity of microorganisms could not instantly overcome it. Rebuilding complexity requires time, and the ocean took exactly as long as it needed, not a moment more or less, and produced a world of oceanic life that is still, in many of its fundamental features, the world we live with today. The ocean had rebuilt itself. The land had greened again. The small, cautious, metabolically thrifty survivors of the dark years had been diversifying for millions of years, cautiously expanding into the enormous ecological space left behind by the extinction. And then, just as things were beginning to settle into something resembling a new normal, the planet decided to turn up the heat considerably. The Paleocene epoch, which began at the KPG boundary and lasted until roughly 56 million years ago, was in many ways a transitional period, a slow rebuilding, a gradual filling of ecological vacancies, a world that was warmer than today but still recognizable in broad outline. Temperatures were elevated compared to the modern baseline. There was no permanent ice at either pole, and tropical forests were more widespread than they are now. But the Paleocene was not yet the world of extremes that was coming. It was, relatively speaking, a gentle warm-up. The main event was still ahead. What happened 56 million years ago is one of the most studied and debated climate events in all of Earth's geological history, and with good reason. It was one of the fastest and most dramatic episodes of global warming in the rock record. It happened for reasons that are still not entirely agreed upon, and its consequences for life on Earth were profound, strange, and in several cases genuinely difficult to explain. Scientists call it the Paleocene-Eocene thermal maximum, which they abbreviate to PETM because life is short and the name is long. The event marks the boundary between the Paleocene and Eocene epochs, and it represents roughly 200,000 years during which the planet's average surface temperature increased by somewhere between 5 and 8 degrees Celsius, above what were already elevated baseline temperatures. To put that in perspective, modern climate scientists are deeply concerned about a global temperature increase of 1.5 to 2 degrees Celsius over the next century. The PETM delivered 3 to 4 times that increase, at a pace that was geologically rapid thousands of years rather than millions, and on top of a baseline that was already substantially warmer than today. The deep ocean, which normally maintains temperatures close to freezing, warmed by roughly 5 degrees during the PETM. The Arctic Ocean, according to fossil evidence from that period, reached temperatures comparable to a warm subtropical sea. Forests not sparse woodlands, but dense, species-rich tropical and subtropical forests extended to within relatively short distances of both poles. The planet, in short, was doing something that modern humans have not experienced and would find quite challenging to visit. The cause of the PETM is still a subject of active scientific debate, which is slightly embarrassing given how thoroughly studied the event is. The rock record shows a dramatic negative shift in carbon isotopes at the PETM boundary, the same kind of signal that indicates a rapid injection of large quantities of carbon dioxide or methane into the atmosphere, but from a source that was isotopically light, suggesting an organic or volcanic origin rather than marine carbonate dissolution. Several hypotheses have been proposed over the decades. Massive volcanic outgassing from the North Atlantic igneous province, which was actively forming as the North Atlantic Ocean spread apart at this time. The catastrophic release of methane hydrates from seafloor sediments, triggered by initial ocean warming, a comet impact delivering carbon-rich material, or some combination of these factors creating a cascading feedback loop. The honest answer, at the current state of scientific understanding, is probably some combination of volcanic forcing and methane hydrate destabilization reinforcing each other, but the relative contributions remain contested. What is not contested is that enormous quantities of carbon entered the atmosphere rapidly, the planet warmed substantially, and the consequences were far-reaching. Among the most visible and consistently remarked upon consequences of the PETM warming was the response of animal body sizes which went, counterintuitively, in the wrong direction. Biologists have long recognized a general principle called Bergmann's rule, which describes the tendency for animals within a given taxonomic group to be larger in cooler climates and smaller in warmer ones. The physiological logic is reasonably intuitive. Larger bodies have a lower surface area to volume ratio, which helps retain heat in cold environments. Smaller bodies have a higher ratio, which helps dissipate heat in warm ones. During the PETM, fossil evidence from multiple mammal lineages in North America and Europe shows a clear and consistent pattern of body size reduction, sometimes dramatic reduction, with some species shrinking by 30% or more relative to their pre-PETM ancestors. This dwarfing was not random. It was a directed evolutionary response to sustained warmth, and it happened relatively quickly by evolutionary standards over tens of thousands of years rather than millions. The most famous exemplar of this PETM dwarfing is the early horse lineage. The ancestors of modern horses were, in the Paleocene and early Eocene, very small animals roughly the size of a small dog, not the impressive creatures we associate with the word horse today. During the PETM, fossil evidence shows that these early equids became even smaller, reaching sizes comparable to a large house cat. After the PETM ended and temperatures gradually declined, body sizes in the lineage rebounded. The pattern is clear enough in the fossil record to use as a proxy for temperature. Paleontologists can, in principle, estimate ancient temperatures by measuring how small the horses got, which is a research methodology that sounds considerably stranger than it is, but it works. The PETM dwarfing event is interesting not just as a historical curiosity, but as a demonstration of how rapidly natural selection can produce measurable changes in body size when selection pressure is sufficiently strong and sustained. 30% body size reduction in tens of thousands of years is fast by evolutionary standards. It required no mutation to a novel genetic pathway, no dramatic anatomical innovation, just the sustained differential survival of smaller individuals in a population, generation after generation, in conditions where smaller body size conferred a meaningful fitness advantage. It is, in a sense, evolution being entirely predictable and mechanical, doing exactly what the physical laws of biology and thermodynamics would expect it to do. While some animals were getting smaller during the PETM, others were doing the opposite, and the particular organism that represents the opposite end of this spectrum is one of the most impressively impractical animals in the entire history of vertebrate life. Titanoboa ceruginoensis, and the full name does deserve its moment, even if only to appreciate how well it suits the animal, was a snake, an enormous snake. A snake so enormous that when its fossils were first properly described in 2009, some of the paleontologists involved reportedly had difficulty convincing themselves that the bones they were looking at were actually from a snake, rather than from some other kind of large vertebrate, because nothing in their experience had prepared them for a snake on quite this scale. Titanoboa lived during the Paleocene epoch, shortly after the KPG extinction, in what is now the Cerrejón coal mine in northern Colombia, a region that 58 to 60 million years ago was a vast tropical rainforest sitting very close to the equator. The fossils were found embedded in coal seams, which is what tropical peat deposits become over millions of years, and they painted a picture of an animal that would strain the imagination even as fiction. Length estimates based on vertebral dimensions place Titanoboa at somewhere between 12 and 15 metres, from nose to tail comparable to a large school bus, for those who like their ancient animals measured in familiar units. Weight estimates exceed 1,000 kilograms, with some calculations suggesting individuals may have exceeded 1,300 kilograms. The head alone was large enough to comfortably swallow a crocodilian of respectable size, which was, based on the associated fauna from the Cerrejón Formation, probably a not uncommon menu choice. To understand why Titanoboa could exist at this particular time and place, and nowhere else in Earth's history, you need to understand the relationship between snake body size and ambient temperature, which is a relationship that is both physiologically real and genuinely constraining. Snakes are ectotherms. They regulate their body temperature through external heat sources rather than through internal metabolic heat production. This means that a snake's body temperature, and therefore its metabolic rate, digestive capacity, and overall physiological function, is directly tied to the temperature of its environment. In cool environments, large snakes are at a disadvantage. Their metabolic rate is too depressed to digest food efficiently, their muscles are too cold to function at full capacity, and the energetic costs of maintaining a large body mass in a thermally unreliable environment are prohibitive. There is in effect a maximum body size for snakes that scales with the temperature of the environment they live in. The Paleocene tropics, with their extraordinary warmth, mean annual temperatures at the equator that have been estimated at roughly 30 to 34 degrees Celsius, based on fossil plant communities, were the only environment in Earth's history warm enough to support a snake the size of Titanoboa. The math actually works out. Researchers have used the relationship between modern snake body size and habitat temperature to back calculate what temperature would be required to support a snake of Titanoboa's dimensions, and the answer is consistent with the independent temperature estimates from the Cerrejón plant fossils. Titanoboa is not just an impressive animal, it is a living thermometer, a biological record of just how warm the Paleocene tropics actually were, preserved in vertebral dimensions that can be measured with a ruler. The world that Titanoboa inhabited was, in almost every sense, a world that modern humans would find deeply disorienting to visit, assuming they survived the encounter with the local wildlife long enough to form an impression. The forests of the early Eocene tropics were dense, humid, and extraordinarily species-rich in fact. Some paleobotanists argue that the early Eocene tropical rainforests were more diverse in certain plant groups than modern Amazon or Congo Basin forests, having had millions of years of warm, stable conditions to accumulate species without the kind of glacial cycle disruptions that repeatedly fragmented and contracted tropical forests in the more recent past. These forests were populated by large, unfamiliar mammals filling ecological roles that had been vacant since the dinosaurs departed, early relatives of ungulates, browsing on low vegetation, early primates in the forest canopy, large flightless birds on the forest floor, and reptiles of various sizes occupying the full range of ecological opportunities that an environment with reliably high ambient temperatures made available. The geographic extent of tropical and subtropical forests during the early Eocene climatic optimum, the warmest period of the Cenozoic, which peaked around 50 to 52 million years ago, was dramatically greater than anything seen in the modern world. Fossil evidence of subtropical and warm temperate vegetation has been found in geological deposits from locations that today lie within the Arctic and Antarctic circles. Fossil palms have been found in Alaska. Fossil breadfruit relatives have been found in the high Arctic of Canada. Fossil crocodilians, animals that require warm temperatures year-round to function, have been found in what are now subarctic latitudes. The polar regions in the early Eocene were not frozen wastelands covered in ice sheets. They were forested, relatively mild environments that would have looked, to modern eyes, something like a warm temperate or even subtropical woodland. There was no permanent ice at either pole. The concept of a polar ice cap would have been, from the perspective of an Eocene organism, as foreign as the concept of a traffic jam would be to a dinosaur. This pole-to-pole distribution of warm forests had profound consequences for the evolution and dispersal of animals. In a world where tropical and subtropical conditions extended all the way to high latitudes, land animals did not face the same latitudinal barriers to dispersal that they do today. An early mammal living in what is now Wyoming could, in principle, disperse northward into what is now Alaska, and continue into what are now the high Arctic islands, and the climate would remain hospitable throughout the journey. Similarly, dispersal between continents via high-latitude land connections like the Thule land bridge between Europe and North America that existed in the early Eocene was facilitated by the warm climate, which turned what would today be a journey through Arctic tundra into a pleasant stroll through warm forest. The biogeographic patterns of early Cenozoic mammals, with their surprising similarities between North American and European faunas, reflect this warm facilitated dispersal with considerable clarity. The mammals of the Eocene were, even by the standards of a group that had been diversifying rapidly since the KPG extinction, impressively diverse, and in several cases impressively large. The old constraint of Mesozoic smallness had been thoroughly overcome by the Eocene mammals, had been steadily growing larger since the KPG boundary, filling ecological roles at progressively larger body sizes as ecosystems recovered and food availability improved. By the Eocene, the largest land mammals were reaching sizes that would have been completely unrecognizable to a Cretaceous observer accustomed to the furtive mouse-sized creatures that had scurried beneath the dinosaurs' feet. Pachycetus and its relatives, the early ancestors of modern whales, were land-dwelling or amphibious mammals in the early Eocene, living in and around the shallow coastal waters of the Tethys Sea in what is now Pakistan and India. They looked nothing like whales. They were four-legged, roughly dog-to-sheep-sized animals that probably lived much like modern otters or capybaras, spending time both in water and on land. But the transition that would produce the enormous, fully aquatic whales of the modern ocean was already beginning in the Eocene, driven by the rich marine resources available in the warm, productive Tethys Sea. The evolution of whales from terrestrial mammals is one of the most well-documented major evolutionary transitions in the vertebrate fossil record, and it happened with remarkable speed within roughly 15 million years of the first fully terrestrial whale ancestors. The lineage had produced organisms that were entirely aquatic, had lost their hind limbs, had evolved the remarkable anatomical specializations for diving and long-distance swimming, and had grown to sizes that rivaled some of the larger marine reptiles of the Mesozoic. The warm, food-rich Eocene ocean, recovering robustly from the KPG collapse, provided both the incentive and the resources for this extraordinary transformation. The early Eocene also saw the diversification of the first large, truly impressive land predators of the Cenozoic. The creodonts, an extinct group of carnivorous mammals that were not closely related to any modern carnivore order, but occupied the ecological roles that wolves, hyenas, and large cats fill today, reached substantial sizes in the Eocene, with the largest forms being genuinely formidable predators by any reasonable standard. The mesonychids, another group of large carnivorous mammals, similarly occupied apex predator roles in Eocene ecosystems, stalking the large herbivores that were themselves becoming increasingly substantial. The ecological architecture of Eocene land ecosystems was, by this point, beginning to look at least vaguely recognizable. There were large herbivores eating plants, medium-sized browsers eating leaves and fruit, large predators eating the herbivores, and scavengers cleaning up what the predators left behind. The specific animals filling these roles would be unrecognizable to a modern observer, but the ecological logic was familiar. The oceans of the Eocene, meanwhile, were experiencing their own period of remarkable biological richness. The warm, extensive Tethys Sea, a vast east-west seaway that connected what are now the Mediterranean, the Middle East, and South Asia, before later tectonic movements closed, it was one of the most biologically productive marine environments in the Cenozoic, hosting extraordinary diversity of fish, cephalopods, marine reptiles in the form of early sea turtles and crocodilians, and an increasing diversity of early whales and other marine mammals. Coral reef systems were returning to something approaching their modern complexity, building extensive reef structures in the warm, shallow Tethys and its adjacent basins. The foraminifera and coccolithophores, whose near-complete collapse at the KPG boundary had been one of the defining features of the immediate post-impact ocean, were back not in the same species as before, but in new forms, filling the same ecological roles with different specific bodies. One of the more striking features of the Eocene world, looking at it from the perspective of modern biogeography, is how different the continental positions were and how those positions shaped the distribution of life. India was still a large island, having broken away from the supercontinent of Gondwana millions of years earlier, and was sailing northward toward its eventual collision with Asia at a pace that seems leisurely by human standards, but was actually quite rapid by geological ones. Australia, similarly, had separated from Antarctica and was beginning its long northward journey toward its current position. South America was still isolated, connected to neither North America to the north nor Antarctica to the south, in the state of continental isolation that would allow it to evolve its extraordinary endemic fauna over the coming tens of millions of years. Antarctica, which we now associate entirely with ice and penguins, still had forests. The arrangement of the continents in the Eocene would look, on a map, deeply unfamiliar to a modern viewer enough that students encountering early Cenozoic paleogeography for the first time often need several minutes to work out what they are looking at. The cooling that eventually ended the Eocene climatic optimum and brought the warm world of the early Cenozoic to a close was gradual by human standards, but relatively rapid by geological ones. Multiple factors contributed to the long-term cooling trend that began in the Middle Eocene, and would eventually, tens of millions of years later, produce the ice ages of the Pleistocene, the opening of the Drake Passage between South America and Antarctica as those continents separated, which established the Antarctic circumpolar current and thermally isolated Antarctica. The ongoing closure of the Tethys Sea as Africa and India pushed northward into Eurasia, reducing the exchange of warm tropical water between the Indian and Atlantic Oceans, declining volcanic outgassing rates reducing atmospheric carbon dioxide, and increasing weathering of freshly uplifted mountain ranges drawing down carbon dioxide through chemical reactions between silicate rocks and rainwater. The transition from the warm Eocene world to the cooler Oligocene was one of the most significant climate shifts of the Cenozoic, and it left its mark on the distribution of life in ways that are still visible in modern biogeography. Tropical forests retreated from high latitudes as temperatures fell. Antarctica began to accumulate ice at first seasonally, then permanently, in a process that would eventually produce the continental ice sheet we know today. Sea levels, influenced by the growing Antarctic ice, fell. Shallow coastal marine environments shrank. The warm-adapted animals of the high-latitude Eocene forests, the palms, the crocodilians, the diverse subtropical mammal communities either retreated toward the equator, adapted to cooler conditions, or went extinct. The world was becoming, very gradually, more like the world we live in today, and it was doing so by cooling, not by warming. The extraordinary warm world of the Eocene was ending, and what it left behind, the evolved, diversified, ecologically complex communities that had developed in its warmth, would carry forward into the cooler, more variable world of the Oligocene and Miocene, adapting and diversifying as conditions changed, laying the biological groundwork for everything that came after. The Eocene, in this context, is worth understanding not just as a warm period, but as a biological forcing function, a sustained period of extraordinary warmth and stability that allowed life to diversify into ecological configurations of remarkable complexity, produced animals of remarkable sizes, and pushed the boundaries of what was biologically possible in ways that have not been repeated since. But before we leave the Eocene entirely, it is worth examining a few of its more remarkable biological stories in greater detail, because the diversity of life in this period was not just a matter of scale. It was a matter of genuine evolutionary novelty organisms finding ways of living that had never existed before and have not existed since. The early primate radiation of the Eocene is a case in point. Primates, the group that today includes lemurs, monkeys, apes and humans, had their origins in the Paleocene. But the Eocene was the period of their first major diversification. Early Eocene primates were small, tree-dwelling animals, probably similar in general appearance and lifestyle to modern tarsiers or small lemurs, though not closely related to either. They were exploiting the extraordinarily rich warm forests of the early Eocene, where fruit and insects were available year-round, and where the stable, warm conditions allowed the development of forest canopy structures of enormous complexity. The diversity of early Eocene primates, documented from fossil assemblages in North America, Europe, Asia and Africa, suggests a group in the early stages of an explosive adaptive radiation, exploring different dietary strategies, different body sizes, different patterns of locomotion and social organization. The reason primates matter in this context is not because they were ecologically dominant in the Eocene, they were not, being small and relatively common rather than ecologically pivotal in the way that large herbivores or apex predators are. They matter because their diversification in the warm forests of the early Cenozoic set the stage for everything that came later in primate evolution, including ultimately the appearance of the genus Homo many tens of millions of years down the line. The Eocene primates were not, in any obvious sense, proto-humans. But they were the starting point of the lineage that would eventually produce them, and the warm, forested, food-rich world of the Eocene was what allowed that starting point to diversify sufficiently to produce the evolutionary raw material for subsequent experimentation. The Eocene also saw the first significant diversification of bats, another group that is easy to take for granted in the modern world, but represents a genuinely remarkable evolutionary achievement. Bats are the only mammals to have achieved true powered flight, and they did so early in the Cenozoic, with fossil bats already well developed and recognizably modern in form, appearing in Eocene deposits from multiple continents. The warm, insect-rich forests of the Eocene provided both the ecological incentive and the resource base for the evolution of bat flight, and once the basic body plan was established, bat diversification proceeded rapidly. Modern bats constitute roughly 20% of all living mammal species, a figure that consistently surprises people who have not thought much about mammalian diversity, and that diversity has its roots in the Eocene radiation of the group, in the warm forests of the early Cenozoic. The Prehistoricals, the group that today includes horses, rhinoceroses, and tapirs, were among the most ecologically prominent large mammals of the Eocene, diversifying into a wide range of body sizes and ecological niches. The Eocene relatives of the modern rhinoceros included some of the largest land mammals that have ever existed, culminating in a group called the Paraceratheres, commonly but slightly misleadingly referred to as Indracotherium or Proceratherium, in popular accounts that achieved body masses estimated at 15 to 20 tons, making them the largest land mammals in the fossil record by a considerable margin. These animals were essentially the ecological equivalent of elephants, but considerably larger, browsing on high vegetation in open woodlands and forest margins across Asia during the Eocene and Oligocene. They required a world with sufficient food productivity to support body masses of that scale, and the warm, vegetatively productive Eocene environment supplied it. The story of the Brontotheriidae, another group of large perissodactyls that diversified dramatically in the Eocene before going extinct at the Eocene-Oligocene boundary, illustrates something important about the relationship between warm climates and large body size. The Brontotheres began the Eocene as relatively modest animals, similar in size to a large tapir, and over the course of the epoch evolved into forms of truly impressive dimensions, with large males in the final Bronto, their genera carrying elaborate bony protrusions from their skulls that were presumably used in social competition. Their extinction at the end of the Eocene, correlated with the cooling transition to the Oligocene, is consistent with the general pattern. The warm world of the Eocene supported large body sizes. The cooling world that followed did not. The Brontotheres had evolved into a size class and ecological niche that the warmer world had made possible, and when that world changed, they had neither the time nor the evolutionary flexibility to adapt downward quickly enough. The Artiodactyls, the group that today includes deer, cattle, pigs, hippos, camels, and giraffes, and whose lineage also gave rise to the whales, were also diversifying through the Eocene, though the truly spectacular artiodactyl radiation that would produce the dominant large herbivores of the modern world was still largely in the future. Early Eocene artiodactyls were small, unimpressive creatures, roughly the size of modern small deer or rabbits, living in forest understories and eating a mixed diet of leaves, fruit, and possibly insects or small vertebrates. They were not, at this stage, the kind of animals you would write a chapter about, but they were accumulating the genetic and anatomical diversity that would eventually, in the cooler and more open environments of the later Cenozoic, give rise to the remarkable ecological success story of the grass-eating ruminant ungulates. The role of the Eocene climate in shaping plant evolution is itself a rich topic that tends to get overshadowed by the more dramatic animal stories. Flowering plants' angiosperms had been diversifying since the mid-Cretaceous, but the warm, stable conditions of the Eocene allowed them to achieve a level of diversity and ecological dominance that has not been surpassed since. The diversity of Eocene tropical forests, documented from fossil floras in locations ranging from the London clay of England to the Messel pit of Germany to deposits in coastal North America, was extraordinary. Families and genera that are today restricted to tropical regions appeared as far north as Middle Europe and Canada during the Eocene warmth, growing in environments that have no modern analogue warm, humid, frost-free forests at latitudes that today support temperate deciduous vegetation. The Messel pit in Germany deserves special mention because it is one of the most remarkable fossil deposits in the world and provides an extraordinarily detailed snapshot of Eocene life in what was then a subtropical environment at roughly the latitude of modern Frankfurt. The Messel site was, 47 million years ago, a volcanic lake in a warm forested landscape, and the deep anoxic bottom waters of the lake preserved organic material with exceptional fidelity. Fossils from Messel include not just bones but soft tissues preserved outlines of skin, fur, feathers, stomach contents, gut bacteria. Early horses are found at Messel with their stomach contents preserved, showing they ate fruit and leaves. Early primates are found with detailed skeletal information that has illuminated debates about early primate locomotion and diet. Ancient birds, bats, snakes, crocodilians, fish, and insects are preserved in extraordinary detail, offering a window into the Eocene world that no amount of fragmentary bone material from other sites could provide. It is, without exaggeration, one of the most scientifically valuable fossil sites on Earth, and the fact that it was nearly destroyed in the 1970s and 1980s by plans to convert it to a garbage dump is one of the more chilling near misses in the history of paleontology. The Eocene world, in all its warm, species-rich, ecologically inventive complexity, was the foundation upon which the subsequent Cenozoic history of life was built. The mammals that diversified in Eocene warmth, the whales that began their transition to fully marine life in Eocene seas, the primates that established themselves in Eocene forests, the grasses that were beginning their rise to ecological prominence in the late Eocene, all of these were laying the groundwork for the world that would follow as temperatures fell and environments changed. The warming of the PETM, dramatic and disruptive as it was in some ways, ultimately produced a more biologically diverse and ecologically complex world than what had existed before it, by providing the temperature and productivity conditions that allowed both body sizes and species diversities to reach their Cenozoic maxima. Titanoboa and its world were not anomalies. They were the natural expression of what life does when given sufficient warmth, sufficient time, and sufficient ecological space to do it. The planet has been cooling ever since, and the world we inhabit today with its ice caps, its seasonal variation, its relatively modest animal sizes compared to the Eocene giants, is in many ways a more constrained version of what life was doing in the early Cenozoic warmth. Which is not to say that our world is less interesting, just, perhaps, slightly less enormous. The cooling transition out of the Eocene warmth did not affect every part of the planet equally, and nowhere was the divergence in evolutionary outcomes more dramatic than in South America. While the northern continents were experiencing the gradual replacement of their warm-adapted Eocene faunas with the more familiar-looking mammal communities of the Oligocene and Miocene, South America was doing something else entirely, something so different that when scientists first began piecing together its fossil record in the 19th and early 20th century, they found themselves looking at an animal community that seemed to have been invented by a completely separate universe. The reason for South America's biological eccentricity is straightforwardly geographical. For roughly 30 to 35 million years, from the late Eocene until approximately 3 million years ago, South America was an island continent. Not an island in the small-scale sense of a landmass surrounded by water, but an island in the full continental sense, a piece of land the size of a modern subcontinent, separated from North America to the north by a seaway, and from Antarctica to the south by open ocean, with no significant land connection to any other major landmass. The animals that found themselves on this island when it separated from the rest of Gondwana were essentially the founding population for an entirely autonomous evolutionary experiment, one that would run for tens of millions of years without any significant external interference. The founding fauna of isolated South America was an interesting mix. The continent carried with it, when it separated, a collection of ancient mammals that had been present since the Cretaceous, or very early Paleocene primitive marsupials, some ancient placental lineages, and a collection of strange ungulate-like mammals that are not closely related to any living group. It also, somewhat later, received two important waves of colonization from Africa via oceanic rafting, a genuinely unlikely mode of faunal exchange that nonetheless happened at least twice, producing the South American monkeys and the South American caviomorph rodents, both of which arrived from Africa on natural rafts of vegetation during the Oligocene, crossing what was then a narrower Atlantic Ocean with the assistance of favourable currents. The logistics of this crossing, involving small animals presumably clinging to floating mats of tangled vegetation for weeks or months on the open ocean, are not something that would make it onto a recommended travel itinerary, but it clearly worked. What South America did not have, for the entire duration of its isolation, was any of the large, specialized carnivorous placentals that dominated predator guilds on other continents. No cats, no dogs, no bears, no hyenas. The ecological role of large terrestrial predator, the organism that hunts and kills large prey items on foot using speed, strength, and sharp anatomy, was vacant when South America became an island, and it stayed vacant for a very long time in terms of large placental carnivores. Evolution, reliably, does not leave large ecological vacancies unfilled. But the organism that stepped in to fill this particular vacancy was not what you might expect. The Forus racids, the group colloquially known as terror birds, a name that is, for once, not an exaggeration, were large, flightless, carnivorous birds that diversified to fill the apex predator role in South American terrestrial ecosystems for roughly 60 million years. They were the descendants of a bird lineage that had survived the KPG extinction and found itself, in the ecologically emptied post-impact world of South America, in the unusual position of being among the largest, fastest, and most capable predators on the continent with essentially no competition from large carnivorous mammals. The evolutionary response was predictable in retrospect. They got bigger, they got faster, they got more powerful, and they diversified into an ecological niche that on every other continent was occupied by animals with 4 legs and fur. At their most impressive, the largest Forus racids stood between 2.5 and 3 meters tall, roughly the height of a basketball net, for those who prefer their ancient terror measured in sporting equipment units. They were not nimble in the way of smaller birds. They were built along the lines of a biological assault vehicle, a massive hook-tipped beak capable of delivering powerful downward blows, strong muscular legs capable of sustained running, at speeds comparable to modern ostriches, reduced and essentially vestigial wings that played no role in locomotion, and a body plan that allocated evolutionary resources almost entirely to killing efficiency. Studies of Forus racid skull biomechanics, using CT scanning and finite element analysis to model the stresses in the beak during strikes, have suggested that the larger species could deliver blows comparable in force to a medium-weight boxer's punch, except with a razor-edge keratin hook rather than a padded glove, and delivered with the neck muscles of an animal that was significantly larger than a human. Their hunting strategy, inferred from anatomy and ecological context, was probably pursuit predation running down prey on the open grasslands and woodlands that expanded across South America as the climate cooled and dried through the Oligocene and Miocene, then dispatching it with powerful beak strikes to vulnerable areas. They were not the kind of predator that relies on stealth and ambush in the manner of cats. They were more analogous to running predators, ecological parallels to the cursorial predators of other continents, except built on a completely different body plan. This is a beautiful example of what biologists call convergent evolution, the independent arrival at similar ecological solutions by organisms that are not closely related, driven by similar selection pressures in similar environments. The terror birds were doing, in South America, essentially the same ecological job that large carnivorous mammals were doing everywhere else. They were just doing it on 2 legs with a beak instead of 4 legs with teeth, which is either impressive or alarming depending on your perspective. The South American mammal fauna that coexisted with the terror birds during this long period of isolation was itself remarkable and strange by the standards of any other continent. The native South American ungulates a broad collection of groups including the notungulates, litopterns, and astropotheres had evolved in complete isolation from the familiar ungulate groups of the northern continents and produced body forms that paralleled them in sometimes startling ways without any shared ancestry. The litopterns included animals that looked remarkably like horses, with long legs, a single functional toe on each foot, and teeth adapted for grazing an almost perfect ecological parallel to the true horses of North America, produced by completely independent evolution. The notungulates included forms that paralleled rhinoceroses, rodents, and small deer, again without any genetic connection to those groups. The toxodonts, large, heavy-bodied notungulates that persisted into the Pleistocene, looked something like a cross between a rhinoceros and a hippopotamus, and were, by all accounts, built for durability rather than elegance. The astropotheres, another uniquely South American group, were perhaps the strangest of the lot. Large, heavy animals with reduced nasal bones suggesting a mobile, possibly prehensile nose or a short trunk, and large canine teeth in some species. They occupied a niche something like a tapir or a small elephant, browsing on vegetation in wetter environments, and they did so with an anatomical combination that exists nowhere else in the mammalian fossil record. They are not closely related to tapirs or elephants. Those similarities are purely ecological, driven by the same general selection pressures on large, generalist herbivores in forested environments. Convergent evolution at work again, reliably producing familiar shapes from unfamiliar starting points. The marsupials of South America, descendants of the ancient marsupial lineages that had been present since the early Paleocene, also diversified into an impressive array of ecological roles. Among the most remarkable were the sprasodonts carnivorous marsupials that evolved alongside the terror birds and occupied the smaller and medium-scale predator roles that the terror birds, as large pursuit predators, were less suited to fill. Some sprasodonts developed saber-tooth-like canine teeth, paralleling the saber-toothed placental cats of the northern continents in a way that is, by this point, almost boringly predictable. Evolution converges on saber teeth for large carnivores in warm environments with sufficient large prey, regardless of the taxonomic identity of the carnivore in question. Saber teeth appear to be one of those evolutionary innovations that natural selection keeps independently reinventing whenever the right ecological conditions arise, which says something interesting about the constraints and attractors of carnivore morphology. The isolation of South America as a biological laboratory produced one more remarkable group worth discussing before we address what happened when that isolation ended: the giant ground sloths. Modern sloths are small, slow, endearingly strange animals that hang upside down in trees and move with a deliberateness that suggests they may be operating on a slightly different temporal scale from the rest of the world. Their ancient relatives, in isolated South America, were operating on a considerably grander scale. Ground sloths technically a paraphyletic assemblage of sloth relatives that independently evolved large body sizes and ground-dwelling habits in multiple lineages range from sheep-sized forms to the enormous Megatherium, which stood roughly 6 meters tall when rearing on its hind legs and weighed an estimated 4 to 6 tons. Megatherium was not fast, and it was not carnivorous, but it was built in a way that suggests few things in South America were seriously threatening it. The bone density in Megatherium's skeleton is remarkable. The limb bones are so thick relative to body size that they would be structurally capable of supporting an animal considerably larger than the animal they actually supported. This over-engineering of the skeleton may reflect the evolutionary heritage of small-bodied ancestors that needed dense, strong bones for a different purpose, or it may reflect selection for structural robustness in an animal that reared upright on its hind limbs to reach high vegetation. The long isolation of South America ended approximately 3 million years ago, when tectonic forces completed the uplift of the Central American land bridge, the Isthmus of Panama, and for the first time in 30 million years, North and South America were connected by a continuous corridor of land. This event, which triggered what paleontologists call the Great American Biotic Interchange, was one of the largest and most consequential faunal mixing events of the Cenozoic, and its consequences for South American life were, to put it diplomatically, significant. From North America, a wave of large placental mammals streamed southward across the new land bridge. Horses, tapirs, deer, camels, gomphotheres, elephant relatives, and a range of large carnivores including early relatives of jaguars, pumas, and spectacled bears. These were animals that had been evolving in competition with each other on the northern continents for tens of millions of years, tested, refined, and ecologically sophisticated in ways that the more sheltered South American fauna simply had not been. The result of their arrival in South America was, for many of the endemic South American groups, not pleasant. The native ungulate lineages, the notungulates, litoptons, toxodonts went extinct, replaced in their ecological roles by the morphologically similar but evolutionarily more competitive northern arrivals. The sparassodont carnivores, competing against a new influx of large, efficient placental predators, also disappeared. The terrorbirds, the apex predators of South America for 60 million years, found themselves suddenly in competition with large cursorial carnivores for the first time in their evolutionary history, and most of them went extinct relatively quickly, though at least one terrorbird species, Titanus walleri, managed to cross into North America and survive there for a time, which suggests they were not entirely outcompeted everywhere simultaneously. The South American exchange was not entirely one-sided. Animals moved northward too. Ground sloths, glyptodonts, capybaras, armadillos and opossums colonized North America, with varying degrees of long-term success. Ground sloths became one of the characteristic large mammals of Pleistocene North America, ranging from what is now Florida to Alaska, and leaving fossils across the continent. Glyptodonts, large, armored relatives of armadillos, with shells composed of fused bony plates that covered their entire dorsal surface in a pattern something like a living tank, established themselves in southern North America and survived there until the end of the Pleistocene. Opossums, uniquely among the Cenozoic southern invaders, are still present in North America today, which means that the marsupials of South America achieved at least one successful long-term colonization of the North, even if their placental counterparts fared considerably worse going in the other direction. The lesson that South America's evolutionary history teaches is one of the most important in all of paleontology. Geography matters as much as biology. The specific animals that filled any particular ecological role in any particular time and place were not inevitably produced by some universal law of evolution, selecting always for the same optimal forms. They were produced by whatever genetic and anatomical raw material happened to be present in that location when a given ecological opportunity opened up. South America had birds and marsupials when its large predator niches became available, so birds and marsupials filled them. North America and Eurasia had placentals, so placentals filled the equivalent roles there. The ecological outcomes, large cursorial predators, large armored grazers, small insectivores, look similar between isolated continents because similar ecological pressures produce similar functional solutions. But the animals achieving those solutions were radically different, and the specific history of how they got there was entirely contingent on which piece of real estate they happened to be standing on when the evolutionary opportunities arose. This lesson extends naturally into the broader story of tectonic history and its consequences for life. because South America's isolation was itself a tectonic event, a product of the movement and separation of continental plates that had been operating continuously throughout the Cenozoic and continues to operate today. The biological story of the Cenozoic cannot be separated from the geological story of moving continents, and understanding how the two are intertwined requires taking a step back from individual organisms and looking at the planet as a whole machine one in which biology and geology are not separate systems, but deeply coupled aspects of a single, continuously operating process. The tectonic history of the Cenozoic is, in its broad outlines, a story of gradual fragmentation and rearrangement. The ancient supercontinent of Gondwana, which had already begun breaking apart in the Mesozoic, continued its disintegration through the Cenozoic. South America separated from Africa. India sailed northward from its Gondwanan origin toward its eventual collision with Asia. Australia separated from Antarctica and moved northward. Antarctica became isolated at the South Pole and began accumulating ice. The northern supercontinent of Laurasia similarly continued to break apart, with the Atlantic Ocean widening as North America and Europe moved apart, and with various land connections forming and breaking between North America and Eurasia at high latitudes as sea levels and tectonic positions changed. Each of these tectonic events had direct and measurable biological consequences, because the geography of the continents determines the geography of ocean currents, which determines the distribution of heat and precipitation around the planet, which determines what kinds of ecosystems can exist in different places. When India collided with Asia approximately 50 million years ago, a collision that had been building through the entire Eocene, as India's northward migration accelerated, it began the uplift of the Himalayan mountain range and the Tibetan plateau, a process that would take tens of millions of years to reach its current scale, but whose effects on atmospheric circulation were already being felt in the Oligocene. The Himalayas and the Tibetan Plateau function as an enormous barrier to atmospheric flow, deflecting air masses and creating the conditions for the monsoon circulation that today delivers the seasonal rainfall on which billions of people and entire regional ecosystems depend. Before the Himalayas existed, the climate of Asia was different in fundamental ways, more uniform, less dramatically seasonal, without the intense monsoon systems that now characterize South and Southeast Asian climate. The ecological communities of Asia today are shaped, in their distribution and seasonal rhythms, by a mountain range whose existence is itself the product of a continental collision that began 50 million years ago. The drying of Central Asia that accompanied the Himalayan uplift drove major changes in the vegetation and fauna of the region, contributing to the expansion of grasslands and steppe environments that in turn drove the evolution of the grazing ungulates, horses, bovids, camels that are today among the dominant large herbivores across the Eurasian landmass. The connection between the uplift of the Himalayas and the evolution of modern grassland-adapted mammals is not a simple or direct one, but it is real and traceable. Geological change produced climate change produced vegetation change produced animal evolutionary change, in a chain of causation that links the collision of tectonic plates to the specific body forms of animals grazing in Central Asian steppes today. The opening of the Drake Passage between South America and Antarctica, which began around 33 to 35 million years ago, as these two continents separated, had consequences that reached even further. Before the Drake Passage opened, the ocean around Antarctica was connected to the rest of the global ocean in a way that allowed warm water from the north to flow southward and moderate Antarctic temperatures. Once the passage opened, the Antarctic circumpolar current could establish itself a massive flow of water circling the entire Antarctic continent, with no land barrier to interrupt it, effectively isolating the Southern Ocean thermally from the warmer waters to the north. The result was the progressive cooling and eventual glaciation of Antarctica, transforming a continent that had supported forests as recently as the Eocene into the ice-covered wasteland it is today. The loss of the Antarctic forest ecosystem and the cooling of high-latitude ocean temperatures globally as Antarctic ice began forming and cold bottom water spread across the ocean floor drove the global cooling trend that would eventually, tens of millions of years later, produce the ice ages of the Pleistocene. The formation of the Isthmus of Panama, which we have already encountered in the context of the Great American Biotic Interchange, also had profound effects on ocean circulation that extended far beyond its impact on land animals. Before the isthmus closed approximately 3 million years ago, water flowed freely between the Atlantic and Pacific Oceans at the latitude of Central America, allowing the equatorial ocean circulation to operate as a continuous belt around the globe. When the isthmus closed, this flow was blocked, and the Atlantic and Pacific became effectively separate ocean basins at those latitudes. The consequences were dramatic. Cut off from Pacific water exchange, the Atlantic developed different temperature and salinity patterns. The Gulf Stream, which today carries warm tropical water northward along the eastern coast of North America and then across the Atlantic to Western Europe, intensified substantially after the closure of the Isthmus of Panama, driven by the altered pressure gradients of a newly isolated Atlantic. The intensified Gulf Stream carried more moisture into the North Atlantic, which increased precipitation over Greenland and eventually contributed to the growth of the Greenland ice sheet and the intensification of Northern Hemisphere glaciation. There is something genuinely remarkable about this chain of causation. The closure of a seaway in Central America, driven by tectonic forces that had been operating for tens of millions of years, intensified a current in the North Atlantic, which increased snowfall over Greenland, which grew a massive ice sheet, which altered global climate patterns sufficiently to drive the evolution of a new kind of human ancestor capable of surviving in colder, more variable environments. The connection between continental drift and human evolution is not direct or simple, but it is real, and it illustrates the fundamental principle that the history of life cannot be understood in isolation from the history of the planet's physical structure. The marine consequences of the Panama closure were also significant and relatively well documented. As the Atlantic and Pacific became separate basins, populations of marine organisms that had previously been continuous across the Central American Seaway were split into two isolated groups. Over the subsequent 3 million years, those populations have diverged into distinct species pairs of closely related but distinct species on either side of the isthmus, one Atlantic and one Pacific, that are similar enough to reveal their common ancestry, but different enough to demonstrate millions of years of independent evolution. Scientists call these sister species geminate pairs, and there are hundreds of them: fish, invertebrates, crustaceans, corals, each pair representing a population that was split by the closure of a seaway, and has been evolving separately ever since. The Isthmus of Panama is, in effect, a natural experiment in speciation, with a very precise start date, and it has been extensively studied precisely because the timing is known so well. Not many evolutionary processes come with a clear geological timestamp, which makes the Panama closure particularly valuable for testing models of how quickly populations diverge after geographic isolation. The broader point that emerges from looking at tectonic history and its biological consequences is one that should probably be more widely appreciated than it is. The evolution of life on Earth has never been a purely biological process. It has always been a geological process as well shaped and redirected by the physical rearrangement of the planet's surface, the changes in climate driven by that rearrangement, the opening and closing of migration routes, the isolation and reconnection of populations, and the formation of new environments and the destruction of old ones. The organisms that fill the modern world are not simply the products of the biological logic of natural selection acting in a fixed environment. They are the products of natural selection acting in an environment that has been continuously and dramatically transformed by the movement of the planet's tectonic plates over hundreds of millions of years. Every mountain range is a biological event. Every ocean basin that opens or closes is a biological event. Every land bridge that rises or sinks is a biological event. The geology and the biology are not separate stories running in parallel. They are one story, operating at different scales and through different mechanisms, but ultimately inseparable in their consequences and their meaning. Understanding life on Earth means understanding the planet it lives on, not just as a stable background stage for the drama of evolution, but as an active, restless, continuously changing participant in that drama, as influential in shaping its outcomes as any organism that has ever lived on its surface. The East African Rift System provides a particularly compelling illustration of this principle, because its tectonic history is directly entangled with one of the most important evolutionary stories of the entire Cenozoic, the evolution of the hominins. The East African Rift is a zone where the African continent is slowly being pulled apart along a north-south axis, creating a chain of elongated valleys, lakes, and volcanic mountains running from the Afar Triangle in Ethiopia, southward through Kenya, Tanzania, and into Mozambique. This rifting has been ongoing for roughly 25 million years, and it has progressively created a topographic and climatic barrier between the more humid forests of Western Africa and the drier, more open environments of Eastern Africa. The timing of increased rifting activity in East Africa and the diversification of hominins is not coincidental. As the rift deepened and the eastern side of the continent became increasingly cut off from the moisture-bearing winds coming off the Atlantic, the vegetation of Eastern Africa shifted from continuous forest toward more open woodland and eventually grassland and savanna. This shift in vegetation created new ecological opportunities and new ecological pressures for the primates living in this changing environment. Primates adapted to forest living were faced with a choice, in evolutionary terms: adapt to the new, more open environments, or retreat toward the remaining forest refugia in the west. Different lineages made different choices, and those choices drove the divergence between the lineages that would eventually produce modern chimpanzees and bonobos in the west, and the hominin lineage in the east. The Pliocene climate variability hypothesis, developed by the paleoclimatologist Rick Potts among others, argues specifically that it was not simply the opening up of African environments, but the increased variability of those environments oscillating between wetter and drier conditions on timescales of thousands to tens of thousands of years that drove hominin brain evolution. In highly variable environments, generalist cognitive abilities learning, problem-solving, behavioral flexibility are more valuable than specialized physical or behavioral adaptations that work well in one specific condition, but fail when conditions change. The East African Rift, by creating an environment of high temporal variability driven by the interplay of tectonic, orbital, and atmospheric factors, may have been selecting specifically for cognitive flexibility in the hominins that lived there, which is either a flattering or a humbling origin story for human intelligence, depending on how you feel about being the product of an unstable geological zone. The relationship between tectonic activity and biological evolution is also clearly visible in the history of island biogeography. Volcanic islands, which are created by tectonic and volcanic processes and then slowly eroded and submerged over millions of years, have repeatedly served as natural laboratories for evolutionary experimentation in ways that strongly parallel the South American isolation story, but on a smaller and often more rapid scale. The Hawaiian archipelago, formed by the movement of the Pacific Plate over a stationary hotspot that has been generating volcanic islands for tens of millions of years, shows a beautiful succession of evolutionary radiations, birds, insects, plants on each island, with each new island providing fresh ecological opportunity for organisms that colonized from older islands and then diversified in isolation. The Hawaiian silverswords, a group of plants that have diversified from a single ancestral colonist into dozens of species ranging from rosette plants to shrubs to trees to climbing vines, illustrate in miniature the same principles of geographic isolation and ecological opportunity that drove the great continental evolutionary radiations of the Cenozoic. Tectonic events also drove significant changes in global sea level, which in turn opened and closed shallow water migration routes and created and destroyed coastal marine habitats. During periods of high global temperature like the Eocene optimum, there was little or no ice at the poles, sea levels were substantially higher than today, and shallow inland seas covered large portions of what are now continental interiors. North America during the Eocene had a shallow seaway running north-south through the central part of the continent, connecting the Gulf of Mexico to the Arctic Ocean. This western interior seaway had been a feature of the Cretaceous and survived into the early Cenozoic before its final regression, and its presence created extensive shallow marine habitats that supported their own distinctive communities of marine organisms completely different from those of the open ocean. As global temperatures fell through the Oligocene and Miocene, ice accumulated at the poles, sea levels dropped, and these shallow inland seas retreated, exposing vast new areas of continental interior to colonization by terrestrial plants and animals. And the great grassland expansions of the Miocene, which drove the diversification of grazing mammals discussed earlier, were possible partly because the falling sea levels of the Oligocene and Miocene exposed large areas of flat, well-watered continental interiors that had previously been covered by shallow seas. What ties all of these stories together, the South American Biological Laboratory, the Himalayan uplift and Asian monsoons, the Drake Passage and Antarctic glaciation, the Isthmus of Panama and the Great American Interchange, The East African rift and hominin evolution, the sea level changes and grassland expansion, is a single, unifying principle. The surface of the Earth is not a fixed stage on which biological evolution performs. It is a co-protagonist in the story, as dynamic and consequential as the organisms themselves, driving change on timescales ranging from thousands to tens of millions of years, and shaping the outcomes of evolutionary processes in ways that could not have been predicted from biology alone. The Cenozoic era is, in this sense, the period during which the interplay between tectonic change and biological evolution became most clearly legible in the geological record, because the organisms involved were complex enough to leave detailed fossil evidence, and because the tectonic events were recent enough to be reconstructed with considerable precision. We know, approximately, when the Himalayas reached heights sufficient to significantly deflect atmospheric circulation. We know when the Drake Passage opened sufficiently to establish the circumpolar current. We know when the Isthmus of Panama closed. And we know from the fossil record how biological communities responded to each of these changes. The correspondence is detailed enough to move beyond general principles and into specific causal chains, a level of understanding of the relationship between geology and biology that was simply impossible before the development of modern geochronology, paleoclimatology, and molecular phylogenetics. This understanding has practical implications that extend well beyond the academic interest of understanding ancient events. The Earth's tectonic plates are still moving, the Himalayas are still rising, the East African rift is still widening, and will eventually, tens of millions of years from now, split Africa into two separate continents. The Atlantic is still widening, Antarctica is still cooling. The biological consequences of these ongoing geological processes are still unfolding, operating on timescales that make them invisible within the span of human civilization, but entirely real from the perspective of deep time. The evolutionary pressures generated by ongoing climate change, much of which has geological as well as anthropogenic components, are today selecting for the same kinds of traits that geological change has always selected for: flexibility, generalism, tolerance of variable conditions, and the ability to move when a formerly hospitable environment becomes hostile. The terror birds are gone. The litopterns and notungulates are gone. The enormous isolated South American ecosystem that produced them was dismantled by the arrival of more competitive faunas from the north. But the principle their story illustrates has not gone anywhere. Geography shapes evolution, isolation produces novelty, and the outcome of evolutionary processes is always contingent on the specific historical circumstances, the specific piece of ground, the specific tectonic configuration, the specific climate state in which those processes operate. Biology plays out on a geological stage, and the stage is never still. The geological stage had been set over tens of millions of years of tectonic rearrangement, climate shifts, and biological diversification. The continents were roughly where we find them today. The grasslands had expanded across the interiors of North America, Eurasia, and Africa, providing vast, productive ecosystems that could support large bodies in quantities that earlier, more forested Cenozoic environments had not. The ice ages had begun cycling through their relentless rhythms, driving climate variability that selected for adaptability and range. And into this world, evolution delivered what might reasonably be described as its most extravagant period of large animal experimentation since the Mesozoic. The Pliocene and Pleistocene epochs, spanning from roughly 5 million years ago to approximately 10,000 years ago, were the age of megafauna, a period when enormous animals were not the exception, but something close to the rule, and when the diversity of large-bodied species on multiple continents exceeded anything seen before or since in the Cenozoic. The word megafauna technically refers to animals above a certain body mass threshold, usually 44 kilograms or more, though definitions vary, but in common usage it evokes something considerably more dramatic. The mammoths, the giant ground sloths, the armored glyptodonts, the massive short-faced bears, the oversized rhinoceroses, the diprotodonts of Australia, the giant deer of Europe and Asia, and the various enormous predators that hunted them. These were not isolated oddities. They were characteristic and abundant members of their ecosystems, present on every continent except Antarctica, and collectively they represented a level of large animal biomass and diversity that has not been matched since their disappearance at the end of the Pleistocene. understanding why so many large animals existed in the Pliocene, and Pleistocene requires understanding the specific combination of conditions that made large body size advantageous, or at least not so disadvantageous as to be selected against across such a broad range of environments and taxa. The ecological logic of large body size is not simple. Large animals require more food per individual than small ones. They reproduce more slowly, which means populations recover more slowly from losses. They have fewer places to hide from predators, though large enough body size eventually means having no predators to hide from. They are more vulnerable to environmental change because their home ranges are larger and their populations denser. On the other side of the ledger, large body size confers resistance to predation from smaller predators, improved thermal regulation in variable climates, access to food resources too tough or too high for smaller competitors, and advantages in competition with other individuals of the same species for mates and territories. The Pleistocene ice ages created environmental conditions that specifically tilted this cost-benefit analysis toward large body size in ways that are worth examining. The cycling of glacial and interglacial periods drove dramatic, repeated changes in vegetation across middle and high latitudes, forests expanding during warm periods, contracting during cold ones, grasslands and tundra expanding during glaciations, retreating during interglacials. Animals that could survive these cycles needed to be either highly mobile, capable of tracking their preferred habitat as it shifted geographically, or metabolically flexible enough to exploit whatever resources were locally available. Large body size assists with both. Large animals can travel further per unit of energy expenditure than small ones, and their larger energy reserves allow them to tolerate periods of food scarcity that would be fatal to smaller animals. The mammoth steppe, the vast cold grassland that extended across northern Eurasia and into North America during glacial periods, connecting what are now Siberia, Alaska, and the unglaciated portions of Canada via the Bering Land Bridge, was one of the most productive grassland ecosystems in Earth's history, despite its cold temperatures and harsh conditions. It supported enormous herds of woolly mammoths, woolly rhinoceroses, bison, horses, cave lions, and a range of other large mammals at densities that would seem impressive even by the standards of the modern African savanna. The productivity of the mammoth steppe has been a subject of some scientific controversy for a long time. It was assumed to be a relatively impoverished environment, more like modern Siberian tundra than a rich grassland, but more recent analysis of ancient soils, pollen records, and isotopic data from fossil bones has suggested a much more productive system than previously thought, capable of supporting large mammal biomass through the cold winters via the high energy density of grasses and sedges compared to the woody vegetation of forests. The mammoths themselves are the iconic megafaunal animals of the Pleistocene, and with good reason they were genuinely impressive by any reasonable standard of impressiveness. The woolly mammoth, Mammuthus primigenius, was not actually the largest mammoth species, but it is the most familiar because it lived in environments conducive to exceptional preservation, and because it overlapped temporally with early human populations who depicted it extensively in cave art. Adult male woolly mammoths stood roughly 3.4 meters at the shoulder and weighed between 5 and 6 tons, comparable to a large modern African elephant, though covered in a dense coat of long reddish-brown hair and equipped with tusks that curved outward and upward in a way that looks, to modern eyes, simultaneously magnificent and structurally inconvenient for getting through doorways. Not that this was a frequent concern for Pleistocene mammoths. The tusks deserve particular attention because they were not merely impressive ornamentation. Analysis of mammoth tusks using isotopic chemistry and growth ring analysis has revealed a remarkable amount of information about individual mammoth lives, growth rates, seasonal feeding patterns, periods of stress, migration routes, and even the age at which females gave birth for the first time. Mammoth tusks grew continuously throughout the animal's life, adding new material at the base each year in a pattern similar to tree rings, and the chemical composition of each year's growth recorded information about what the animal ate and where it travelled that season. The tusks of some well-preserved Siberian mammoths have been analysed in detail sufficient to reconstruct something approaching individual life histories. Not a biography exactly, but a record detailed enough to identify years of nutritional stress, periods of migration, and the physiological changes associated with breeding season. This is a level of paleontological detail that would have seemed like science fiction to researchers a generation ago, and it illustrates both how much information is preserved in fossil tissues and how much our ability to extract that information has improved with analytical technology. The largest mammoth species, the steppe mammoth Mammuthus trogontherii, was considerably bigger than the woolly mammoth shoulder heights of up to 4.5 meters have been estimated for large males, making it one of the largest land mammals in the entire Cenozoic, outside of the enormous Eocene and Oligocene perissodactyls. The steppe mammoth inhabited the temperate grasslands of Eurasia during the Middle Pleistocene, before the woolly mammoth evolved from it during the subsequent glacial cooling. Its size, by the standards of Cenozoic mammals, was extraordinary, approaching the lower range of large sauropod dinosaurs, which is a comparison that tends to somewhat reframe the popular image of the Pleistocene as a world of merely large animals rather than truly gigantic ones. The Columbian mammoth of North America, Mammuthus columbi, was a separate species from the woolly mammoth and considerably larger than its males, reaching shoulder heights of roughly 4 meters and weights of up to 10 tons, which places it firmly in the upper tier of land animal body sizes for the entire Cenozoic. The Columbian mammoth inhabited temperate and subtropical North America, ranging from what is now southern Canada to Central America, and its range overlapped with that of the woolly mammoth only at the far northern edge of the continent, where the two species appear to have occasionally interbred, producing hybrids documented by ancient DNA analysis. The existence of mammoth hybrid zones in glacial-era North America is one of the more charming discoveries of recent paleogenomics, demonstrating that the barriers between mammoth species were permeable at the edges in ways that parallel the behavior of closely related large mammals in modern Africa. In the ocean, the Pliocene and early Pleistocene were the era of Otodus megalodon, the giant shark whose reputation in popular culture has, if anything, been somewhat undersold relative to the actual animal. Megalodon was a close relative of the modern great white shark, but was not, as sometimes depicted, simply a scaled-up version of it. It was a distinct and in some ways more specialized animal, adapted to hunting large marine mammals, particularly the baleen whales and toothed whales, that had diversified enormously in the warm, productive Miocene and Pliocene oceans. Size estimates for Megalodon have varied considerably over the years as methodologies have improved, but the current scientific consensus places maximum length at roughly 15 to 18 meters, with some exceptional individuals possibly reaching 20 meters. The teeth, which are what megalodons left behind in substantial numbers, are triangular, serrated, and in large specimens can reach 18 centimeters in height, large enough that the first researchers to study them in the 17th century initially believed they were the petrified tongues of large serpents, which was a classification that tells you something about the limits of 17th century marine biology. The jaw of a large megalodon has been estimated at roughly 2 to 3 meters across, wide enough to comfortably accommodate a standing adult human with room to spare on both sides. Not that any megalodon would have found this a particularly compelling use of its capabilities. Its prey was primarily large baleen whales, and the bite marks preserved on whale fossils from the Miocene and Pliocene tell a fairly clear story about hunting strategy. Megalodon appears to have targeted the locomotory anatomy of large whales, biting into flippers and tail flukes to immobilize prey before going for more vulnerable areas. This is a different strategy from modern great white sharks, which typically target soft tissue directly, and it reflects the different body size of the prey. A large baleen whale is a considerably more formidable target than a sea lion, and disabling it before attempting to feed is a considerably more pragmatic approach. The logistics of taking down a 30-ton whale are not trivial even for a shark the size of a school bus, which is presumably why Megalodon developed the approach it did rather than simply biting into whatever was convenient. Megalodon's extinction, which occurred sometime between 3.5 and 2.5 million years ago, is one of the more discussed events in Pleistocene paleontology, partly because of the animal's cultural prominence and partly because the timing aligns with several significant environmental changes. The leading hypotheses involve some combination of cooling ocean temperatures, reducing Megalodon's preferred warm water habitat, the closure of the Isthmus of Panama disrupting ocean circulation and productivity, and the diversification of more agile, cooperative predators, early killer whales and large dolphins that competed more effectively for the whale prey that Megalodon depended on. No single factor is sufficient to explain the extinction with certainty, but the alignment of multiple simultaneous pressures in a relatively short geological window is consistent with the pattern seen in many megafaunal extinctions. Multiple stresses combining to push a large-bodied, slow-reproducing species past the threshold of population viability. The terrestrial megafauna of Africa during the Pliocene and Pleistocene was, in some ways, the most diverse and ecologically complex large animal community of the entire Cenozoic, and Africa is notable for being the one continent where a substantial portion of that megafaunal diversity has actually survived to the present day, albeit in reduced form. The African megafauna of the Pleistocene included many of the same animals present today: elephants, rhinoceroses, hippos, giraffes, lions, leopards, but also a range of additional large animals that are now extinct, including several species of giant buffalo, a large-horned sheep relative called Pelorivus, with horn spans of up to 3 meters, enormous pigs of the genus Metridiochorus that would make modern warthogs look like lapdogs, and a diverse range of large carnivores, including the giant African hunting hyena Pachyrhacota, which was considerably larger than modern spotted hyenas and appears to have been a bonecracker of formidable capacity. The persistence of African megafauna into the present, while comparable fauna on other continents went extinct, is one of the most important and hotly debated topics in Pleistocene paleontology, and it anticipates a discussion that properly belongs to the next chapter. But the ecological context is worth establishing here. Africa's large animals had been evolving alongside early hominins and their precursor species for millions of years. They had experienced, gradually and continuously, the gradual improvements in human hunting technology and social coordination that characterized the long evolutionary history of the Homo lineage in Africa. The African megafauna, in other words, had time to develop what ecologists call a wariness of humans' behavioral responses to human predation that reduced individual vulnerability and helped populations persist even as human hunting pressure increased. This is a calibration that took generations to develop, and it was precisely the calibration that megafauna on other continents, encountering modern human hunters for the first time, entirely lacked. The Australian megafauna tells a particularly stark version of this story. Australia in the Pleistocene was home to an extraordinary array of giant animals. Diprotodon optatum, the largest marsupial that ever lived, was roughly the size of a rhinoceros and resembled a wombat scaled up to implausible dimensions. Procoptodon goliah, the largest kangaroo ever, stood nearly 3 meters tall and had a flat, forward-facing face, giving it an expression of mild surprise that seems appropriate for an animal of those proportions. Thylacaleo carnifex, the marsupial lion, was a predator whose skull biomechanics suggest a bite force per unit body mass, exceeding that of any modern cat, equipped with shearing premolars that functioned as enormous biological scissors. And Megalania prisca, a giant monitor lizard whose length estimates range from 4 to 7 meters, meaning that Australia had not only an enormous carnivorous mammal, but also what was essentially a terrestrial crocodile wandering its forests and woodlands. All of these animals went extinct within a geologically brief period following the arrival of humans in Australia, approximately 65,000 years ago. The correlation is striking. A continent full of enormous animals that had been evolving and diversifying for tens of millions of years, in the complete absence of any primate predator, suddenly receives a population of highly intelligent, technologically capable hunter-gatherers, and within tens of thousands of years, a blink in geological time, the entire megafaunal community is gone. The debate about the relative contributions of human hunting and climate change to the Australian megafaunal extinction is ongoing and contentious, but the timing of the collapse and the fact that previous climate fluctuations of similar or greater magnitude had not caused comparable extinctions argue strongly for a significant human contribution. The megafauna of Eurasia present a more complex picture, because Eurasia had been in contact with African hominins for long enough that some behavioral adjustment to human predation had likely occurred. The woolly mammoth and woolly rhinoceros of Eurasia survived multiple glacial cycles and multiple periods of hominin presence before going extinct relatively late in the Pleistocene, suggesting greater resilience than the Australian fauna. But they too disappeared, and the timing of their extinction generally tracks the expansion of modern Homo sapiens across their ranges, earlier in areas where sapiens arrived earlier, later in refugia, where human populations were sparse or arrived late. The last population of woolly mammoths known from the fossil record lived on Wrangel Island in the Arctic Ocean until approximately 4,000 years ago, well within historical time, contemporary with the construction of the Egyptian pyramids surviving long after all mainland populations had disappeared, in a location so remote and so difficult to access that human hunting pressure remained low until the end. The glyptodonts of South America occupy a special place in the megafaunal story because they were, in a purely engineering sense, one of the most impressively constructed animals that ever existed. Relatives of modern armadillos, glyptodonts, had evolved the armadillo's basic body plan, a shell of bony dermal scutes covering the back, to an extreme that armadillos can only dream about, or perhaps sensibly choose not to, given the practical constraints involved. The shell of a large glyptodont was a single fused dome of bone, immobile, formed from hundreds of interlocking polygonal plates, covering the entire dorsal surface from the back of the neck to the base of the tail. The tail itself was armoured with rings of bone and, in some genera, terminated in a spiked or clubbed tip that was presumably used for defence or competition. The weight of the shell alone in a large adult Dedicurus, one of the biggest glyptodont genera, has been estimated at 400 to 500 kilograms out of a total body weight of perhaps 1,400 kilograms. They were, in effect, walking fortresses, and the predators of Pleistocene South America apparently found them as difficult to penetrate as that description suggests. The giant ground sloths of the Pleistocene, including the truly enormous Megatherium that we briefly encountered in the chapter on South American evolution, add another dimension to the megafaunal picture. Ground sloths were not confined to South America by the Pleistocene, as noted in the context of the Great American Biotic Interchange. They had successfully colonized North America and were present across much of the continent during the late Pleistocene. The diversity of ground sloth species in Pleistocene North America included forms ranging from Megalonyx jeffersoni, named partly because Thomas Jefferson, who was an enthusiastic amateur naturalist in addition to his other activities, described fossil bones of the animal in 1799, and initially suggested they might belong to a giant lion to the enormous Erematherium, which approached Megatherium in size and left fossil trackways showing how it moved across Pleistocene landscapes. The trackways, discovered in South Carolina and Brazil, preserve the footprints of ground sloths, walking bipedally on their hind feet with their forelimbs raised, a posture used, apparently when travelling rather than feeding, and one that gives the tracks an unexpectedly humanoid quality that has reportedly startled more than one fossil hunter encountering them for the first time. The short-faced bears of North America, the genus Arctodus, specifically the giant short-faced bear Arctodus simus, deserve mention as one of the most formidable large carnivores of the Pleistocene, and one that is considerably less well known than its size warrants. Arctodus simus was the largest terrestrial carnivore of Pleistocene North America, with standing heights at the shoulder of roughly 1.8 meters and estimated weights of up to 900 kilograms in large males. It had longer legs relative to body size than modern bears, suggesting it was built for running rather than the lumbering pace associated with modern ursids, though whether it was primarily a predator, a scavenger, or an omnivore that relied on intimidating other predators from their kills is still debated. Its short, broad face had powerful jaw muscles and could generate considerable bite force, but the relatively weak teeth suggest a dietary emphasis on soft tissue rather than bone crushing. The most current interpretation of its ecology suggests a large, wide-ranging omnivore that spent considerable time displacing other predators from kills, a behaviour called kleptoparasitism, which is a technical term for an animal that has essentially decided that stealing is more energy efficient than hunting, a strategy that is hard to argue with when you weigh 900 kilograms and can run faster than a modern bear. The cave bear of Eurasia, Ursus spelaeus, was a different animal from Arctodus but similarly impressive in scale, larger than modern brown bears, with males averaging perhaps 500 to 600 kilograms and exceptional individuals reaching 1,000 kilograms. Cave bears were primarily herbivorous, despite their impressive size and predatory-looking anatomy, with tooth-wear patterns suggesting a diet dominated by plant material. They denned extensively in caves during winter, sometimes in large groups, and the accumulation of their bones in European cave systems has produced some of the most abundant Pleistocene fossil assemblages on the continent in some caves. The bones of hundreds or thousands of cave bears have been found, representing generations of animals using the same hibernation sites over thousands of years. The density of these bone accumulations is striking enough that early European naturalists, encountering them in the 18th century, initially believed they must represent the victims of some catastrophic mass mortality event, rather than the natural accumulation of hibernation deaths over geological time. The truth that cave bears simply died in their dens with some regularity over thousands of years, and that bones in caves preserve exceptionally well, is less dramatic but speaks to just how common these animals were. The Pleistocene megafauna also included in North America animals that are technically still present today, but in dramatically reduced form. Bison that were considerably larger than their modern descendants, grizzly bears with a continental range far greater than their current distribution, American lions that were larger than African lions, and American cheetahs whose presence on the Great Plains helps explain why pronghorn antelopes can run at speeds far in excess of anything that currently hunts them. The pronghorn's extraordinary speed, it can sustain 80 kilometers per hour for extended distances, making it the fastest land animal in the Western Hemisphere, is one of those evolutionary legacies that only makes sense in the context of the predators that are now gone. Evolution does not immediately remove adaptations when the selection pressure driving them disappears, and the pronghorn carries in its physiology the memory of a predator community that has not existed for 10,000 years. This is the world that was, a planet populated by enormous animals on every continent, a world in which large body size had been selected for across millions of years by the combination of productive grasslands, cycling climates, and predator-prey dynamics that rewarded size. The giant deer of Eurasia, Megaloceros giganteus, commonly called the Irish elk, though it was neither exclusively Irish nor exclusively an elk, represents one of the more visually spectacular entries in the Pleistocene megafauna catalogue. Its antlers, which were present only in males and shed and regrown annually in the manner of all deer, spanned up to 3.7 meters from tip to tip and weighed roughly 40 kilograms a set of head ornaments that would be, by any reasonable workplace health and safety standard, entirely impractical. The metabolic cost of growing this much bone every year was enormous, requiring the animal to find and consume large quantities of calcium and phosphorus within a relatively short growing season. Analysis of Megaloceros fossil sites has shown that many individuals in certain populations were in poor nutritional condition relative to others, with bone pathologies consistent with mineral deficiency. The antlers, in other words, were a genuine physiological burden even for an animal well adapted to carrying them. But they persisted because the reproductive advantages conferred by impressive antlers in male-male competition and female choice were sufficient to outweigh the metabolic costs, even substantial metabolic costs. Evolution's approach to cost-benefit analysis is, at times, strikingly indifferent to what common sense might suggest. The woolly rhinoceros, Chelodonta antiquitatis, deserves more attention than it typically receives in popular accounts of Pleistocene megafauna, perhaps because it lacks the charisma of mammoths or the cultural resonance of giant sloths. It was nonetheless a genuinely substantial animal, weighing up to 2,700 kilograms, with a shoulder height of roughly 1.8 meters, and it was, for most of the Pleistocene, one of the characteristic large herbivores of the Eurasian mammoth steppe. Its two horns, the larger of which could reach 1.5 meters in length, were made of keratin, the same material as human fingernails, which means that hair growing to remarkable lengths is, structurally speaking, what you are looking at. The horns were flattened laterally rather than circular in cross-section, suggesting they were used for sweeping snow aside to reach vegetation in winter, a plausible behavioral inference supported by the wear patterns observed on fossil horns from Siberian permafrost specimens. Woolly rhinoceros remains have been found preserved in permafrost with hair, skin, and soft tissue intact, providing a level of morphological detail that is impossible to obtain from dry bone alone, and that has substantially improved our understanding of their appearance and ecology. The Eurasian cave hyena, Crocuta spelaea, was a subspecies of the spotted hyena that inhabited most of Europe and Western Asia during the Pleistocene, and was, on average, somewhat larger than modern spotted hyenas, with maximum body weights estimated at around 100 kilograms in large individuals. Cave hyenas were among the most ecologically significant carnivores of Pleistocene Europe, competing directly with early hominins for large prey and for access to cave shelter. The fossil record of European cave sites contains evidence of this competition in the form of mixed assemblages of hyena-gnawed bones and hominin-worked stone tools, sometimes in the same layers, suggesting that caves changed hands between hyena denning and human occupation on timescales of decades to centuries. The relationship was presumably not friendly, though the specific dynamics of competition and coexistence between cave hyenas and early Neanderthals across thousands of years of European prehistory is a subject of ongoing research that continues to produce surprising results. The North American predator guild of the late Pleistocene was, by any comparative measure, extraordinarily diverse. In addition to Arctodus simus, it included the American lion Panthera atrox, larger than modern African lions, with males estimated at 250 to 350 kilograms, the saber-toothed cat Smilodon fatalis, the American cheetah Myrcinonyx, the dire wolf Enocean dirus, multiple large birds of prey, and the recently established Homo sapiens. This is a predator community of a density and diversity that has no modern analogue anywhere on Earth. The modern African savanna, which supports the richest predator community in the contemporary world, has perhaps 5 or 6 species of large predators coexisting in a given region. Late Pleistocene North America had at least twice that number in overlapping ranges, all competing for the same pool of large herbivore prey. How this community was structured ecologically, which species dominated which prey types, how they partitioned resources and avoided direct competition, is a question that modern ecological theory has been applied to with interesting results, using stable isotope analysis of fossil bones to reconstruct dietary overlap and competition. The dire wolf, despite its formidable name, was in many respects a more conservative predator than its reputation in popular culture, suggests the version appearing in fantasy fiction is essentially a normal wolf at a slightly exaggerated scale, which is actually not far wrong. Enocean dirus was larger and more robust than the grey wolf, with heavier bones and more powerful teeth adapted for crushing bone rather than just cutting soft tissue. But it was ecologically similar to a modern wolf in most respects. A pack hunter, probably pursuing horses, bison, and other large ungulates on the open grasslands of Pleistocene North America. The La Brea tar seeps in Los Angeles have produced fossils of thousands of individual dire wolves, in numbers that dwarf the remains of any other large predator at the site, suggesting they were extraordinarily abundant at their ecological peak, abundant enough that trapping of prey in tar must have been a significant source of food for local populations. The bones of herbivores trapped in tar would have attracted scavengers and predators, which themselves sometimes became trapped, creating the extraordinary fossil assemblages for which La Brea is famous. It is, in effect, a geological record of a food chain caught in the act of operating, preserved in asphalt that has been dated to between 40,000 and 10,000 years ago. Smilodon fatalis, the most famous of the saber-toothed cats, was built along significantly different lines from modern large cats, and deserves a more careful description than the usual characterization, as simply a large cat with very long teeth. The canine teeth, which could reach 28 centimeters in length in large adults, are the most obvious feature, but they were the outcome of a suite of anatomical modifications that extended throughout the skull and skeleton. The jaw could open to an angle of approximately 120 degrees, roughly twice the gape of a modern lion, which was necessary to bring the saber teeth to bear on prey. The neck muscles were extraordinarily powerful relative to body size, providing the driving force for the downward stabbing strike that was the saber-tooth's primary killing mechanism. The forelimbs were heavily muscled and equipped with large retractile claws, probably used to hold and immobilize prey during the killing bite. Smilodon weighed roughly 160 to 280 kilograms, comparable to a large modern lion, and probably hunted large, thick-skinned prey like bison, horses, and young mastodons or mammoths that were sufficiently large to justify the specialized killing apparatus. The megafauna of the Pleistocene were not simply large versions of modern animals, they were an entire ecological system organized around large body sizes, with prey animals large enough to sustain predators of exceptional dimensions, predators specialized for dealing with thick-skinned or heavily armored prey, and scavengers capable of processing the enormous carcasses those predators left behind. The condors, vultures, and teratons that soared over the Pleistocene landscapes of North America were finding food resources of a scale that simply does not exist in modern North America. A dead mammoth carcass represents a nutritional bonanza that could sustain a vulture community for weeks, and that required birds with sufficiently large wingspans and sufficiently powerful beaks to process the tough hide and massive bones. The California condor, which today survives only thanks to intensive conservation efforts, is in a very real sense a biological relic of this vanished world, an animal built for processing large carcasses in an environment where large carcasses were once common, persisting in a world that no longer provides the ecological context for which it was evolved. It was by any measure one of the most impressive biological configurations that has ever existed on Earth, and it was ending. Not slowly, not gradually, not through the familiar processes of extinction that had been operating throughout the Cenozoic, the competitive replacements, the climate-driven range contractions, the sea level changes. It was ending quickly, in geological terms, and the reasons for that speed would force a reckoning with a new kind of force in the history of life on Earth, one that had never operated at quite this scale before. The Pleistocene megafauna had survived, as a collective, approximately 50 glacial cycles over the past 2.5 million years. 50 cycles of expanding ice sheets, falling temperatures, shifting vegetation zones, changing sea levels, and collapsing food resources and the mammoths, the giant ground sloths, the saber-toothed cats, the cave bears, and the rest of the enormous cast of characters described in the previous chapter had come through all of them. Not without stress, not without population contractions and range reductions, but without the kind of mass extinction that would erase dozens of genera simultaneously across multiple continents. The ice ages were, from the megafauna's perspective, a familiar and manageable challenge that their lineages had been navigating successfully for millions of years. They had done it before, they would do it again, and then, between roughly 50,000 and 10,000 years ago, depending on the continent in question, most of them were gone. The scale and speed of this extinction event is genuinely extraordinary when you look at the numbers. In North America, an estimated 33 out of approximately 45 genera of large mammals went extinct at or near the end of the Pleistocene. In South America, the losses were even more severe. Roughly 50 genera of large animals, including all of the spectacular native South American megafauna that had survived the Great American Biotic Interchange, vanished within a few thousand years. Australia lost essentially its entire megafaunal community, as noted previously. Europe lost its woolly mammoths, woolly rhinoceroses, cave bears, cave lions, cave hyenas, and giant deer. Only Africa retained a substantial proportion of its Pleistocene megafaunal diversity, and even Africa lost some large species and saw significant range contractions in others. The total extinction rate across the late Pleistocene is staggering, in comparison to the background extinction rate of the Cenozoic. The Cenozoic had been, relative to the end Cretaceous catastrophe, a period of relatively modest extinction rates for large mammals. Species came and went, but not in the wholesale fashion of a mass extinction event. The late Pleistocene collapse of the megafauna happened at a rate that looks, in the geological record, distinctly abnormal, more like the tail end of a mass extinction than the ordinary background turnover of an otherwise stable period. And identifying the cause, or causes, of this abnormality has been one of the most contentious debates in all of quaternary science for the past several decades. The climate hypothesis is the older of the two main competing explanations, and it has the virtue of pointing to a real and well-documented environmental change. The end of the last glacial maximum and the rapid warming of the early Holocene, which transformed large areas of grassland and tundra into forest and wetland, reducing the habitat available for the large grazing mammals that had dominated those environments. The woolly mammoth, the woolly rhinoceros, the giant deer, these were animals adapted to cold, open grassland conditions. As their preferred habitat contracted northward and eventually disappeared from large parts of their former range, populations declined, and some species presumably went extinct when the last viable habitat was gone. This is a logical and internally consistent story, and it draws on mechanisms that are well understood from modern ecology. Habitat loss is one of the primary drivers of contemporary species extinctions, and there is no reason to think it was any less effective in the late Pleistocene. The problem with the climate hypothesis, as the primary explanation, is that it does not explain the timing particularly well. The last glacial maximum ended approximately 19,000 to 20,000 years ago, and the warming that followed, though rapid by geological standards, unfolded over thousands of years. But the megafaunal extinctions on different continents did not all cluster around this warming event. They clustered, with quite striking consistency around a different date, the date of first human arrival. Australia lost its megafauna approximately 46,000 to 50,000 years ago, well before the last glacial maximum ended, but right around the time that anatomically modern humans first colonized the continent. North and South America lost their megafauna approximately 13,000 to 10,000 years ago, right around the time that humans first entered the Western Hemisphere in significant numbers via the Bering Land Bridge. Europe and Northern Asia lost their remaining megafauna somewhat later, in pulses that track the expansion and technological development of modern human populations across the continent. The overkill hypothesis, originally proposed in its modern form by the paleoecologist Paul S. Martin in the 1960s, and subsequently developed and contested by a large number of researchers, argues that this correlation is not coincidental. The core claim is that modern humans, Homo sapiens, were significantly more capable hunters than any predator the Pleistocene megafauna had previously encountered, and that the combination of high hunting efficiency, rapid population growth, and the naivety of prey that had no prior experience with this particular kind of predator produced a wave of extinction wherever modern humans arrived. The analogy to modern situations is instructive. Large animals on islands that have never experienced human hunting. The dodo being the most familiar example, though there are many others are famously approachable and easily killed by hunters because they have no behavioral response calibrated to human predation. The Pleistocene megafauna of the Americas and Australia, encountering modern humans for the first time, are argued to have been in exactly this position. Behaviorally unprepared for an intelligent, cooperative, technologically equipped predator that hunted in organized groups and did not limit its predation to the most vulnerable individuals. The overkill hypothesis, in its original simple form, has been substantially refined and complicated by subsequent research because the evidence is considerably messier than a clean narrative of human hunters systematically eliminating megafaunal species one by one. Direct evidence of human hunting of specific megafaunal species kill sites with stone tools associated with megafaunal remains is actually surprisingly rare relative to the scale of the proposed extinction, which is one of the persistent criticisms of the overkill hypothesis. You would expect, if humans were the primary driver of extinction across dozens of species on multiple continents, to find extensive archaeological evidence of megafaunal hunting across broad time periods and geographic areas. Instead, kill sites are comparatively uncommon, and many megafaunal species have left essentially no direct evidence of human predation, despite their presumed extinction by humans. The defenders of the overkill hypothesis offer several responses to this objection. First, the conditions required to preserve a kill site bones in association with stone tools in a context that is clearly the result of hunting rather than scavenging are sufficiently demanding that most hunting events would leave no archaeological trace, making the rarity of kill sites entirely consistent with heavy hunting pressure over many generations. Second, humans need not have hunted every megafaunal species to extinction directly. Killing the apex predators of an ecosystem, or reducing the population of a keystone herbivore below the threshold necessary to maintain habitat structure, can trigger cascading extinctions of species that were never directly targeted. Third, humans hunting at rates that would seem modest by modern standards, taking 1 or 2 mammoths per band per year, for example, could be sufficient to drive populations of slow reproducing large animals below viable numbers over timescales of a few centuries, a process that would leave limited archaeological evidence but produce genuine extinction. The mathematics of this last point have been worked out in considerable detail by ecological modelers and are surprisingly compelling. Large animals with long generation times, late age at first reproduction, and low reproductive rates are extremely vulnerable to even modest levels of additional mortality from human hunting, because their populations cannot recover quickly enough to compensate. The most sophisticated current view of late Pleistocene megafaunal extinction is neither pure climate hypothesis nor pure overkill, but a synergistic model in which both factors contributed in ways that varied by region, species, and the specific circumstances of human arrival. The climate changes at the end of the last glacial maximum were real, and did reduce habitat for cold-adapted megafauna. This is not disputed. But for most species and most regions, climate change appears to have been a contributing stressor, rather than a sufficient cause. It reduced population sizes and restricted ranges, making species more vulnerable to the additional pressure of human hunting that arrived simultaneously or shortly afterward. The combination of a population already stressed by habitat change and then subjected to novel hunting pressure was, for many species, more than they could demographically withstand. The African exception to the global megafaunal extinction pattern is the most powerful single piece of evidence in this debate, and it deserves careful examination. Africa is the only continent where the pre-Pleistocene megafaunal diversity is substantially represented in the modern fauna. Elephants, rhinoceroses, hippos, giraffes, zebras, Cape buffalo, lions, leopards, cheetahs, spotted hyenas, and a remarkable diversity of antelopes and other ungulates are all present-day continuations of an ancient megafaunal community. Africa did lose some large species at the end of the Pleistocene. A giant buffalo, several large pigs, and a few other taxa went extinct, but the losses were far less comprehensive than on any other continent. Why? The most widely accepted explanation draws on the coevolutionary history between African megafauna and African hominins. The hominin lineage had been present in Africa for roughly 6 to 7 million years, gradually improving its hunting capabilities over the entire span of megafaunal existence on the continent. The African megafauna had millions of years in which natural selection could calibrate behavioral responses to hominin predation, producing animals that were appropriately wary of bipedal primates with sharp objects, that maintained sufficient distance from approaching humans to give adequate time to flee, and that generally behaved in ways that made them harder to hunt than animals without this evolutionary experience. This behavioral wariness is observable in modern African wildlife. African elephants, lions, and other large animals are typically far more cautious around humans than equivalent animals in places where human hunting pressure is evolutionarily novel. The behavioral memory of millions of years of coexistence with human hunters is written into the instincts of modern African megafauna, and it is probably what saved them. The Americas provide the starkest contrast. Anatomically, modern humans arrived in the Western Hemisphere approximately 15,000 to 13,000 years ago. The exact timing is still debated, with some evidence suggesting earlier coastal arrivals, but the substantial colonization that preceded the main megafaunal extinction clearly happened around this time frame. The megafauna of the Americas had never encountered any primate predator of any kind, let alone one with the hunting capabilities of modern humans. Their only experience with predators was with the quadrupedal carnivores, dire wolves, American lions, short-faced bears that had been selecting for the same anti-predator behaviors for millions of years. Run fast, watch for movement at ground level, stay in groups for mutual vigilance. None of these behaviors are particularly useful against human hunters who can throw projectiles from outside the flight distance of most large animals, and who can pursue prey across distances that exhaust even large, fit herbivores. Experimental evidence from modern situations involving islands or regions with limited prior human contact consistently shows that large animals are dramatically easier to approach and kill in the absence of a prior evolutionary history with human hunting. The endemic birds of the Mascarene Islands, including the dodo of Mauritius and the related solitaire of Rodriguez, walk towards sailors with what contemporary accounts describe as apparent curiosity rather than fear, having evolved on islands with no terrestrial predators of any kind. Within decades of human arrival, both species were extinct. This is a compressed version, on an island timescale, of the process proposed to have occurred on continental scales in the Pleistocene, with the difference that the continental megafauna had more individuals spread across larger areas, so the process took centuries to millennia rather than decades. The outcome, however, was similar. The specific methods by which early Americans hunted Pleistocene megafauna have been studied extensively through the archaeological record of what is called the Clovis culture, named for a distinctive style of fluted stone projectile, point first identified near Clovis, New Mexico, and subsequently found across much of North America in deposits dated to approximately 13,000 to 12,500 years ago. Clovis points are associated with the remains of mammoths, mastodons, and other large megafauna at a number of sites, providing some of the clearest direct evidence for human megafaunal hunting in the Western Hemisphere. The points were hafted onto wooden or bone spear shafts and were almost certainly used in conjunction with throwing devices at ladles or spear throwers that dramatically increased the velocity and penetrating force of a thrown spear beyond what could be achieved by hand. An atlatl-propelled Clovis-pointed spear could penetrate the thick hide of a mammoth to the depth necessary to reach vital organs, a capability that was genuinely novel in the predator community that mammoths had previously experienced. Whether Clovis hunters were the first humans in the Americas, or whether earlier populations preceded them, is a question that has been substantially revised in recent years by new archaeological discoveries. Several sites in North and South America now have credible evidence for human presence substantially before the Clovis horizon, most notably the Cooper's Ferry site in Idaho, with evidence suggesting human occupation around 16,000 years ago, and the Paisley Caves in Oregon with coprolites dated to similar ages, and sites in South America with claimed dates of 20,000 to 30,000 years. If pre-Clovis populations were present in the Americas for thousands of years before the main megafaunal extinctions, this complicates the simple correlation between human arrival and megafaunal collapse, suggesting either that early populations were too sparse to drive extinctions, that the extinctions were delayed relative to human arrival, or that the timing of the extinctions was indeed determined primarily by climate, with human hunting as a secondary factor. The mathematical models of megafaunal extinction under human hunting pressure have been refined considerably since Martin's original overkill proposal, and they consistently produce extinction timelines of a few hundred to a few thousand years for large-bodied, slow-reproducing species under realistic assumptions about human hunting rates and population growth. This is fast enough to appear essentially instantaneous in a geological record with the temporal resolution of most Pleistocene sediment sequences, but slow enough that it would be difficult to detect archaeologically without a very dense record of sites with good chronological control. The models also consistently show that species with the lowest reproductive rates, elephants, rhinoceroses, ground sloths, are most vulnerable to even modest additional mortality, while faster reproducing species can absorb higher hunting pressure without population collapse. This prediction is consistent with the observed pattern. The species that went extinct in the late Pleistocene were disproportionately the largest, slowest reproducing forms, while smaller and faster reproducing megafauna survived in greater numbers. The cascade effects of megafaunal extinction deserve consideration, because the disappearance of large herbivores and large predators from ecosystems does not simply leave a smaller version of the same ecosystem. It fundamentally restructures the way the ecosystem functions. Large herbivores maintain open habitats by removing vegetation. Mammoths, for instance, have been argued to have been keystone engineers of the mammoth steppe, maintaining the open grassland structure of that ecosystem through their feeding, trampling, and movement. Their removal likely contributed to the conversion of open steppe and grassland to closed forest, or scrub across large areas of the northern hemisphere, changing albedo, water cycling, and nutrient dynamics in ways that persisted for thousands of years. The concept of trophic rewilding, reintroducing large herbivores to modern landscapes to restore ecosystem functions lost with the Pleistocene extinctions, draws directly on this understanding, and experiments in Siberia with the Pleistocene Park project have demonstrated that large grazing animals can indeed convert mossy tundra to grassland under appropriate conditions, suggesting that the ecosystem effects of the original megafaunal extinctions were substantial and long-lasting. The removal of large predators similarly restructured ecosystems through what ecologists call trophic cascades, the effects of predator removal on prey populations, and the downstream consequences of those effects on vegetation. In Yellowstone National Park, the reintroduction of wolves in the 1990s after a 70-year absence produced not just changes in elk populations, but changes in elk behavior, vegetation structure, riverbank stability, and ultimately river channel morphology, a cascade of effects that had been set in motion by wolf removal decades earlier and reversed by wolf reintroduction. The removal of the entire suite of large Pleistocene predators, American lions, dire wolves, short-faced bears, saber-toothed cats from North American ecosystems at the end of the Pleistocene, must have produced trophic cascade effects of comparable or greater magnitude, restructuring plant communities and herbivore populations in ways whose consequences are still, arguably, visible in the structure of North American ecosystems today. The debate about human versus climate causation is, in many respects, the wrong framing because the evidence consistently points to both being real and significant, with their relative contributions varying by continent, species, and the specific timing of events in each region. What the debate has accomplished over decades of research and argument is a substantially improved understanding of the mechanisms involved. The specific vulnerabilities of large-bodied, slow-reproducing megafauna to elevated mortality, the behavioral naivety of animals encountering novel predators for the first time, the synergistic interaction between climate stress and hunting pressure, the cascade effects of removing keystone species from ecosystems. These mechanisms are not just historically interesting. They are directly relevant to the conservation challenges facing large animals in the modern world, where habitat loss, hunting pressure, and climate change are operating simultaneously on megafauna populations that are, in many cases, already stressed to the edge of viability. What the late Pleistocene extinctions established, for the first time in Earth's 4.5 billion year history, was the existence of a biological entity capable of driving global-scale ecological change at rates faster than most evolutionary processes can respond to. A single species, operating through behavioral rather than physiological means, had within tens of thousands of years reshaped the biology of every continent it inhabited. The forests of North America, the grasslands of South America, the savannas of Australia, all had been ecologically reorganized by the activities of one primate that had left Africa with a brain, a social structure, and a toolkit that no prior evolutionary history had prepared the rest of the world's megafauna to deal with. This was something genuinely new, not new in the sense of unprecedented ecological impact, volcanic eruptions, asteroid impacts, tectonic events had all produced larger and faster ecological changes, but new in the sense of being caused by the decisions and activities of a living organism rather than by physics or chemistry. The geological record. Now it was beginning to record something else, the decisions of a species that had learned to think about the future, and still, for reasons that remain entirely understandable from an evolutionary standpoint, consistently chose the food in front of it over the food that might be there in 100 years. The megafauna were gone. The world they had structured the great open grasslands maintained by mammoth herds, the tundra shaped by woolly rhinoceros browsing, the South American pampas engineered by generations of ground sloths and glyptodonts was gone with them, replaced by ecosystems that had reorganized around their absence. The ancient DNA evidence that has accumulated over the past 2 decades has added a new dimension to the megafaunal extinction debate that was simply unavailable to earlier researchers, and it has produced some genuinely surprising results. Analyses of ancient DNA extracted from mammoth bones and teeth preserved in Siberian permafrost have allowed scientists to reconstruct mammoth population history in remarkable detail, tracking changes in population size, genetic diversity, and geographic structure over the past 100,000 years or more. The picture that emerges is more nuanced than either a simple climate or a simple overkill story. Mammoth populations show evidence of declining genetic diversity, beginning well before the last glacial maximum, suggesting that population contractions had been occurring for tens of thousands of years. But the final collapse of most populations appears rapid, and coincides with both the post-glacial warming and the expansion of human populations across the mammoth's range. The two factors were operating simultaneously, and the ancient DNA data does not cleanly separate their contributions. Similar analyses have been applied to other Pleistocene megafaunal species with sufficient DNA preservation. Irish elk, cave bears, cave lions, and woolly rhinoceroses have all been subjected to ancient genomic analysis, and in each case the patterns show a combination of long-term demographic change, periods of expansion and contraction, correlated with glacial cycles, and a terminal decline in the late Pleistocene that is difficult to attribute solely to climate, without invoking human hunting as an additional factor. The cave bear genome, sequenced from multiple specimens across a time series, shows a dramatic decline in effective population size beginning approximately 35,000 to 40,000 years ago, which is considerably earlier than the main warming event and correlates more closely with the expansion of modern humans into Europe. Cave bears went extinct approximately 24,000 years ago, during a glacial period rather than during the subsequent warming, which argues against a primarily climate-driven extinction for this species. The isotopic evidence from megafaunal fossils has also provided important insights into the dietary and ecological flexibility of various species in the face of changing conditions. Strontium and oxygen isotopes in fossil teeth can reveal whether individual animals were migrating seasonally or were resident year-round in specific areas, while carbon and nitrogen isotopes reflect dietary composition, and the types of vegetation consumed. Studies of woolly mammoth isotope records from Siberian specimens show that some populations were highly mobile, tracking seasonal vegetation across large distances, while others appear to have been more sedentary, and the sedentary populations tend to show earlier signs of nutritional stress and population decline as their habitat contracted. Mobility was, it appears, a significant survival strategy for late Pleistocene megafauna facing climate change, and populations that lost the ability to track their required habitat, whether through habitat fragmentation, hunting pressure, or both, were at considerably greater risk of extinction. The archaeological evidence for early human hunting of megafauna has expanded substantially since Martin's original overkill proposal, and it now includes well-documented kill sites on multiple continents. In North America, sites like Waco Mammoth in Texas, Dent in Colorado, and Murray Springs in Arizona preserve clear associations of Clovis technology with mammoth remains. In South America, sites in Uruguay and Argentina preserve evidence of early human exploitation of native megafauna, including toxodonts and giant ground sloths. In Siberia, sites like Yana River and Berelek provide evidence of intensive mammoth hunting, extending back tens of thousands of years, though whether this northern Asian hunting pressure was sufficient to drive extinctions, or whether the Siberian megafauna were more resilient due to lower human population densities is still debated. The totality of the archaeological evidence now makes a reasonable case for widespread human predation of megafauna across multiple continents and time periods, even if the evidence is still less dense than overkill proponents would ideally like. The vegetation change evidence provides another independent line of data bearing on the extinction question. Pollen records from lake sediment cores across the northern hemisphere show dramatic vegetation shifts at the end of the Pleistocene transitions from grassland-dominated to forest-dominated pollen assemblages across large areas of what had been mammoth steppe and other open environments. These vegetation changes would indeed have reduced the habitat available for cold-adapted grazers. But a complication arises. In some regions, the vegetation changes appear to have occurred after the megafaunal extinctions rather than before them, suggesting that the loss of large herbivores may have caused or accelerated the vegetation change rather than the reverse. This is consistent with the keystone herbivore hypothesis that mammoths and other large grazers were actively maintaining open habitats through their feeding behavior, and that their removal allowed vegetation succession toward closed forest to proceed unchecked. The sequence of events matters enormously for establishing causation, and in some regions the data suggests that the humans arrived, the megafauna disappeared, and then the vegetation changed a sequence that is difficult to explain without assigning significant causal weight to the human hunting component. The question of whether the late Pleistocene megafaunal extinction qualifies as a genuine mass extinction, comparable in its biological significance to the 5 major mass extinctions of Earth's history, has been debated with some passion. By some metrics, it does. The proportion of the large mammal genera lost worldwide in the late Pleistocene is comparable to the proportion of marine genera lost in some of the recognized mass extinction events. By other metrics, it does not. The taxonomic breadth was narrower, concentrated primarily in large land mammals, rather than affecting multiple phyla across marine and terrestrial environments simultaneously, and the total species loss, while very large in absolute terms, was smaller in proportion to total global biodiversity than the recognized mass extinctions. The most measured assessment is probably that the late Pleistocene event was a genuine ecological catastrophe with mass extinction characteristics for large-bodied terrestrial mammals, without qualifying as a global mass extinction by the strictest definition. This is a distinction that may provide some cold comfort to the mammoths. The surviving megafauna of the modern world, African elephants, white and black rhinoceroses, hippopotamuses, giraffes, the big cats of Africa and Asia represent a heavily depleted remnant of what existed in the Pleistocene, and they face in the modern era the same combination of habitat loss and hunting pressure that their predecessors encountered at the end of the Ice Age in accelerated and intensified form. The conservation status of virtually every surviving megafaunal species is concerning. The northern white rhinoceros is functionally extinct, with only 2 surviving individuals as of the most recent counts. The Javan rhinoceros survives in a single population of fewer than 80 individuals in a single national park in Indonesia. African elephant populations, while larger than rhinoceros populations, are in significant decline across much of the continent. The same human activities that drove the Pleistocene megafaunal extinctions, hunting, and habitat modification are operating today at a pace and scale that makes the Pleistocene events look measured by comparison. What the late Pleistocene extinctions ultimately demonstrated, beyond the proximate debate about climate versus humans, is the existence of a new kind of evolutionary force on Earth, one that operates through cognition and culture rather than through biology. The capacity for cumulative technological development, for coordinated social hunting, for rapid geographic dispersal, and for modifying environments at landscape scales gave Homo sapiens a suite of ecological capabilities that were genuinely unprecedented in the history of life. Individual organisms had always shaped their environments. Beavers build dams, earthworms restructure soil, trees modify microclimates, but no single species had ever previously combined the individual intelligence, the social coordination, the technological capability, and the reproductive rate necessary to restructure the large animal communities of entire continents within centuries to millennia. The world had encountered a new kind of agent, and the megafauna were the first to experience its consequences. The world had changed, as it had always changed, but this time the primary agent of change was not a volcano, not an asteroid, not a shifting tectonic plate. It was a small-brained, large-footed, intensely social primate from East Africa, whose own story had been quietly unfolding alongside these extinctions, and whose story was just beginning in earnest. The primate that would eventually reshape the biology of every continent on Earth started its career in a fairly unpromising position. The earliest hominins, the lineage that diverged from the ancestors of modern chimpanzees, roughly 6 to 7 million years ago in Africa, were, by the standards of the Pliocene landscape they inhabited, not obviously special. They lacked the size of the large herbivores they lived alongside. They lacked the speed of the cursorial predators that hunted them. They lacked the armoured skin of the rhinoceroses, the horns of the giant buffalo, the formidable weapons of the saber-toothed cats. What they had, at this early stage, was a slightly unusual posture, a modest increase in relative brain size compared to their ape relatives, and a set of circumstances that were, depending on how you look at it, either deeply challenging or extremely educational. They were, in the ecological hierarchy of the African Pliocene, somewhere between medium-sized prey and small-time scavenger, which is not, historically, a starting position that predicts becoming the dominant ecological force on the planet. And yet, the defining feature of early hominin evolution, which distinguishes it from the pattern seen in most other mammalian lineages, is the extraordinary degree to which brain size technically, endocranial volume, the size of the brain cavity increased relative to body size over the course of the lineage. This process, called encephalization, is not unique to hominins, but the rate and scale of brain size increase in the human lineage over the past 3 million years has no real parallel in the mammalian fossil record. The earliest hominins, represented by genera like Sahelanthropus and Ardipithecus, had brain sizes roughly comparable to modern chimpanzees around 300 to 370 cubic centimeters, which is small enough to fit in a teacup with room to spare, and which produces a level of cognitive capability that is impressive for a non-human primate, but was not, at this stage, producing civilizations. By the time of the Australopithecines, the group that includes the famous specimen nicknamed Lucy, Australopithecus afarensis, who lived approximately 3.2 million years ago, in what is now Ethiopia, brain sizes had increased to roughly 380 to 430 cubic centimeters. This is a modest increase over earlier hominins in absolute terms, but the Australopithecines also show skeletal evidence of habitual bipedalism, walking upright on 2 legs, that had significant implications for subsequent brain evolution. The advantages of bipedalism are debated, but one well-established consequence is that it freed the forelimbs from locomotion, allowing the hands to become specialized for manipulation rather than weight-bearing. Hands that are good at fine manipulation are useful for making and using tools. Tools amplify the effectiveness of behaviors that the brain plans and executes, and more complex tool use and planning generates selection pressure for larger, more capable brains. The feedback loop between bipedalism, freed hands, tool use, and brain development is one of the foundational narratives of human evolutionary biology, and while the specific causal relationships are more complicated than a simple sequential chain, the correlation between the emergence of habitual bipedalism and the subsequent acceleration of brain size increase is real and meaningful. The appearance of the genus Homo in the fossil record, approximately 2.4 to 2.8 million years ago, marks the beginning of the main phase of hominin brain expansion. The earliest Homo species, including Homo habilis and its relatives, had brain volumes in the range of 510 to 690 cubic centimeters, a substantial increase over the Australopithecines, and are associated with the earliest well-documented stone tool industry, called the Oldowan tradition, after the Olduvai Gorge in Tanzania, where many of the defining specimens were found. Oldowan tools are, by the standards of later lithic technology, relatively simple, primarily sharp flakes struck from stone cobbles, suitable for cutting meat and breaking bones rather than for complex manufacturing tasks. They were nonetheless sufficient to transform hominin ecology in a significant way, because a sharp stone flake is the difference between accessing and not accessing the nutritious marrow and soft tissue of large animal carcasses. Scavenging from the kills of large predators, which would have been highly profitable but also highly dangerous without the ability to rapidly process carcasses, became considerably more practical with even basic cutting tools. The important thing about Homo habilis and its ecological situation is what it reveals about the early trajectory of hominin success. It was not built on physical capabilities but on behavioral ones. Homo habilis was not faster than the cursorial predators that shared its landscape. It was not stronger than the large carnivores it competed with for carcasses. It was not better armoured than the herbivores that could trample it. It survived and thrived because it had access to a behavioral flexibility, the ability to learn from experience, plan ahead, teach skills to other individuals, and modify its environment in simple ways that no other organism in its ecological community possessed to the same degree. This flexibility allowed it to exploit resources that were otherwise inaccessible, to avoid dangers that it could not physically resist, and to occupy a broader ecological niche than any comparable-sized primate had previously managed. The subsequent 2 million years of Homo evolution are characterized by a continuous and rapid increase in brain size, punctuated by the appearance of new species with progressively larger brains and more sophisticated behavioral repertoires. Homo erectus, which appeared approximately 1.9 million years ago and was among the first hominins to leave Africa, had brain volumes ranging from around 600 to over 1,100 cubic centimeters, in later representatives already approaching the lower range of modern human brain sizes. Homo erectus made Acheulean hand axes, a significantly more sophisticated stone tool technology than the Oldowan tradition, and there is evidence from African and Asian sites that Homo erectus was an active and capable hunter of large prey, not merely a scavenger dependent on the kills of other predators. The geographic range that Homo erectus achieved, spreading from Africa across Europe and Asia within a few 100,000 years of its appearance, demonstrates a level of ecological adaptability and technological capability that was genuinely without precedent in hominin history. The control of fire, which the evidence suggests was achieved by hominin populations somewhere between 400,000 and 1 million years ago, with some disputed evidence pushing dates earlier, still represents the moment when hominins acquired a technology that changed their ecological situation more profoundly than anything since bipedalism. Fire provided warmth that extended the range of habitable environments into colder climates. It provided light that extended the active period of the day into hours when large nocturnal predators were most active. It provided a social focus around which groups could gather, share food, and engage in the kind of extended communication that probably accelerated the transmission of learned skills and knowledge between individuals. And critically, it provided a way to process food cooking that increased the caloric availability of both plant and animal foods, reduced the time and energy required for digestion, and allowed hominins to extract more nutritional value from the same quantity of food. The cooking hypothesis, developed most thoroughly by the primatologist Richard Wrangham, argues that cooking was not merely a useful technological addition to the hominin behavioral repertoire, but a primary driver of the dramatic brain size increase that characterizes later Homo. The brain is metabolically expensive despite comprising only about 2% of body mass. It consumes approximately 20% of resting metabolic energy in modern humans. Maintaining and growing a large brain requires a reliable supply of high-quality, calorie-dense food. Cooking makes food more digestible and more calorie-dense, effectively pre-processing it externally in ways that reduce the metabolic cost of digestion and make more calories available for other uses, including maintaining a large brain. The correlation between the appearance of controlled fire use in the archaeological record and the most rapid phase of hominin brain size increase is consistent with this hypothesis, though establishing direct causation from the fossil and archaeological record is inherently difficult. What fire did not do, and this point is worth emphasizing, because popular accounts sometimes imply otherwise, was make hominins physically more formidable than the large predators and megafauna they coexisted with. A campfire is excellent for warmth, cooking, and keeping away some predators at night. It is not a substitute for tusks, claws, or a body weight of several tons. The role of fire in early hominin survival was primarily defensive and dietary, not offensive. The ability to maintain a fire through the night reduced the vulnerability of sleeping groups to nocturnal predators, which was a significant advantage in an African landscape populated by large cats, hyenas, and other dangerous animals that were primarily active after dark. But early fire-using hominins were still, by day and in open landscapes, relatively vulnerable prey animals that needed to maintain constant vigilance, and preferred the safety of trees and rocky terrain over open ground. The emergence of anatomically modern Homo sapiens approximately 300,000 years ago in Africa, based on the most recent fossil evidence, marks the culmination of the encephalization process. In terms of brain size, modern human brain volumes average around 1,350 cubic centimeters, roughly 3 to 4 times the size of the earliest Homo specimens and 10 times the size of the earliest hominins. But brain volume alone does not capture what was different about modern humans. The expansion of certain brain regions, particularly the prefrontal cortex, associated with planning, social reasoning, and impulse control, and the regions associated with language production and comprehension, produced cognitive capabilities that were qualitatively as well as quantitatively different from those of earlier hominins. The capacity for fully modern language, abstract symbolic thought, and cumulative cultural transmission, the ability to pass learned knowledge and innovations across generations in a way that accumulates rather than resets, appears to have been fully developed in Homo sapiens, and it was this capacity more than raw brain size that ultimately made the species ecologically transformative. The behavioral modernity transition, the moment when the full behavioral repertoire of modern humans, including art, symbolic expression, complex social networks, and sophisticated long-distance trade, appears in the archaeological record has been dated to approximately 50,000 to 100,000 years ago by some researchers, with earlier, more scattered evidence of symbolic behavior pushing possible dates back to 300,000 years ago or more. The debate about when behavioral modernity appeared is partly a debate about what counts as behavioral modernity, and partly a genuine empirical question about the timing of specific innovations in the fossil and archaeological record. What is not in serious dispute is that by the time modern humans began dispersing out of Africa approximately 60,000 to 70,000 years ago, they carried with them a behavioral toolkit language, cooperative planning, cumulative technological development, social networks capable of exchanging information and resources across large distances that was without parallel in the history of life. The Neanderthals, who had evolved in Europe and Western Asia over the preceding several 100,000 years from populations of archaic Homo that had left Africa earlier, provide an important comparative case for understanding what was different about modern humans. Neanderthals were not, as they are sometimes depicted in popular culture, stupid or primitive. Their brains were, on average, slightly larger than those of modern humans. They made sophisticated stone tools of the Mousterian tradition, used ochre for possible symbolic purposes, produced ornaments from eagle talons and shell, and cared for their injured and elderly in ways that imply significant social complexity and emotional investment in group members. They survived in Europe through multiple glacial cycles, adapting to environments ranging from Mediterranean woodland to subarctic steppe. They were, by any reasonable standard, cognitively capable, socially complex, and ecologically successful hominins, and yet, within a few thousand to tens of thousands of years of modern human arrival in Europe, approximately 40,000 years ago, Neanderthals were gone. The cause of Neanderthal extinction is another hotly debated topic, but the most current evidence suggests a combination of factors: competition with modern humans for resources, some degree of interbreeding that absorbed Neanderthal genetic lineages into the modern human gene pool rather than eliminating them entirely, and possibly disease transmission from modern human populations. Modern non-African humans carry roughly 1 to 4% Neanderthal DNA, on average a signature of interbreeding that occurred during the period of overlap in Europe and Western Asia. The Neanderthals did not simply vanish, they were to some degree absorbed. But as a distinct biological population they ceased to exist, and the evidence consistently points to the arrival of modern humans as the proximate trigger for their disappearance, whatever the specific mechanisms. The Denisovans, a hominin population known primarily from ancient DNA, extracted from fragmentary specimens found in Denisova Cave in Siberia, similarly disappeared with the expansion of modern humans across Asia, leaving behind a genetic legacy in the modern populations of Melanesia, Aboriginal Australia, and parts of Southeast Asia that descend from ancient interbreeding events. The picture of late Pleistocene human biogeography that has emerged from ancient DNA studies over the past 15 years is far more complex than the simple, out-of-Africa replacement narrative that dominated the field 2 decades ago. Multiple archaic hominin populations were present across Eurasia when modern humans arrived. Interactions between these populations and modern humans were more frequent and more varied than previously assumed, and the genetic legacy of those interactions is still detectable in living human populations today. The success of Homo sapiens, in the context of this larger story, is not a story of inevitable triumph. It is a story of contingency, of specific capabilities that happen to be extraordinarily valuable in the specific circumstances of the late Pleistocene. The combination of language-enabled cooperative planning, cumulative cultural transmission of technology, and the cognitive flexibility to adapt behavior rapidly to novel situations produced an organism that could, within a few generations, develop effective responses to new challenges, new prey species, new environments, new competitors that would otherwise require thousands of generations of genetic evolution to address. This is the key advantage of cultural evolution over biological evolution. It is faster, it is reversible, and it accumulates. A hunting technique that proves effective can be taught to every member of a group within days. An anatomical adaptation that proves useful takes hundreds of generations to spread through a population. In a world of rapid environmental change, the difference in speed between these two kinds of adaptation is the difference between survival and extinction. But the story of human success is also, from a certain angle, a story of significant biological fragility. Humans are not particularly fast compared to most large African mammals. They are not particularly strong. They have no natural armor, no effective natural weapons, and a reproductive rate that is low compared to most comparably sized animals. Human infants are born at a remarkably early developmental stage relative to other primates, spending years in a state of complete dependence on adult care that would be catastrophic for any individual whose social network failed. Human populations are vulnerable to disease in ways that reflect their evolutionary origin in relatively small, isolated groups that were never exposed to the range of pathogens that agriculture and dense settlement would eventually concentrate. Homo sapiens is, by the standards of large mammals, an animal with a remarkably narrow margin for error, dependent on social cooperation, stored knowledge, and accumulated technology in ways that no prior animal has ever been, and therefore vulnerable to disruptions of those systems in ways that prior animals never experienced. This vulnerability is easy to overlook from the perspective of a species that currently numbers nearly 8 billion individuals and has colonized every terrestrial environment on Earth. But the genetic evidence suggests that modern humans passed through one or more severe population bottlenecks at some point in their prehistory periods when the total human population was reduced to numbers that, by modern standards, seem remarkably small. Estimates of the minimum effective population size during the most severe bottleneck vary, but some analyses suggest periods when the total human population may have been as low as a few thousand to a few tens of thousands of individuals. A species with a global population smaller than a modern mid-sized city is, in demographic terms, at genuine risk of extinction, and the fact that modern humans are descended from a population that narrow suggests that the success we now take for granted was, at some point in the not-so-distant past, far from guaranteed. The hominin lineage had existed for 6 to 7 million years before Homo sapiens appeared. During that time, multiple hominin species had evolved, diversified, and gone extinct: Homo heidelbergensis, Homo naledi, Homo floresiensis, the Denisovans, the Neanderthals, and many others that left only fragmentary traces in the fossil and genetic record. The emergence of modern humans was not the inevitable culmination of a directed process toward a predetermined endpoint. It was the latest in a long series of evolutionary experiments in the hominin lineage, each of which represented a different combination of brain size, body proportion, technological capability, and behavioral flexibility, and each of which existed for a time before being replaced or going extinct. Homo sapiens is simply the one that is still running. The other hominin lineages were not inferior in any absolute sense. Neanderthals survived in Europe for hundreds of thousands of years through conditions that killed enormous proportions of other animal populations' ice ages, volcanic eruptions, dramatic climate oscillations. Homo floresiensis, the diminutive island hominin of the Indonesian island of Flores, survived until approximately 50,000 years ago in a highly restricted environment with limited resources, which required extraordinary behavioral flexibility and presumably a level of social cooperation that small body size and small absolute brain volume did not preclude. Homo naledi, discovered in the Rising Star Cave system in South Africa in 2013 by a team led by Lee R. Berger, had a brain the size of a chimpanzee's, but appears to have intentionally deposited its dead in a difficult-to-access underground chamber, a behavior with possible symbolic or ritual implications that is otherwise unknown in organisms with such small brains. What exactly Homo naledi was doing and why it was doing it is still being studied and debated, but its existence complicates any simple narrative about the relationship between brain size and behavioral complexity in hominins. The evolutionary success of modern humans, then, is not simply a matter of having the largest brain Neanderthal brains were larger on average, or of being the strongest, or the fastest, or the most physically formidable. It is a matter of having the specific combination of traits that happen to be most valuable in the specific environmental and ecological circumstances of the late Pleistocene and early Holocene. Language-enabled social coordination, cumulative technology, extraordinary behavioral flexibility, and the reproductive rate and dispersal capability to expand rapidly into new environments. Whether that combination continues to be advantageous in the environments that Homo sapiens is now creating, environments characterized by dense urban populations, global connectivity, and ecological disruptions at scales that have no natural precedent, is a question that the evolutionary record cannot answer, and that the geological record will eventually record, with characteristic geological patience, regardless of what the answer turns out to be. The ascent of humans is an extraordinary story. It is also, in the context of the 66 million year history we have traced in this documentary, a very recent one and a very small fraction of it. The social dimension of human evolution is frequently underemphasized in popular accounts, which tend to focus on brain size and tool technology as the primary drivers of human success. But there is a compelling argument that the most important evolutionary development in the human lineage was not any specific anatomical change, but the expansion of the scope and depth of social cooperation, the ability to coordinate behavior in groups of individuals who are not closely related, to share information and skills across generational boundaries, and to maintain what anthropologists call extended social networks, connecting hundreds or thousands of individuals through chains of reciprocal relationship. No other primate maintains social networks of this scale and complexity, and the implications for collective problem-solving are enormous. A group of 500 individuals sharing accumulated knowledge is not 500 times more capable than a single individual. It is orders of magnitude more capable, because it can simultaneously hold in active use a breadth and depth of specialized knowledge that no individual could maintain alone. The transition to fully modern language was probably the key enabling development for large-scale social cooperation, because language is not merely a communication system, it is a knowledge storage and transmission system that operates across time as well as space. Written language is often credited with enabling the accumulation of human knowledge, but oral traditions in non-literate societies routinely preserve detailed practical and historical knowledge across dozens of generations in a form that can be updated, corrected, and elaborated as new information is acquired. Language allows a community to collectively know things that no individual member knows in their entirety, drawing on that collective knowledge as needed without requiring any individual to be an expert in everything. This is the cognitive foundation of specialization, of trade, of division of labor, and ultimately of civilization, though civilization itself was still many tens of thousands of years in the future at the time we are discussing. The archaeological record of the period between 100,000 and 40,000 years ago shows a gradual but accelerating accumulation of behavioral innovations that reflect this expanding social and cognitive repertoire. Pigment used, particularly red ochre, which is ground iron oxide, appears at sites across Africa and the Levant in this period, in contexts suggesting symbolic or decorative use. Perforated shells that were apparently used as personal ornaments appear at coastal sites in Morocco and Israel, dated to approximately 80,000 to 130,000 years ago. Geometric engravings on ochre stones from Blombos Cave in South Africa, dated to approximately 75,000 years ago, represent some of the earliest clearly intentional symbolic markings known anywhere in the world. Long-distance transport of raw materials, obsidian, high-quality chert, shells across distances of hundreds of kilometers, provides evidence for exchange networks connecting distant communities in ways that imply not just trade, but the social relationships that make sustained trade possible. The question of whether these early behavioral innovations were produced by populations that were fully cognitively modern, or whether the full modern behavioral repertoire emerged gradually over tens of thousands of years, is one of the central unresolved questions in paleoanthropology. The evidence for symbolic behavior in populations outside of Africa, during the same period cave art, personal ornaments, musical instruments appears somewhat later, roughly correlating with the dispersal of anatomically modern humans out of Africa and into Eurasia around 60,000 to 70,000 years ago. Whether this reflects a genuine temporal difference in cognitive development, or simply the fact that African sites have been more intensively studied in some respects, or that the African behavioral record was preserved under different conditions, is actively debated and probably will continue to be. The dispersal of modern humans out of Africa represents one of the most rapid geographic expansions in the history of large-bodied mammals, and it was made possible not by any unusual physical capability, but by cultural adaptability, the ability to develop new technologies, new food processing methods, and new social strategies appropriate to radically different environments in a time frame far shorter than genetic evolution could manage. Modern humans reached Australia by approximately 65,000 years ago, crossing a substantial water gap that required at least some form of watercraft and the navigational knowledge to use it intentionally. They reached the Arctic by approximately 30,000 years ago, developing the specialized clothing, shelter, and food storage technologies necessary to survive winters that would be immediately fatal to an unequipped tropical primate. They reached the Americas, the last major landmass to be colonized sometime between 15,000 and 30,000 years ago, completing a global dispersal that had no precedent in the history of any single terrestrial species. The physical demands of surviving in radically different environments drove rapid biological as well as cultural adaptation in dispersing human populations. The well-known variation in skin pigmentation between human populations living at different latitudes reflects selection for UV protection in high UV tropical environments and for vitamin D synthesis in low UV northern environments, adjustments that occurred over tens of thousands of years of population differentiation after the dispersal from Africa. Adaptations to cold climates, high altitudes, and different dietary compositions also evolved in specific populations during this period, producing the phenotypic diversity of modern humans, while the underlying genome remained remarkably similar across all populations because the dispersal was recent enough that drift and selection have not had time to produce large genetic differences, and because there was sufficient gene flow between adjacent populations to prevent strong genetic divergence from accumulating. The relationship between Homo sapiens and the other great apes that are its closest living relatives provides a useful perspective on just how unusual the human trajectory has been. Chimpanzees and gorillas, which share a common ancestor with humans within the last 6 to 7 million years, are cognitively impressive animals by the standards of non-human primates. Chimpanzees use tools, engage in coordinated group hunting, have documented cultural traditions that vary between populations, and can solve complex problems that require multi-step planning. But chimpanzee technology has not accumulated over the past several million years the stone cracking and termite fishing techniques observed in modern chimpanzee populations are presumably not vastly more sophisticated than those practiced by their ancestors of the same species hundreds of thousands of years ago. The reason is the absence of sufficient cumulative cultural transmission. Individual chimpanzees can learn from observation, but the chain of transmission is short, the fidelity is imperfect, and innovations are not reliably preserved and built upon across generations in the way that they are in human cultures. The ratchet mechanism of cumulative cultural evolution, which preserves each innovation as a foundation for the next, appears to be specifically a human capability, enabled by language and the social structures that language makes possible. This ratchet mechanism is ultimately what separates the ecological impact of modern humans from that of every prior organism in Earth's history. A termite colony can construct impressive architectural structures, but termite architecture has not changed significantly in millions of years, because each generation essentially reinvents it from scratch using genetically inherited behaviors. Human technology, by contrast, has been accumulating and accelerating for hundreds of thousands of years, with each generation inheriting not just the physical artifacts produced by previous generations, but the knowledge of how to make and use them, and, crucially, the capacity to improve them. The rate of technological change in the human lineage has been accelerating, not decelerating, as the knowledge base grows, and as one innovation creates the foundation for further innovations. This is a pattern that has no analogue in biological evolution, where there is no comparable mechanism for the directed cumulative transmission of adaptive innovations across generations. It is worth noting that the Homo sapiens currently populating the planet are, in a very literal sense, the lucky survivors of a long and extremely unforgiving process. The fossil record documents dozens of hominin species that existed, diversified, and went extinct over the past 6 to 7 million years. The lineage that produced modern humans was not the only experiment, and it was not obviously the most likely one to succeed from the perspective of any observer watching the Pliocene African landscape unfold. Homo erectus, which survived for nearly 2 million years across a range extending from Africa to Southeast Asia, was by some measures a more ecologically successful species than Homo sapiens has yet managed to be, having persisted for a far longer time period, though admittedly without building any cities or launching any space programs. The survival of the modern human lineage through the population bottlenecks of the Pleistocene, through the climate fluctuations that eliminated other hominin populations, and through the competitive interactions with Neanderthals, Denisovans, and potentially other archaic human populations, required not just capability, but good fortune of a kind that is difficult to disentangle from the capability itself. The ascent of humans is an extraordinary story. It is also, in the context of the 66 million year history we have traced in this documentary, a very recent one and a very small fraction of it. If the entire Cenozoic era were compressed into a single year, modern humans would appear in the last few minutes of December 31st. Agriculture, cities, writing, and the entire recorded span of human civilization would occupy the final seconds. The Cenozoic was not waiting for us. It was not building toward us. It produced us as one product of a vast and indifferent evolutionary process that has been running without direction or purpose for as long as life has existed on this planet, and that will continue running with the same indifference long after any particular experiment, including the current one, has reached its conclusion. We are the latest chapter in a story that was not written for us, which makes the fact that we are here to read it, if anything, considerably more interesting. We have travelled a long way. 66 million years, roughly speaking, from the smoking crater in the Yucatan to the primate sitting in front of a screen watching a documentary about its own origins, at some hour that is probably later than intended. The full arc of the story, from the near-total biological collapse of the KPG extinction, through the slow rebuilding of oceanic and terrestrial ecosystems, through the extraordinary warmth of the Eocene, the isolation experiments of South America, the tectonic forces that reshaped continents and redirected evolution, the age of giants, and the disappearance of most of those giants in a geologically brief window of time is, in its totality, one of the most remarkable stories that the rock record has preserved for us to read. And the appropriate response to reaching the end of it, if there were such a thing as an appropriate response to 66 million years of planetary history, is probably not satisfaction. It is probably something closer to unease. Because the lesson of the Cenozoic is not a comfortable one. It is not a story about stability, or about progress towards some predetermined endpoint, or about the inevitable triumph of complexity over simplicity. It is a story about a planet that has never, at any point in its 4.5 billion year history, stopped changing and that shows no signs of starting now. The tectonic plates are still moving. The Atlantic Ocean is still widening at roughly the same rate as your fingernails grow, which sounds slow until you consider that fingernails growing for 50 million years would extend from the Earth to the Moon several times over, and that the Atlantic has been widening for approximately that long. The East African Rift, which we discussed in the context of hominin evolution, is still deepening and widening, and in another 10 to 20 million years, Eastern Africa will have separated from the rest of the continent, creating a new ocean basin where the Horn of Africa currently sits. The Indian subcontinent is still pushing northward into Asia, still contributing to the ongoing uplift of the Himalayas and the continuation of the monsoon systems that those mountains generate. The Pacific Plate is still moving northwestward, carrying the Hawaiian Islands with it, and building new volcanic islands over the hotspot that has been producing the archipelago for tens of millions of years, which means that the Big Island, currently over the hotspot and geologically young and actively volcanic, will eventually move away from it in the same way that the older, more eroded islands have, and a new island is already building on the seafloor to its southeast. Geology, unlike history, does not go on hiatus. The climate system is similarly in a state of continuous change that did not pause for human civilization and will not pause after it. The Pleistocene Ice Age cycles, driven by Milankovitch orbital variations, the rhythmic changes in Earth's axial tilt, orbital eccentricity, and the timing of seasonal proximity to the Sun are ongoing, and without the complication of anthropogenic greenhouse gas emissions, the planet would be expected to cool slowly into the next glacial maximum over the next several tens of thousands of years. The carbon cycle, which operates on timescales from seasons to millions of years, and which the PETM illustrated, can produce dramatic and rapid climate shifts when large carbon reservoirs are destabilized, is currently being perturbed by human activities at a rate that, in the geological record, would look distinctly abnormal, comparable to, and in some respects faster than, the rates of carbon released during the PETM itself. The geological record of the PETM shows us what a rapid large-scale carbon injection does to Earth systems. It warms the planet, acidifies the oceans, disrupts ecosystems at a global scale, and takes tens of thousands of years to fully reverse. It also shows that life survived, but that the specific community of organisms that survived was radically different from the one that existed beforehand, because the ones best adapted to the pre-event conditions were largely replaced by ones better suited to the new conditions. This is the genuinely important lesson of the PETM, and of the KPG extinction, and of every other major perturbation documented in the Cenozoic record. Earth systems are resilient, but that resilience operates on timescales that are entirely indifferent to the concerns of any particular species. The planet survived the end Cretaceous impact. Life recovered. The fact that the recovery took 10 million years and produced a biosphere that was completely different from the Cretaceous one is not a qualification to the statement that life survived. It is a clarification of what surviving means when you're talking about a planet rather than an organism. The planet does not care which specific collection of species constitutes its biosphere at any given moment. It has replaced its entire biological community multiple times already, with considerable creativity and without apparent distress. The question, then, is not whether the Earth will survive whatever comes next. It will. The geological record provides essentially no scenario, short of the planet being physically destroyed, in which life does not eventually persist and diversify. The question is specifically about the organisms currently in residence US, and the ecosystems on which we depend, and whether the rate and scale of current changes fall within the range that those organisms can adapt to, either biologically or culturally, within the time available. And the Cenozoic record, when examined honestly, does not provide particularly reassuring precedents for organisms that are large-bodied, slow reproducing, ecologically specialized, and highly dependent on the continued functioning of complex stable ecosystems. The rate of current species loss, measured against background extinction rates from the fossil record, is already substantially elevated. Estimates place current extinction rates at between 100 and 1,000 times the background rate, which puts the current period in the territory of a genuine mass extinction by any geological standard. The causes are familiar from the Pleistocene story: habitat destruction, hunting and overharvesting, the introduction of invasive species to new environments, climate change and chemical pollution, operating simultaneously and synergistically in ways that amplify each other's effects. The target organisms are, again, disproportionately the large-bodied, slow-reproducing species, the megafauna of the modern world that are most vulnerable to even modest levels of additional mortality and least capable of rapid demographic recovery. The parallel to the late Pleistocene extinction is not coincidental. It is the same process, operating at an accelerated rate with more sophisticated tools and a more densely connected global human population. The ocean acidification story, which we examined in the context of the KPG extinction and the PETM, is currently unfolding in real time. Ocean pH has dropped by approximately 0.1 units since the beginning of the industrial era, which sounds small but represents roughly a 30% increase in hydrogen ion concentration, because pH is a logarithmic scale. The rate of acidification is faster than anything documented in the geological record except for the immediate aftermath of the Chicxulub impact, which is not an encouraging comparison. Calcareous marine organisms, corals, mollusks, some plankton groups are already showing measurable impacts in locations where acidification is most advanced. Coral reefs, which we noted took millions of years to rebuild after the KPG extinction, are currently experiencing bleaching events of increasing frequency and severity, driven by the combination of warming and acidification that constitute a particularly unfavorable combination for coral physiology. What the Cenozoic record provides, which is genuinely valuable, is a calibrated sense of what Earth systems are capable of both in terms of disruption and in terms of recovery. The planet has experienced temperature increases of 5 to 8 degrees Celsius within geologically brief periods, the PETM being the most relevant example, and while those events produced severe ecological disruption and substantial extinction among vulnerable groups, they did not produce a sterile world. They produced a different world, and that distinction matters enormously for how we think about the consequences of current climate change. The pessimistic reading that rapid warming will trigger mass extinction and ecological collapse comparable to the PETM or worse is supported by the geological record. The optimistic reading that life is resilient and the planet will recover is also supported by the geological record. Both readings are correct. They simply apply to different timescales and different collections of organisms. The specific vulnerability of human civilization as opposed to the human species, and as opposed to life in general, is in some ways more acute than the vulnerability of most of the organisms that went extinct in the PETM or the KPG event, because civilization depends on a set of ecological and climatic conditions that are far more specific and far more narrowly defined than the conditions required simply for human biological survival. Humans can survive in environments ranging from the Arctic to tropical rainforests to high-altitude deserts. Human civilization, as currently organized, depends on predictable agricultural productivity across specific latitudinal bands, on stable coastlines that support the enormous concentrations of infrastructure and population in coastal cities, on water availability in regions where water supply is already stressed, and on the continued functioning of marine fisheries, forest carbon sinks, and a range of other ecological services that are themselves dependent on the continued functioning of the ecosystems that provide them. The 8,000 years of relatively stable, warm, post-glacial climate that coincided with the development of agriculture and the rise of human civilization is, in the geological record, an unusually stable interglacial period. It is not the norm. It is a brief window of climatic stability embedded within the Ice Age cycles of the Pleistocene, and the organisms and ecosystems that human civilization has built its foundations on were selected over the preceding millennia for precisely the conditions that prevailed during that window, changing those conditions whether by shifting precipitation patterns, raising sea levels, intensifying extreme weather events, or altering the seasonal timing of temperature and precipitation, is not simply an inconvenience to be managed. It is a restructuring of the ecological substrate on which civilization as currently constituted depends. This sounds grave, and it is. But it is also, viewed from the broader Cenozoic perspective, a situation that previous life on Earth has navigated not identically, not without enormous losses, but navigated nonetheless. The small mammals that huddled in burrows through the impact winter of the KPG event were facing conditions incomparably more severe than anything projected under current climate scenarios, and they came through. The organisms that survived the PETM and diversified in its aftermath produced some of the most ecologically complex and biologically diverse communities that the Cenozoic has seen. The capacity of life to find a way through disruption is one of the most robustly documented facts in the entire 3.8 billion year history of biology. What the Cenozoic also shows, with equal clarity, is that there are no free passes. Every organism that survived a mass extinction or a major climate event survived because it happened to have the right traits in the right place at the right time. The traits that matter in a crisis are not the ones that were most valuable in the prior stable period. They are the ones that allow persistence through the disruption itself, flexibility, low energy requirements, tolerance of variable conditions, the ability to exploit new resources as old ones disappear. The organisms that specialize too deeply in a particular set of conditions, that built their ecological strategies around the assumption that those conditions would continue indefinitely, were the ones that disappeared when the conditions changed. Humans have one capability that no previous organism facing a major environmental disruption has possessed. We can read the geological record of past disruptions, understand what caused them and what happened as a result, and use that understanding to inform our responses to current challenges. The ferns that colonized the KPG landscape had no idea why the forests had burned. The small mammals that emerged from their burrows into the post-impact fern fields had no model of atmospheric chemistry or radiative forcing that helped them understand why the sky had gone dark. They simply responded to the immediate conditions with the behavioral repertoire they had, and the ones whose repertoire was adequate survived. We have something they did not: the capacity to look at 66 million years of documented Earth history and draw lessons from it that are applicable to the present. Whether we use that capacity effectively is a question that is still being answered in real time. The Cenozoic record does not tell us what we will do. It tells us what is possible and what has consequences. It tells us that the planet responds to large, rapid inputs of carbon by warming, by acidifying its oceans, and by restructuring its ecosystems on timescales of tens of thousands of years. It tells us that large-bodied, slow-reproducing species are disproportionately vulnerable to both climate change and direct human pressure. It tells us that ecosystems simplified by the loss of keystone species undergo cascading changes that are difficult to predict and expensive to reverse. These are not warnings, they are observations. They are the geological record speaking in the only language it has: cause and effect, played out over the timescales in which planetary systems operate. The Cenozoic is not finished. The tectonic forces that have been operating for 66 million years are still operating. The climate cycles that have been driving ice ages and warm periods for millions of years are still cycling. The evolutionary processes that have been producing new species and eliminating old ones since the first cells appeared in the ancient ocean are still running. The particular configuration of the biosphere that exists today, including the 8 billion Homo sapiens currently inhabiting it, is not a destination. It is a moment in a process that has no destination, that has no predetermined arc, and that does not, as far as the geological record can tell us, particularly care about any specific outcome. What the Cenozoic tells us about the future is not a prediction. It is a perspective. It is the perspective of deep time of 66 million years of continuous change, of ecosystems built and destroyed and rebuilt in configurations that no prior time could have predicted, of species emerging from apparently hopeless circumstances and going on to fill the world in ways that would have seemed impossible from the vantage point of their own dark age. It is the perspective that the organisms sitting in burrows through the impact winter could not have had, but that we, inheritors of the entire documented history of their world, can at least try to hold. The Cenozoic lesson is this: the planet does not rest, it does not repeat, and it does not owe any particular outcome to any particular organism. It is indifferent in the way that physics is indifferent, not malevolent, not benevolent, simply operating according to its own rules at its own pace with no interest in whether any specific experiment succeeds or fails. We are one experiment among many. We are the experiment that is currently running. Whether the experiment continues, and in what form, depends on choices that are being made now, which is a remarkable amount of agency for a 6 million year old lineage of slightly peculiar primates to find themselves possessing. The story that started with a rock and a dark sky and a world of ferns has not ended. The specific parallels between the geological past and the present moment are worth examining in considerably more detail, because the Cenozoic record is not just a set of general principles about Earth system behaviour. It contains specific quantified precedents that speak directly to the situation we currently find ourselves in, with a precision and specificity that is sometimes underappreciated in discussions that treat the geological past as merely metaphorical background. Consider the rate of current sea level rise in the context of Cenozoic sea level history. The geological record documents sea levels fluctuating by 100 to 120 metres between glacial maxima and interglacial periods over the Pleistocene Ice Age cycles, and sea levels substantially higher than today during the warmer periods of the early and middle Cenozoic. Estimates for Eocene sea levels range from 50 to 100 metres above present. These numbers tell us what the equilibrium sea level is at different temperature baselines. A world that is 5 to 8 degrees warmer than today, like the PETM, has no polar ice sheets and sea levels that make a large proportion of current coastal infrastructure permanently unavailable. The ice sheets that would melt to produce this outcome are not immediately responsive to temperature. They take thousands of years to fully collapse, but the geological record shows that once the warming is sustained, the ice eventually goes and the sea level eventually rises to match the new equilibrium. The Cenozoic does not tell us exactly when, but it tells us very clearly by how much. The loss of biodiversity that is currently occurring while you're reading this, not as a historical abstraction, is documented well enough in both the fossil and biological records to allow meaningful comparison to past extinction events. The Cenozoic record shows that recovering from a major extinction event to something approaching the prior diversity takes on the order of 5 to 10 million years. It shows that the specific species lost in an extinction event do not come back. Evolution produces new species to fill the vacated ecological roles, but those new species are different organisms in different lineages, not the same organisms restored. The woolly mammoth is gone and will remain gone despite the considerable enthusiasm of some researchers for de-extinction technologies. What any de-extinction program might eventually produce would be a novel organism with some mammoth genetic characteristics, not a restored population of a functioning Pleistocene species embedded in a functioning Pleistocene ecosystem. The ecosystems that mammoth populations shaped and maintained are themselves gone, replaced over the past 10,000 years by vegetation communities organised around the absence of mammoths. Restoration is, in the strict sense, not available as an option. Adaptation to what exists and preservation of what remains are the options the Cenozoic record leaves open. The nitrogen and phosphorus cycles, the biogeochemical processes that move these essential nutrients through ecosystems and that underpin the productivity of most terrestrial food webs, have been substantially altered by human agriculture, which now fixes more nitrogen from the atmosphere annually than all natural processes combined. The runoff of excess agricultural nitrogen and phosphorus into aquatic systems produces what ecologists call eutrophication, the over-fertilization of water bodies that generates explosive algal growth, oxygen depletion in bottom waters, and the collapse of aquatic food webs in affected areas. The dead zones that develop in coastal waters receiving agricultural runoff areas of oxygen-depleted water, unable to support fish or most invertebrates, are among the most visible current examples of human-driven ecosystem disruption, and they have geological precedence in the oxygen depletion events documented in ancient ocean sediments during periods of elevated nutrient input. The sediment record of past eutrophication events shows them to be reversible when nutrient inputs decline, but the recovery timescales are decades to centuries, not years. There is no rapid fix for a nutrient-disrupted ocean system, as the history of the Baltic Sea, one of the most severely eutrophied bodies of water on Earth, has demonstrated with stubborn consistency over several decades of management efforts. The story of nitrogen is interesting also because it illustrates a less commonly discussed aspect of the relationship between the current moment and the Cenozoic history we have traced. The degree to which the biological systems operating today are still, in many essential ways, the systems rebuilt from the KPG aftermath and elaborated through 66 million years of Cenozoic evolution. The mycorrhizal fungal networks that connect forest trees underground and allow nutrient sharing across plant communities are the descendants of fungal lineages that were among the critical agents of ecosystem recovery after the KPG impact. The nitrogen-fixing bacteria in the root nodules of legumes, a symbiosis that underpins a significant proportion of terrestrial productivity, are lineages with deep Cenozoic roots. The bees and other pollinators that service modern flowering plant communities are the inheritors of the flower-pollinator relationships that were already diversifying in the Eocene warm forests. Every ecological interaction currently operating in the modern world has a Cenozoic history, and that history matters for understanding the resilience and vulnerability of those interactions to current disruption. The question of what the Cenozoic tells us about the pace of potential evolutionary adaptation to current environmental change is perhaps the most directly relevant one, and the answer is not particularly comforting. Evolutionary change in response to new selective pressures occurs at rates that vary enormously depending on the organism, the intensity of selection, and the available genetic variation. For bacteria and viruses, with generation times measured in hours and enormous population sizes that provide abundant genetic variation, evolutionary change can be effectively immediate bacterial resistance to antibiotics develops within years, and influenza viruses evolve rapidly enough to require new vaccines annually. For large-bodied, long-lived organisms with generation times of years or decades, meaningful evolutionary change in response to sustained selection pressure requires hundreds to thousands of generations, which translates to timescales of thousands to tens of thousands of years. The large mammals, birds, and other organisms most vulnerable to current environmental changes are precisely the ones with the longest generation times and slowest evolutionary rates. The Cenozoic record of rapid environmental change, the PETM, the late Pleistocene climate shifts consistently shows that large-bodied specialized organisms are the most likely to go extinct during rapid change events, and the least likely to evolve quickly enough to track the changing conditions. Cultural evolution is a different matter, and here the human case is genuinely unique. As discussed in the previous chapter, the rate of cultural and technological change in human populations has been accelerating for hundreds of thousands of years and shows no signs of decelerating. The speed at which new technologies relevant to environmental challenges, renewable energy systems, agricultural efficiency improvements, carbon capture approaches, conservation management tools can be developed and deployed through human cultural transmission has no biological parallel and creates possibilities for addressing environmental challenges that would be entirely beyond the capacity of any other organism. This is a real and significant advantage, and dismissing it would be as much an error as dismissing the scale of the challenges that the Cenozoic record documents. The problem is not human ingenuity. The problem is the mismatch between the timescale on which human political and economic systems respond to diffuse, long-term risks, and the timescale on which the geological and biological consequences of current activities will unfold. The carbon dioxide released by burning fossil fuels stays in the atmosphere and influences climate for thousands of years. The species currently going extinct will not be recovered for millions of years. The aquifers being depleted by current agricultural practices accumulated their water over thousands to tens of thousands of years, and will not be refilled in any time frame relevant to the civilizations currently depending on them. Human political systems, economic incentive structures, and individual decision-making horizons typically operate on timescales of years to decades, occasionally centuries in the case of the longest-lived institutions. The mismatch between the timescale of decision and the timescale of consequence is the deepest structural challenge that the Cenozoic record highlights for the current moment. This is not a new observation. It is, in fact, one of the oldest observations in environmental science, and the persistence of the mismatch despite broad awareness of it tells us something important about the constraints on human collective action. Knowing that a course of action will have severe consequences 100 years from now does not automatically produce the behavioral changes necessary to avoid those consequences, any more than knowing that mammoths were slow reproducing made the Pleistocene hunters adjust their hunting rates to sustainable levels. The capacity for foresight is one of the things that makes humans unique, but it does not automatically translate into the exercise of foresight in collective decision-making, as the geological record of the past 50,000 years somewhat uncomfortably demonstrates. What the Cenozoic ultimately offers, beyond the specific factual precedents discussed throughout this chapter, is a shift in perspective that is itself valuable, regardless of what it implies for specific policy or behavioral choices. It is the shift from thinking about the present as the culmination of history to thinking about the present as a moment within a continuing process, a process that has been operating for billions of years before the present moment, and that will continue operating for billions of years after it. This shift does not make the current challenges less urgent. It does not provide comfort about outcomes that are likely to be difficult regardless of choices made now. But it does provide a certain clarity about what is at stake and what is not. What is not at stake, in any realistic assessment of the current situation, is the survival of the planet or of life in general. The planet has survived conditions incomparably more severe than anything currently projected, and life has persisted through every major disruption, the geological record documents emerging each time in new configurations that the prior world could not have predicted. The resilience of life at the planetary scale is genuinely extraordinary, and the Cenozoic record from the fern fields above the KPG boundary to the warm Eocene forests to the rebuilt ocean of the Paleogene provides ample documentation of that resilience. What is at stake is considerably more specific. The particular configuration of ecosystems, species, and ecological relationships that currently exists, and the particular version of human civilization that has developed within and depends upon those ecosystems. These are worth caring about, not because the planet needs them, it does not, and it will produce replacements in due course, but because we need them, and because the capacity to understand and act on that need is one of the specific capabilities that makes the human experiment, for all its considerable flaws, genuinely remarkable in the context of the history we have traced tonight. The story that started with a rock and a dark sky and a world of ferns has not ended. It is still going. You are part of it, whether you signed up for that or not. And on that note, wherever you are watching from in your city, at your hour, in whatever corner of this restless, never-still planet you happen to occupy, thank you for making it to the end of this one. Sleep well and dream of something ancient. Good night.